Statistics is really all about data, so I want to spend a little time in this video introducing the idea of data and talking about the most simplest kind of data that we'll deal with in this course. You can think about data just as information. So when I say data, just think information in general. And let's say, for example, I have some data here about people and their heights. So I have Wendy, Michael, Rachel, and Alan, and their corresponding heights. There's actually a lot going on here with the data that's in this table. So first of all, let's go back to our data information correlation here. So we have information about people and the height of each of those people. So since this is just information here, I could think about this as data. So I have data, not just information. I have data about people and their heights. Because I've arranged this data into a table, we can call this thing here a data table. So when we put our information or put our data into a table where we have a header here across the top or down the side, and then we have our data collected and summarized in a table format, we call it a data table. And we have different types of information inside of this table. So first of all, we have the people, and the people we call individuals. So we would say these are the individuals. Now it's important to say that individuals aren't always people. They can be cases, things, studies, all different kinds of objects. So when we say individuals, we don't just mean human people. We mean sort of the object around which the data is based. So we have a table here about people, and then we've recorded the height for each person. So this table is really focused on each person. So the people are the individuals in this case. And then the height here, we've recorded the height for each one of them. The height is what we call a variable. So we call this a variable. And a variable is just a property of each individual. So we always have variables recorded for individuals. Notice here that we have one variable for each individual, but we could have more than one variable. So for example, let's look at a different table. This one is about ice cream. So notice here that we have the individuals in the first column. This time they're not people, they're flavors of ice cream. So remember we said before that individuals don't necessarily have to be people. They're just sort of the subject of the table. So we have the flavors of ice cream down the left-hand side, but this time we have three variables, not just one. So these here are the variables in our table. And we've recorded the value of each of our three variables for every individual. So this is the data for an ice cream shop for 1 month, and we're recording the number of scoops that were sold of each flavor, whether or not that flavor contains chocolate, and whether or not that flavor is smooth or chunky. So is it totally consistent, or does it have chunks in it? So for example, cookies and cream, the third row in our table, that has those cookie pieces in it, so it's a chunky flavor. So we have three variables, and one thing we notice right away about these variables is that the scoops sold variable is numerical, it's numbers, versus contains chocolate and smooth or chunky, we've got those variables recorded in words. So it's important to realize that variables don't always have to be numbers. Here we had heights, that's kind of a number. We have feet and inches, or we could have converted each of those heights into just inches alone. And scoops sold here, we have a number, but our variables don't always have to be numbers. In fact, when our variables are numbers, we call them quantitative variables. So this scoop sold here would be a quantitative variable because it's a quantity, it's a number. We can count the number of scoops sold, we can assign a numerical value to that, we express it as a number. But these two variables are not expressed as numbers, we're expressing those in words. We call those categorical variables. One thing we always want to be able to do with data tables is to describe the individuals and the variables and say whether the variables are quantitative or categorical. So for example, in our first data table about the heights of people, we would say that our individuals are people, that we have one variable for those people about height, and that height variable is a quantitative variable. In our data table here for ice cream, we would say that the individuals are the ice cream flavors, and we've collected data for 3 variables about those individuals, one of which, scoops sold, is quantitative, and 2 of which, contains chocolate and smooth or chunky, are categorical. Now, both of these tables, both of these examples, are examples of one-way data, as opposed to two-way data, which we'll talk about later. So one-way data is data that's focused on or collected about just the single individual. Another way to make sure that you're dealing with one-way data is to think about how many questions you have to ask. So for example, with our ice cream table here, if someone says, "How many scoops of ice cream did you sell?" you would only have to ask one question. You would say, "For which flavor?" And they'd say, "Oh, for chocolate," and then you would answer 450 scoops. We sold 450 scoops for chocolate ice cream. Or for this table here, if someone asks you, "How tall is the person?" you only have to ask one question, "Which person?" They'd say, "Oh, Rachel," and you could answer then 5'3". So you only have to answer one question if the data represents one-way data. When you have two-way data, you'll have to answer 2 questions, but again, we'll get more into that later. Now, the only other thing you want to think about when you're talking about one-way data tables is the number of individuals that you have compared to the number of variables that you have. In both of these tables, we had more individuals than variables. So in this table, we had 4 individuals, Wendy, Michael, Rachel, and Alan, and just one variable, height. In this table, we had 6 individuals, vanilla, chocolate, cookies and cream, mint chocolate chip, fudge brownie, and rocky road. So 6 individuals, and just 3 variables. When you have more individuals than variables, you're usually going to go ahead and list the individuals down the left-hand side of the table, and then put the variables across the top of the table before filling it in. But sometimes you might have the opposite situation. You might have a smaller number of individuals and lots of variables, or just more variables than you have individuals. And usually in that case, it's helpful to flip the orientation of the table. So let's look at this last table here, which is information about 2 houses that are for sale in your neighborhood. So here we have 2 individuals, 317 Spruce Road and 819 Lilac Street. Those are 2 different houses for sale in your neighborhood. And you've gone and collected all of this information about both houses. So we have 2 individuals and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, it looks like, variables for 2 individuals. So in that case, it's much better for us to write the individuals across the top and all the variables down the left-hand side. If we tried to do this table in the same way that we did the tables for ice cream and people and their heights, it would be extremely wide. We would have 317 Spruce Road and 819 Lilac Street down here on the left, and then we would have all these variables listed out to the right here across the top, and the table would be way too wide to be useful. So when that's the case, flipping the orientation of the table and putting the individuals on the top and the variables down the left-hand side is really helpful and makes the table a lot easier to read. So as you're creating and analyzing data throughout this course, just remember that one-way data is when we have one or more variables, they could be quantitative or categorical, for one or more individuals, where the individuals could be people, they could be ice cream flavors, they could be houses, it doesn't matter, but one or more variables for the individuals. And if we want to know for sure that this is one-way data, we just need to ask ourselves, how many questions do we have to ask? And give ourselves an example. So if somebody says in our third table, how many bedrooms does the house have? We only have to answer one question, which is, which house? We've already looked at one-way data and how to organize one-way data in a data table. Now we want to talk about different ways that we can visualize that one-way data, 2 of which are going to be bar graphs and pie charts, and that's going to be the focus of this video. So let's say, for example, that we have this one-way data table here. And this data table shows us the host cities for the Summer Olympic Games. We have the host city and country, so Athens, Greece, Paris, France, the cities and countries for each Summer Olympic Games going back to 1896. What we want to do is summarize this one-way data by continent. Obviously, it's great that we have this super long list here of information, but what we're really trying to do is get a feel for how often each continent has hosted the Summer Olympic Games. So what we could do is we could actually simplify the one-way data that we have into a simpler table. So for example, we could count up the number of times that each continent has hosted the game. So for example, North America, we could say they've hosted once, twice, 3, 4, 5, 6 times. So we can see North America has hosted 6 times. We could do that for each continent and then summarize our results in a separate one-way table. And we would see that we could get a count by continent for the summer games. So let's just go ahead and call this the summer games here. Already, we've simplified the data in our original one-way table significantly, and we just have this smaller one-way table of the number of times each continent has hosted the summer games. But there are other ways that we can visualize this. For example, we could make a bar graph out of this data. We want to start here by creating a chart. So we could draw some lines like this, and we could label these as 0, 5, 10, 15, and 20. And then we could go ahead and start sketching in a bar that matches each of the continents in our one-way table. So for example, Europe has hosted the Summer Games 16 times. So we could draw a bar up to about 16, and we could go ahead and call that Europe. Notice that the bar starts at the bottom of the chart and extends all the way up to about 16 here based on this vertical axis. North America's hosted the game 6 times, so we could go ahead and draw another bar next to the first one. It starts at the bottom and goes up to about 6, and we could call this one North America. Asia has hosted the games 3 times, so we could draw a bar at about 3 and call that Asia. Australia has hosted twice, so we'll call this Australia. And then South America has hosted once, so we could call this South America. And this is now a bar graph that represents the data in the original one-way table. So the reason that this is so helpful is because it can give us quickly a great visual picture of the data that's in this table. So if we're given this huge table to start with, yes, we have all the information here, we have all the detail, and we can count up the continents, we can look at the dates, we can sort of think about and analyze what we see in here, but we can't just glance at this and get a quick visual picture. So for example, if I gave you this table and said, who's hosted more Summer Olympic Games, North America or Australia, you might be able to see it just at a glance, but you'd need to go through and scan and count the number of times North America has hosted, then go back through the table and count the number of times Australia has hosted. But if we have a bar graph of that information, we can see right away North America's bar is higher than Australia's bar, so we know immediately it's hosted more times. Even if we didn't have this vertical axis over here on the left, we would know that North America has hosted more than Australia simply because the bar is bigger. We can also get estimates from the bar graph. So even when every increment of this vertical axis here isn't marked off, so we only have increments of 5, not every increment of 0, 1, 2, 3, 4, 5, etc., we can still say right away that Europe has hosted more than 15 times and less than 20 times, because we can see that the bar extends above 15 but doesn't make it to 20. And we could probably guess that it's hosted about 16 or 17 times based on where that bar is. Same thing here with North America. We know immediately it's hosted more than 5 times, but fewer than 10 times, and we would probably guess that it's hosted 6 times, maybe 7 if we're not sure. And we can see immediately that Asia, Australia, and South America have each hosted less than 5 times. Asia the most, then Australia, then South America. So this is just a great visual way to summarize a lot of data. We can also build bar graphs horizontally. So this bar graph is really vertical because the bars extend up and down, they extend vertically. But we could also build a horizontal bar graph. So instead of sketching our lines here horizontally, instead we would sketch them vertically, like this. And then just like we marked off our increments here, we would mark them off this way. So we could say 0, 5, 10, 15, and 20, like this. And then we could go in and sketch each bar, but this time horizontally. So we could show here Europe extending from 0 all the way up past 15 to 16 here, in the same way that Europe extended from 0 up to 16 here. And so then we could go ahead and call this Europe. We know that North America is hosted 6 times, so we would draw that bar up past 5. So that would look like about this, and we would call that North America. Asia has hosted 3 times, so we could sketch that in there. Australia twice, so this would be Australia, and then South America once, and so we could draw that in and label South America. And this is the exact same bar graph as the one we drew up here, except that this is a horizontal orientation for a bar graph instead of a vertical orientation, because the bars extend horizontally from left to right. And just like the first bar graph, this gives us a quick visual picture of the data that was in the original table, and we can make quick conclusions about the data, like the fact that Europe has clearly hosted the most games by far. Keep in mind that when we build these bar graphs, not always, and you certainly don't have to do it this way, but it is common to show the largest bar here on the left in a vertical bar chart extending out to the smallest bar on the right, or to show the largest bar here at the top in a horizontal bar chart extending down to the smallest bar down at the bottom, especially if the order of the individuals here doesn't really matter. So sometimes, for example, we can build a bar chart that shows data for the months of the year, so January, February, March, April, May. In a situation like that, where the order of the individuals is important, we would maybe expect it to be in calendar year order, starting with January, extending through to December. We would keep the data in that order, and you would see maybe the bars go up and down, for example. And it would make more sense to have January and then February and then March. But in this case, the fact that we have Europe, North America, Asia, Australia, South America doesn't really make any difference. We just as easily could have had Australia, North America, Asia, Europe, then South America, and it would have been just as logical. And so in that case, when it doesn't really matter what the order is, it's nice to arrange the data so that the largest bar is either on the left or at the top, because that just allows us to really quickly get a visual picture of whichever category has the most data down to whichever category has the least. Another great way to visualize one-way data is with a pie chart. And in a pie chart, what we're really doing is we're graphing each of these values as a percentage of a circle, or you can think of it as a piece of a pie. The way that we do that is first by finding the total of this count here of the values we have. So again, we're going to use this summary here of Summer Olympic Games by host continent. So if we add up the total of all these counts, 16 plus 6 is 22, plus 3 is 25, plus 2 is 27, plus 1 is 28. So the total count is 28. Then what we want to do is figure out the percentage of the total that each count represents. So Europe hosted 16 of the 28 total games. So if we take 16 divided by 28, we get approximately 57%. If we take 6 divided by 28, so 6 divided by 28, we get approximately 21%. If we take 3 divided by 28, we get about 11%. Here we get about 7%. And 1 divided by 28, we get about 4% approximately. What we want to do then is sketch a circle, or again, you can think about it as a pie, and shade in about 57% of the circle to represent Europe. So here's what that would look like. We would take a circle and we'd sketch about 57% of it, and that would represent Europe. And it's really helpful when you're building a pie chart because it's hard to tell that this piece is exactly 57%, it's really helpful to give some extra indicator. So the fact that this represents Europe, we could put 16 here to indicate that it's Europe. And then North America has hosted about 21% of the time. So 21% of the area of a circle looks approximately like this. And we could go ahead and put a 6 there to indicate North America. 11% of the area of a circle is about this much more, and that's Asia, which is hosted 3 times. And then Australia at 7% of the total area has hosted twice, and South America has hosted once, and so we could put a 1. The other thing that's great to include with a pie chart is a key. So notice that we put here each continent in a different color. If we had done them all the same color, you wouldn't be able to see the boundary between each section of the pie. So you always do them in different colors, and you usually organize them if you can. And again, if the order doesn't matter, largest to smallest. So notice here that we have this biggest piece here for Europe, and then the next biggest piece is North America, the next biggest is Asia, then Australia, then South America, in the same way that we organized the bar chart from largest to smallest. And so we'll go ahead and call this our pie chart. As I said, we also want to include a legend so that we can tell that this 16 portion here actually represents Europe. So because we have these color-coded, we could color code our legend and just say here that red is Europe, that this is North America in yellow, that white represents Asia, and that we have then Australia in light blue and South America in dark blue. The last thing I want to talk about is that bar graphs are also a great way for displaying data side by side. So let's say here that we have data about not only the Summer Olympics, but also the Winter Olympic Games. If I wanted to, I could display both summer and winter data side by side in a bar chart. Obviously, I could add things together. So for example, I could add Europe's pieces together, 16 and 14, and get 16 plus 14 is 30, and then just show one bar for Europe that says they've hosted 30 times. But it would be much more interesting to keep the detail and display both side by side. So the way that we would do that is, again, we would sketch lines here if we're going to do a vertical bar chart. Notice that the largest value across both data tables is still 16, and the smallest is 1. So we can go ahead and label these axes here 0, 5, 10, 15, and 20. If we go up to 20, then our max value of 16 will still be contained within the chart. So we're good there. And then what we want to do is, remember, we already plotted or sketched the data for the Summer Olympic Games. So for the Summer Olympics here, we said Europe has hosted 16 times, that this was North America hosting 6 times, that this was Asia hosting 3 times, Australia twice, and South America once. So this is the same bar chart that we had before for the Summer Olympic Games. But now what we can do is display data about the Winter Olympic Games side by side with the data about the Summer Games. So for example, for Europe, we could go ahead and plot this count of 14 to say that Europe has hosted the Winter Games 14 times. So we would go ahead and plot that, starting down at the bottom again and rising up to 14 just below the 15 line to indicate that Europe has hosted the Winter Games 14 times. North America has hosted the Winter Games 6 times, so we could go ahead and plot that next to their summer total. And then Asia has hosted the Winter Olympics 3 times, so we could go ahead and plot that there. Notice that Australia and South America don't appear on our Winter Olympic chart, and that's because neither of those continents has ever hosted the Winter Olympics. And that's another important point to make about bar charts. If the count for something is 0, you just show no bar at all. So because Australia has never hosted the Winter Olympics, we'll just leave this spot blank. We won't show a bar for the Australian Winter Olympics. That'll indicate to us that they've hosted 0 times, and because it'll also be missing for South America, we'll know that South America has hosted the Winter Olympics 0 times as well. Now, just like with a pie chart, we want to indicate a legend for this bar chart because we want to make sure that people know that this red color here represents Summer Olympics and yellow represents Winter Olympics. So we could go ahead and indicate here with color Summer Olympics and then with color Winter Olympics like this so that people know. And sometimes people will shade in these bars instead of with color with some kind of a pattern. For example, if they were going to use maybe dots or something, they might say that the pattern for Summer Olympics is dots, and then the pattern for Winter Olympics is lines this way. So if you don't have color, you can still pattern the bars differently so that you can have the legend and see the difference between Summer and Winter Olympics. And just like before, this bar chart gives us a lot of really great information at a glance. So we can say similar things as before. For example, Europe has clearly hosted, by far, the most Summer Olympics and the most Winter Olympics, and clearly has the largest combined total, because even if we added the totals together for North America, if we imagine stacking this yellow bar on top of the red bar, it wouldn't even reach, we don't think, the yellow bar here for Europe. So Europe has hosted the largest combined total by far. We can see individual data about the Winter Olympic Games, that Europe has hosted the most, then North America, then Asia, and that Australia and South America have never hosted the Winter Olympics. We can compare within a continent, so we can see that Europe has hosted more Summer Olympics than it has Winter Olympics, and that both North America and Asia have hosted an equal number of Summer and Winter Olympics between them, with North America hosting a larger number than Asia. So just remember that when you have one-way data, especially when you have a lot of it, you have a really big table of one-way data, that there are visual ways to represent that data, including bar graphs and pie charts. If it's hard from your original table to get a really quick understanding of what the data is telling you, you might want to create a visual representation in either a bar graph or a pie chart. Once you've made your chart, whether it's a bar graph or a pie chart, make sure to just double check your chart and ask yourself whether someone would be able to tell what the chart is representing if all they had was the chart and not the data. That's where things like legends are important. For example, in this chart, we needed to indicate that red represented Summer Olympics and yellow represented Winter Olympics. Or remember with the pie chart, we put the count on each section of the pie and included a legend as well. It's also really helpful to include a title for the chart. So for example, a helpful title for this chart might be Olympic Games host, and then maybe by continent. This way we know that we are graphing in our chart the host cities of each Olympic Games and that we're categorizing by continent, which is why we see then the continents listed across the bottom here, Europe, North America, etc. We have our axis labeled here so we can get a pretty accurate picture of the count for each of these bars, and we have a legend here to distinguish between summer and winter games. We've looked at how we can use bar graphs and pie charts to display one-way data, and in this video I want to talk about two other ways to display that kind of data, line graphs and ogives, and we're going to go ahead and start with line graphs. We've already used this example where we've created a bar chart out of data about the Summer Olympic Games. We counted up the number of times each continent has hosted the Summer Olympics and used that data to create a bar chart, and this is what it looked like. The reason I'm bringing up a bar graph is because a bar graph is really similar to a line graph, and we can turn one into the other and vice versa. So if we wanted to turn this bar graph into a line graph, all we need to do is plot a point at the top middle of each bar. So that would look like this. We just come to the top of each bar, right in the middle, and we sketch a point. So we know Europe has hosted the Summer Olympics 16 times, So right up here at 16, we plot a point. North America's hosted the Summer Olympics 6 times, so right here at 6, we plot a point, and so on. So we have a point at the top of each bar, and then all we have to do is connect those points with straight lines. So we connect one point to the next with a straight line, then this point to the next with a straight line, then this point to the next with a straight line, and so on until we've connected all the points. Then if we just remove the bars that are left over from our bar graph, this suddenly is a line graph. So this is what a line graph looks like, and as you can see, it's really the same as a bar graph, except that instead of displaying the data with bars, we display the data with points connected by lines. Now you might be wondering, if bar graphs and line graphs are so similar, when is it appropriate to use a bar graph, and when is it more appropriate to use a line graph? Well, line graphs are typically better when there's some kind of a connection between the data points. So for example, when you have change over time, if you want to graph data every hour in the course of a day or every month of the year, something like that. So moving through time and there's a connection between the points. Or if somehow these aren't really discrete categories and they're connected together, it feels like there should be a flow, then a line graph is a good choice. But if these categories here, the individuals that we graph along the bottom, are discrete and don't really have anything to do with each other necessarily, then a bar graph is usually the better choice. So in fact, this graph here of how often each continent has hosted the Summer Olympics is probably better as a bar graph rather than a line graph, so we'll go ahead and change that back. On the other hand, something like the monthly average high temperature in Scottsdale, Arizona, is going to be better as a line graph because it shows change over time. So as we move through a calendar year from January to February to March, etc., we're showing change over time of temperature, and it's more interesting for us to see the connection between these individual months. So instead of doing this as a bar graph, it makes a little more sense to do it as a line graph. But again, to be fair, we could still do this as a bar graph. It would still make sense that way as well. But let's go ahead and do this as a line graph. So the first thing we want to see is that our lowest temperature is down here in December at 68 degrees, and the highest temperature is here in July at 105 degrees. So if we want to sketch this as a line graph, we need to put in our horizontal lines here to indicate the intervals, and we need to cover at least from 68 degrees to 105. So we could go ahead and sketch in something like this, where we start at 0, which is well below 68, and we go up to 110 to make sure we encompass the highest value. Then we would want to go ahead and along the bottom here, write out the months January through December before we go in and plot points. So here we have January, February, March, April, May, June, July, etc., all the way through to December. Now to create the line graph, all we have to do is plot individual points. So January is 69 degrees. We could go ahead and come up here from January just above 66 and plot a point there. And if we do that for each month, we see here a plot of the average high temperature in each month. So we do in fact see 69 degrees for January, right up above 66. February is 73, so it's a little higher. July, 105, which is the hottest month, is all the way up here, just below 110. So we plot our points first, and then we go ahead and just connect each of those points with a straight line. So we don't draw a smooth curve, we draw a straight line in between each point, and that looks like this. We said before that it's nice to use a line graph when there's some kind of connection between the data points, between the individuals, as opposed to a bar graph when that connection isn't as strong. And here's one of the reasons why. When we have a line graph, it's really easy for us to see the slope or the rate of change between data points. So for example, I could look at this section of my line graph right here, which is the change in temperature between June and July. So as we move from June to July, because this line is slightly sloped upward, I can conclude that the temperature rises from June to July. So July is hotter than June. The temperature creeps up slightly. I can say slightly because the line doesn't have a very steep slope. It's pretty gradual. And in fact, if I look here at my table, I can see that June is about 103 degrees, July is 105. So it is a gradual slight increase from June to July. But if I contrast that with this section of the graph right here, which is the change between September and October, I can see that the line segment connecting September to October is not only negatively sloped, where this line segment was positively sloped, but it's also much steeper versus this slope is much more shallow. So what I can say is that from September to October, the temperature is dropping, it's getting colder, and it drops at a much more significant rate. The change in temperature from September to October is much greater than the change in temperature from June to July. And if I look back at my table, I can see that. From September to October, I drop 11 degrees. 100 minus 89 is 11, so I drop 11 degrees, whereas from June to July, I gained 2 degrees. So just plus 2 versus minus 11, this is a much greater drop, and I can see that reflected in my line graph because the slope of the line is steeper here and more shallow here. Now an ogive is really similar to a line graph. It looks just like a line graph, but you can think of it as an accumulated line graph. So for instance, let's say I have this table here. Let's say it shows your age from age 30 to age 39 and the investment that you make into a retirement account each year. So let's say at age 30, you invested $5,500. At age 31, you invested another $5,500. At age 32, another $5,500, and you keep doing that until you're 39. This is an interesting table in the sense that you can see your investment each year, but it would be even more interesting to see not only the investment you made each year, but your accumulated total. So if I modify this table and I add in your accumulated total, I see now that after the first year, you've invested $5,500 and your total is $5,500. In the second year at age 31, you invest an additional $5,500, so I see that investment that year. But I can also see that your accumulated total is now $5,500 plus $5,500 is $11,000. And I can see that each year you add $5,500, and I can see that the total increases until eventually, after 10 years, you have a $55,000 total. Now let me just say for a second that normally when you say investment, you're talking about putting in some kind of investment amount like the $5,500 and then getting some kind of an interest return on that investment. In this example, we're just talking about the invested amount. We're ignoring any interest that you would gain from that investment. So I just want to look at the amount that we invest and then the accumulation of that invested amount over time. This kind of data is perfect to graph in an ogive because an ogive allows you to show this accumulated total here. So let's see what that looks like. First of all, I know that I'm starting at 5,500. I'm going to end up at 55,000. So I would want to go ahead and plot my lines here and then plot my ages from age 31 to 39. And then go ahead and on the left-hand side here, say I'm starting at 0. And I know I'm going up to 55. So I'm going to need my axis to come up to maybe $60,000 so I can capture all of the data in my chart. Then instead of plotting the investment each year, because if I simply plotted 5,500 for each year, I would have a straight horizontal line somewhere around here, just straight across at the bottom of the graph, showing a $5,500 investment each year. That really wouldn't be very interesting. But if I plot the accumulated totals, then I would see actually the accumulation and my money growth over time. So I would say here that at age 30, I invested 5,500, so my total was 5,500. At age 31, I made an additional investment, and now my total is 11,000, so I plot the 11,000. At age 32, I made an additional investment, now my total is 16,500, so I plot that point 16,500 right above 15,000 here. So basically, I'm plotting the total every year, not just the investment. And when I connect these with straight lines, again, a straight line between every point, now I have an ogive because the ogive is showing the accumulated total over time. It shows me that by age 33, I have maybe about 20,000. It shows me that at age 39, I have something around $55,000 because I'm showing the accumulated total of the money that I'm saving. Notice here that for the line graph that we did for temperature, so we have up here the line graph, it wouldn't make sense at all to do this as an ogive because we would be adding temperatures together every month. So January would be 69 degrees, February would be 69 plus 73 is 142 degrees, March would be over 200 degrees, etc. And that doesn't make any sense. We would just have constant rising temperature. Temperature is not a good variable to graph as an ogive. It makes sense in a line graph where we see change over time. But savings over time is great in an ogive. We'll go ahead and say that this is our ogive. Savings over time is great in an ogive because it allows me to see my accumulated savings over time. And it also allows me to see the rate of my investment. So the reason that this is a perfect line is because my investment stays constant over the entire decade from age 30 to 39. I invest $5,500 each year, so my rate of investment is always the same. If my rate of investment changed and I invested a different amount each month, then the slopes of these lines would be different. We might have something instead that looks like this. I could have invested much more and then maybe a little bit less that year, and then invested a little bit more, and then not quite as much this year, but then a lot this year, and then a lot the next year, and then a little bit less. And so I would be seeing my accumulated savings, and I would also be able to see the rate of change of my savings. So in these years, I invested a lot and my savings grew more quickly. In these years, like here and here and here, I invested less, and so my savings didn't grow quite as fast. And then when we have this linear relationship, it tells us that our saving rate is constant. So just remember that bar graphs are best for representing data that isn't necessarily connected, more categorical data that doesn't need to be tied together in any way. A line graph is really, really great for representing change over time so that we can see how one variable moves up and down and the rate of change between each data point. An ogive is best when you want to show an accumulated total. Not only can you see rate of change between each data point, but you also get the bonus of seeing the accumulation over time. So you're kind of getting two pieces of information in one graph. And so an ogive really makes sense when you want to show both of those things at the same time. A great example of which is showing your savings over time so that you can see not only your year-to-year savings rate, but also the total amount of savings that you've accumulated. In this video, we're talking about two-way data and how it's different than one-way data. So let's just quickly review what we mean by one-way data, which we've already covered previously. So something like this would be a one-way data table where we have the individuals, which are the months in this particular case, down the left-hand side, and then the single variable for those individuals down the right-hand side where the variable is revenue. We can also describe individuals and variables as dependent and independent variables. So in this case, the month is the independent variable, and the revenue is the dependent variable because the revenue depends on the month. If I asked you how much revenue did we make, you would ask me in what month, because the revenue is dependent on the month. The amount of revenue that we have made depends on the month that we're talking about. So previously we had referred to the month as the individual and revenue as the variable, but we can also call the month the independent variable and the revenue the dependent variable. And we also already know how to graph data in a one-way table. So for example, if we made a bar graph for this data, it would look something like this. We can see that the smallest value that we have in the table is the revenue for the month of February, just under $15,000. And the largest revenue figure that we have is for the month of November at just over $48,000. So we'd want to set up our axis here from 0 up to $50,000 so that we can capture this $48,000. And then we would just graph the revenue for each month. So for January, we had about $28,000. So you see that comes up to a little over the $25,000 mark. Here's February at just under 15. So that comes up just over the $12,500 mark, and we plot those bars all the way to December. We've already done all that, and we know how to handle one-way data. So now, how is two-way data different than one-way data? Well, this here is actually a table that we're saying displays the revenue earned by an artist in each month of the year. But we're saying that this artist has been in business from 2014 through 2017. So he's been in business 2014, 15, 16, and 17, 4 years total. And in order to get the data in this table, what we actually did was we took his revenue from all 4 years in January. So January of 2014, January of 2015, 2016, and 2017, all 4 months of January, added that revenue all together to get one figure for January. And we did the same thing for February. We took all 4 Februaries, added them together, got a revenue total, and therefore we have a one-way data chart and we were able to plot that. But of course, if this is actually a real-life scenario, well, this is a great summary table to see maybe which month the artist does best in. So for example, we can see that November is clearly his best month, January is his second best month, etc. We really lose a lot of detail. We have no detail that shows the artist's revenue in 2014, 15, 16, or 17. It's all lumped together. So we can't tell, for instance, if the artist's business is declining, if he's making less money year after year after year, or if his business is doing well. Maybe he's made more money every year. We have no visibility into that because we don't have the breakdown here by years. It's just a one-way summary table. The way that we fix that is by creating a two-way table instead to show the detail by year. So here's what that might look like. If we created a two-way table for the artist's revenue and we still have the months down the left-hand side, but now instead of just showing a total figure for each month, we've broken it out by year. So we have detailed data for 2014, 2015, 2016, and 2017. And this is a two-way table, and this is the difference between one-way data and two-way data. With one-way data, we just have the individuals and then the variables here. And the dependent variable only depends on one thing. Again, going back to the how many questions do you have to ask idea, if I ask you, how much revenue did we make? You only need to ask me one question. For which month? If I then tell you July, you can tell me right away, oh, $17,990. All you need to know is the month. You only need to answer one question in order to figure out which value of the dependent variable you're interested in. But with two-way data, you need to answer 2 questions. So in the body of the chart here, we have revenue. And if I ask you, how much revenue did we make? You now have to ask me 2 questions, which is why it's called two-way data instead of one-way data. Not only do you have to ask me for which month, but you also have to ask me for which year, because you need to know that I'm actually interested in April of 2016 in order to give me a figure. You need to know the month and the year. You have to ask 2 questions, so it's two-way data. So the dependent variable of revenue in the body of the chart depends on 2 independent variables, both the month and the year. Two-way data tables get even more interesting when we show totals, if possible, by row and by column. So we can add in here, we can replace this two-way data table with one where we show the total by row here on the right side and the total by column here on the bottom. Here's what we're doing. If I take all of the revenue for 2014 and I add it up, I get a figure of $8,980. That tells me how much the artist made in the year 2014. Then I can look and see how much he made in 2015, 16, and 17. Now I actually have some detail because I can see that his business is growing. In fact, it's growing significantly. I can see that his revenue in 2014 was only about $9,000, but then in 2015 it increased to $31,000, then about $72,000, and then a little over $161,000. I had no insight or no visibility into that in the one-way table, but breaking the data apart into a two-way table allows me to see that growth year over year. In addition to that, on the right-hand side, I have totals by month. These represent the sum of each row, so 28,361 is the sum of January across all 4 years, which makes sense because these numbers match the data in my one-way table. Notice here January is also 28,361, like it is over here 28,361. So this gives me the total for all of January, 14,744 is for all of February, 19,407 is for all of March, etc. And this gives me insight into the best month for the artist historically. Again, I can see that November is by far his best month, whereas February and April are his worst months historically. And that's one of the reasons a two-way table is so helpful. I get visibility into both the year and the month because I can analyze the data and sum the data both ways. I can also see things like the historical best month ever. I can see that it was November of 2017 at just over $26,000. This is the largest figure in the body of the table, so I know that the artist made more in November of 2017 than he did in any other month. The least he ever made was $254, which was the very first month he was ever in business, January of 2014. And I could look and see the very best month for any particular year, or I could see the very worst month for any particular year. I also have data where now I could, for example, create a line graph of just his data for 2014, or just his data for 2016, or just his data for August year over year. So you can see how the two-way table becomes really powerful. Let's go ahead and do a side-by-side comparison bar graph to illustrate the data in the two-way table. So we want to start with our axes as we normally do, and then we're going to need values along the vertical axis that encompass the lowest possible value of 254 and the highest possible value of 26,000. So for example, we might do axes like this, starting at 0, so we can graph 254, and going all the way up to 30,000, so that we can graph 26,000. We could pick other increments, but these are just the ones that we picked. And then, of course, we want to put the months across the bottom to show all of the data in the table. Now, from here, we could go in and graph the data for 2014, and that might look something like this. Obviously, the largest value in 2014 is just under $2,400, so that's going to be about a third of the way up to $7,500. Everything else is going to be a little shorter. Then we could go in and graph the data for 2015, and this will start to get a little clearer because the values get bigger. So in 2015, our data would look like this. And now we can quickly tell that the artist did better in every single month of 2015 than he did in each month of 2014. So for example, January 2015 was better than January 2014, and February 2015 was better than February 2014, etc. So every single month he did better year over year. If we add in the data for 2016, we get a plot that looks like this, and then we add in the data for 2017, and now we see a full picture of the two-way data, or the two-way data table. This is a comparison bar graph, but we could have also done a comparison line graph. But no matter how you graph it, we can see in the same way that we analyze the data in the table, we can analyze the data visually in the bar graph. So for example, we can focus in on just January, and we can see that the artist made a very small amount of money, then a little bit more, and then maybe something around $10,000 or so, and then maybe something a little over $15,000 in 2014, 15, 16, and 17 respectively in January. We could analyze February individually or March individually, but we could also look across years. For example, if we take the light blue, which represents 2016, we can see that he got a strong start in January, pretty well in February and March, and then much slower in April, May, June, slowly building in July, August, September, and then as we've seen in the table, a really strong November before closing out the year in December. Or we could look at his 2017 data in the dark blue, and we could see that he had his best month ever, every month, in 2017. So we can get a lot of information from a comparison bar chart that we constructed from a two-way table. And as usual, especially when you have multiple data sets graphed in the same chart, it's helpful to include a legend. So we could include something like this that indicates by color which data set represents 2014, 2015, 2016, and 2017. So either one of these, the one-way data table and the two-way data table, both are acceptable and they certainly both have their benefits. For example, the one-way table is a really nice, simple view of revenue by month. We don't have all this detail that we have to deal with. It sort of simplifies things, makes it easy to see revenue by month. So if that's all we're interested in, a one-way table might be just fine. There are lots of instances where we don't need the detail of a two-way table. But as you can see, a two-way table can certainly provide a much higher level of detail and give us much more visibility and insight into the data itself. Venn diagrams are a great way of visualizing two-way data, or the data in two-way data tables. They're especially helpful when we have the kind of data that we can classify as both, neither, or one or the other. So if we have categories of items, where some items have one characteristic, other items have another characteristic, some have both characteristics, and some have neither characteristic, Venn diagrams are extremely useful. So let's look at an example. We're going to pretend for a second that we are baking Christmas cookies for our family. So we go ahead and bake a bunch of cookies, and it looks like we have, 4 cookies across and 4 cookies down. So we've baked 16 Christmas cookies. And we're not really too organized with our baking. So we decide that we're going to put frosting on some of them and sprinkles on some of them. And we kind of do this haphazardly. We're going to go ahead and say that we decided to frost these ones. So we dipped some of them in red frosting, of course, because it's Christmas. And so we did some of these randomly with frosting. Then we decide we want to add white sprinkles, and we're going to go ahead and put white sprinkles on these ones. So as you can see, we're kind of all over the place. We have some cookies that have neither frosting nor sprinkles. Then we have some cookies that have just red frosting. It's the sugar cookie, we dipped it in red frosting, but then we stopped there. Then we have some cookies that have just the white sprinkles, so we didn't dip them in frosting, but then we put sprinkles on them. And then some of the cookies we decided to both dip in red frosting and then cover in sprinkles. So on the one hand, we're a little bit disorganized. On the other hand, our cookies are looking pretty good. What we want to do is organize this data, organize our cookies into a two-way table, of course. So here's what that would look like. We would set up a two-way table where we say down one side, either frosting or no frosting. Did we apply frosting or did we not apply frosting? And then across the top, sprinkles or no sprinkles. So we want to say the ones we put sprinkles on, the ones we didn't put sprinkles on. This then gives us all combinations. Because if we look at this box here, this box represents all of the cookies that have frosting and sprinkles. And so we can see that we got here 1, 2, 3, 4 cookies with frosting and sprinkles, so we put that in there. Then we have here in the first column, second row, all of the cookies that have no frosting but did get sprinkles. So there's no red frosting, but they did get the white sprinkles, and we can see that we have here 1, 2, 3 of those cookies that have no frosting but do have white sprinkles. So we put the 3 there. Then we look at the second column, first row, because we're going through each cell in our body here. And we can see that this cell represents frosting but no sprinkles. So we have the red frosting but no white sprinkles. And that would be 1, 2, 3, 4, 5 of our cookies that have frosting and no sprinkles. And then finally, the last cell, which indicates cookies that have no frosting and no sprinkles. Those are going to be our plain sugar cookies that got nothing. So this cookie got nothing. 1, 2, 3, 4 cookies that didn't get frosting or sprinkles, so we put a 4 there. Now we could have just left our table that way, but we can also include totals across the bottom and down the right-hand side. So we can see that if we add up the column, we know that there are 7 cookies with sprinkles, and we can see that that's true. We have 1, 2, 3, 4, 5, 6, 7 with sprinkles, 9 cookies with no sprinkles when we add up the second column. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9. And then 9 cookies with frosting when we add across the top row. So 4 plus 5 is 9. 9 cookies that have frosting. So 9 cookies that have red frosting. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then adding across the second row, 7 cookies that have no frosting. So 7 cookies without the red frosting. 1, 2, 3, 4, 5, 6, 7. And we do in fact get 7. And then the total of both the column and the row, which should be the same both ways, 16. And we know that we do have 16 cookies because we have 4 cookies across by 4 cookies down is 16 total cookies. So this is our two-way table representing our sugar cookies. Now we want to see how to translate a two-way table into a Venn diagram. So here's how you build a Venn diagram. The first thing you want to do is draw a box. And I made mine the color of sugar cookies because this box in a Venn diagram, it's always going to represent your whole universe of data, all of the data that you have. So here we have all our data in a two-way table or all of our data in sugar cookies. We want to make sure we get all of our data represented somewhere inside of this box. So this is our entire sugar cookie universe. Now in our two-way table here, we put frosting or no frosting and sprinkles or no sprinkles, which means that in a Venn diagram, we want to draw a circle for each of those decisions. So we want to draw one circle for frosting, one circle for sprinkles. So we'll go ahead and draw a frosting circle in red to match our frosting. And we don't have to, but we can go ahead and label that the frosting circle. And then we want to go ahead and draw a circle for sprinkles. And since our sprinkles are white, we'll draw a white circle and we'll go ahead and call this our sprinkles circle. Now here's what a Venn diagram does. It gives us 4 pieces of area. The first piece of area is inside both circles. It's this piece in the center right here. And this piece in the center is both inside the sprinkles circle and it's inside the frosting circle. So it's inside both. So in our example, it represents all the cookies that have frosting and sprinkles because it's inside frosting and inside sprinkles. So how many cookies do we have with frosting and sprinkles? Well, frosting and sprinkles is this cell right here, 4 cookies. So we'll go ahead and put 4 in that piece of area. Then we have this piece of area, which is inside the frosting circle, and this piece of area, which is inside the sprinkles circle. Those are the next 2. So this one right here, it's inside the frosting circle, but it's outside of the sprinkles circle. So what that means is that this piece of area right here represents the cookies that do have frosting, because we're inside the frosting circle, but do not have sprinkles, because we're outside the sprinkles circle. So how many cookies have frosting, but do not have sprinkles? Well, frosting would be the first row. No sprinkles would be the second column. So that's 5 cookies. So we can go ahead and put a 5 here. Now this piece of area, it's the exact opposite scenario. In this piece of area, we're inside the sprinkles circle. So this is going to represent cookies that do have sprinkles, but we're outside the frosting circle. This is the boundary here of the frosting circle. We're outside of it. So this is going to be sprinkles, but no frosting. We're not inside the frosting circle. So how many cookies have sprinkles but no frosting? Well, here's sprinkles in the first column. No frosting is in the second row. That's 3 cookies. So we put a 3 right there. And then the last piece of area in our Venn diagram is outside of both circles, just the area here around the outside that's still inside of our rectangle, which remember is the universe of all of our cookies. So how many of our cookies do we have that do not have frosting, since we're not inside the frosting circle, and do not have sprinkles, since we're also outside the sprinkle circle? So how many cookies with no frosting and no sprinkles? In other words, neither. Well, no frosting is the second row here. No sprinkles is the second column. We can see right here where they intersect. There are 4 cookies with no frosting and no sprinkles. So we go ahead and write a 4 outside of both circles. And we could have written that up here or here in any of the corners, anywhere outside both circles. But this 4 represents neither. So again, in the middle here, we have both. On the outside, we have neither. And then in these areas, we have here frosting but no sprinkles. And here we have sprinkles but no frosting. Notice too that the numbers we filled in our Venn diagram were the ones from the body of our two-way table. And that's always going to be the case when you have a two-way table and you want to express that or visualize it in a Venn diagram. You want to take all of the values that are in the body in the middle of your table and make sure that those get placed into the Venn diagram. And in order to build the Venn diagram, you can always follow the same steps we did, where you draw a rectangle, you draw 2 circles that are overlapping, so you get this overlapping area, and then you just fill in both this one but not the other one, this one but not the other one, and then neither on the outside. Notice too that when we're reading this Venn diagram, we can see the totals that were in our two-way table. So for example, if we want to know from the Venn diagram the total number of cookies that have frosting, the total number of cookies with frosting is 9. From the Venn diagram, we can see that by looking at all of the numbers that fall anywhere inside the frosting circle. So if I look at this entire frosting circle, the numbers I have inside of it are 5 and 4. They add up to 9, so I know that there are 9 total cookies with frosting. If I want to see the total number of cookies that have sprinkles, that's 7. Well, I just look at all of the numbers that fall inside of my sprinkles circle. That's 4 and 3. The 4 and the 3 are both somewhere inside of my sprinkles circle. So 4 plus 3 is 7, and I can say that there are 7 total cookies with sprinkles. To get my total for no frosting of 7, I just want to add up everything that's outside of the frosting circle. So I know that everything inside of the frosting circle is 5 and 4. These have frosting on them. I ignore those. All of the numbers in my Venn diagram that are outside of the frosting circle are the 3 here and the 4 here. So there are 7 cookies outside of the frosting circle, which means there are 7 cookies with no frosting, which matches our table. And then same thing here for cookies with no sprinkles. I know that 4 and 3 are both inside my sprinkles circle. They have sprinkles on them. I ignore them. But all of the numbers that are completely outside of my sprinkles circle are the 5 here and the 4 here. 5 plus 4 is 9. There are 9 total cookies that have no sprinkles, which is what I see in the two-way table. And then I can even get my total number of cookies, 16 here, from my Venn diagram simply by adding up all of the numbers together. So I have 5, 4, 3, and 4. Those are all of the cookies in my Venn diagram. So 5 plus 4 is 9, plus 3 is 12, plus 4 is 16. So I can see the total number of cookies that I have. So just remember that Venn diagrams are especially great for expressing data when you have 2 questions and you could kind of answer yes or no to both of them. So here we have the question of sprinkles. And we answered either yes, sprinkles, or no sprinkles. And then here we have the question of frosting. And we either answered yes, frosting, or no frosting. So when you have data that you can sort of think of that way, there's these 2 kinds of categories that your data items can fall into. You can make your two-way table this way with frosting or no frosting and sprinkles or no sprinkles. And then you're categorizing each item that you have into one of those boxes. You could look at every item and sort of tally it up. You could say this one is frosting but no sprinkles, so it goes in the frosting and no sprinkles, and you could sort of put a tally there. This one is both frosting and sprinkles, so you could get frosting and sprinkles, put a tally there. And you could just keep going, tallying up your items until you get totals here, and you can see that you have 4 cookies here with both frosting and sprinkles, or 5 cookies with frosting but no sprinkles. Once you get that body of your two-way data table built, then you can create these totals if you want to, and you can express all of the data from your two-way data table in a Venn diagram like this one. We've talked about one-way data tables and two-way data tables, but in this video, we're going to talk about something called relative frequency tables. And a relative frequency table can be made from both a one-way table and a two-way table, but we're going to be focusing on two-way tables. So we're going to be looking at how to turn a two-way data table into a relative frequency table. Let's say, for example, we start with this table here, which is a table that organizes all the surfboards in Ricky's surf shop. So this is a table of surfboards, and we've got the table broken up by color of surfboard. Some of our surfboards are blue, some are white, and then by whether the surfboard is a longboard or a shortboard. So we can tell from the table, for example, that we have 20 blue longboards, or that we have 3 white shortboards. So we've got some information, and this is a great two-way table, but what we really want to know is the percentage of longboards and shortboards given that we've got a blue surfboard, or the percentage of longboards and shortboards given that we have a white surfboard. We're also interested in the other way. We want to know, given that we have a longboard, what percentage of our longboards are blue and white, and what percentage of our shortboards are blue and white. And that's where relative frequency tables come in. So let's just say here that we are going to focus on these blue surfboards right here. So we're just going to look at this column. We're going to ignore the white column for a second. What we want to notice is that we have 25 total blue surfboards. If we add 20 plus 5, we get a total of 25 blue surfboards. The question we want to answer is, of our 25 total blue surfboards, what percentage of those are longboards and what percentage of those are shortboards? So the way that we figure out a percentage is just by dividing the number of longboards by the total number of blue surfboards, or the number of shortboards by the total number of blue surfboards. So if we take 20 divided by 25, what we get is 0.8, or 80%. If we take 5, the number of shortboards, divided by 25, so 5 divided by 25, we get 0.2, or 20%. What this tells us is that 80% of all the blue surfboards are longboards, and 20% of all the blue surfboards are shortboards. Now we could do the same calculation for the white surfboards, so this time ignoring the blue column and just looking at the white column here. If we add the total together, we have 15 longboards, 3 shortboards that are in the color white. 15 plus 3 is 18. So we have 18 total white surfboards. So of our 18 white surfboards, what percentage of those are longboards? Well, that would be 15 divided by 18. So if we say 15 divided by 18, we get approximately 0.83, or approximately 83%. If we want to know the percentage of our white surfboards that are shortboards, we just take 3 divided by 18, so 3 divided by 18, and that's approximately equal to 0.17, or about 17%. What we want to do then is represent these new calculations in a relative frequency table. So here's what that would look like. We would build a new table. Notice it's the same as the original table with longboard, shortboard, and blue and white, except that we replace the count of each category with now a decimal number. So notice here we have the 0.8 and the 0.2, which come from our 0.8 and 0.2 here. And then we have 0.83 and 0.17, which come from our 0.83 and 0.17. So we entered our new calculations into the table. Notice also, and this is really important, that we have this column total row added to the bottom. The fact that we have the totals at the bottom and that we said column total tells us that we found the percentage of each category by column. So we looked in the column and we found the percentage of longboards for this whole column. We found the percentage of shortboards for this whole column. And by the way, it would be totally appropriate in a relative frequency table to to put either 0.8 or 0.80 or 80%. We just as easily could have put here 80%, 20% here, and then 83% and 17%. So you can either enter these as a percentage or as a decimal. Both are totally acceptable. If you have decimals, you want to have at the bottom here 1.0 or 1.00. If you have percentages, you want to match that and say 100% at the bottom, and then 100% here. So either way, decimals or percentages, both are okay. You can pick whichever one you'd like. But the column total at the bottom, and the fact that we say column here, means that we looked at each column individually. And that makes sense because 0.8 and 0.2 add up to 1, and 0.83 and 0.17 add up to 1. So when we sum the column, we get a total of 1, and that's always what we want, 1 or 100%. Notice that if we try to sum across the rows now, we get 0.8 plus 0.83, or 1.63, also known as 163%. And across the shortboard row, we get 0.2 plus 0.17 is 0.37, also known as 37%. And this just doesn't make any sense at all. It doesn't make sense that longboards are 163% of our surfboard population. And the reason these don't make sense is because we didn't look at the rows, we looked at the columns. So because we looked at the columns, that means each column will sum to 1 or 100%. Because we looked at the columns, this is actually called a column relative frequency. Basically, this table just shows us the percentage of type of surfboard based on color. And we say based on color because we based our calculations on the column, and the column is what's showing color. But we could have just as easily done these calculations by row instead of by column. If we want to look at the calculations by row, instead of looking at the whole blue column, we now look at the entire row here for longboards instead. So we'll go through the same process, it'll just kind of be the opposite way. This time we look at the whole row and we say, what are the total number of longboards that we have? So 20 plus 15 is a total of 35. Now of our 35 longboards, what percentage are blue? Well, we would just take 20 divided by 35. So we'll do that up here and we'll say 20 divided by 35 is approximately equal to 0.57, or about 57%. If I want to find out the percentage of longboards that are white, I would take 15 divided by the total of longboards 35, so 15 divided by 35 is approximately equal to 0.43, or 43%. And then I want to do the same thing for the shortboard row. So now I ignore the longboard row, I look just at shortboards, and I want to say this time, which percentage of my shortboards are blue, which percentage are white? Well, the total here, 5 plus 3 is 8. For the percentage that are blue, I'll take 5 divided by 8. So 5 divided by 8 is equal to approximately 0.63, or about 63%. If I want to find the percentage of shortboards that are white, I take 3 divided by 8, which is approximately 0.37, or about 37%. Then if I want to put those in a table, here's what that looks like. This time, instead of a column relative frequency, I will call it a row relative frequency. Notice that I translated the 0.57 and 0.43 here across the row as 0.57 and 0.43, and the 0.63 and 0.37 across the row as 0.63 and 0.37. And just like with the column relative frequency, it's equally acceptable to put here 57%, 43%, and then 63% and 37%. And then if I do that, I just want to make sure that in my row total here, I have 100% and 100%. So I could express these as percentages or as decimals like I have them. Notice how in the column relative frequency table we had across the bottom, column total and then the total decimal 1.00 or 100%. In a row relative frequency table, I have instead the row total. I say specifically it's a row total, and my decimals add up to 1.00. 0.57 plus 0.43 is 1. 0.63 plus 0.37 is 1. So it makes sense to sum up the totals because I'm saying that the row total is 100% of the longboards. 57% of those are blue, 43% of those longboards are white. So either I calculate across by row, where I find the total for the entire row, and then take the individual value here, 20 or 15, and divide that by 35 to get a percentage across the row, and then I put a row total of 1 or 100% and call it a row relative frequency table. Or I find the total down the column. I sum 20 and 5 to get 25 as the total for the column. Find the percentage of 20 in comparison to the column and 5 in comparison to the whole column. And then I put those numbers into my table here and find the column total as 1 or 100% and call that a column relative frequency table. A joint distribution is a little similar to a relative frequency table in the sense that it's a table of percentages. As an example, this is a joint distribution. The reason we call this kind of table a joint distribution is because it's comparing two different distributions. So we have a distribution for hours spent exercising and a distribution for weight loss, and we are sort of cross-referencing or comparing those two distributions. So we'll come back to this table in a second, but let's look at just hours exercising and just weight lost. This particular joint distribution is a data table for a study that we've done with 100 participants, where the participants did some amount of exercise on average each week, and then over the course of the study, lost a certain amount of weight. So let's look first at just weight lost. So ignoring this table up here for a second, and in fact, let's hide it. Let's look at just weight lost. So we could have, from our study, just looked at the distribution of the weight lost by our participants. So we could have seen how many participants lost between 0 and 2 pounds, between 2 and 4 pounds, between 4 and 6 pounds, and 6 or more pounds. And let's recognize that this kind of looks like a relative frequency table, specifically a row relative frequency, because we have percentages in the body here, which across the row sum to 100%. Because we have 100 participants in our study, we know that this is in fact 18 actual participants who lost between 0 and 2 pounds, 31 actual participants who lost between 2 and 4 pounds, etc. So we could have just gathered data from our study and set up a distribution for weight lost. That would have been somewhat interesting, but it wouldn't have been the full picture. Similarly, we could have looked at a distribution just for hours spent exercising. So again, this is the same data, the same 100 participants in the same study, and we could have just looked at the distribution of the hours spent exercising. So we could see that of our 100 participants, 9%, or 9 of them, spent on average 0 to 3 hours exercising each week. 19% of the participants spent between 3 and 6 hours exercising each week on average, 32% between 6 and 9 hours, etc. And realize that this is a column relative frequency because we have these percentages here in the body of the table, and then at the bottom we see that they sum to 100%. The column total is 100%, so this is a column relative frequency. And while it's great that we have information here about hours spent exercising, we still don't get the full detail of all of the data that we collected in the study. Only when we look at the joint distribution, where we actually compare hours spent exercising to weight lost, do we really see the full detail of the data that we gathered. And this is actually a much more valuable table, and it should make sense to us why it is. It's more valuable because it lets us see a correlation between hours spent exercising and weight lost. Once we have the joint distribution, we can answer questions like, did participants lose more weight if they spent more time exercising? Or did participants lose less weight if they spent less time exercising? When we just looked at the distribution of weight lost, we had this total row here at the bottom, and we saw that most of our participants lost between 2 and 4 pounds or between 4 and 6 pounds. These were the largest groups. And when we just looked at hours spent exercising, we had the total column over here on the right, and we can see that the bulk of our data fell in this range here. Most of our participants spent between 6 and 9 hours exercising or 9 and 12 hours exercising. So on average, 6 to 12 hours per week is where the bulk of our participants fell. And we can see that in the detail of the data. So the largest group of participants spent between 6 and 9 hours exercising and lost between 2 and 4 pounds. That was the most common occurrence because this 17% value is larger than any other percentage in our table. The next largest group was this group, which spent between 9 and 12 hours exercising and lost between 4 and 6 pounds. So they exercised a little bit more, and they lost a little bit more weight than this 6 to 9 hour group who lost 2 to 4 pounds. We can see how helpful it is to be able to compare the amount of exercise against weight loss. And again, that's why it's called a joint distribution, because we are joining together two distributions. We're comparing the distribution of weight lost against the distribution of hours spent exercising. Now, there's a couple other things that we can get from this table, which are marginal and conditional distributions. So a marginal distribution, just think of as either the total row or the total column. So these totals here. The marginal distribution is in the margin. It's on the edge. That's a way to remember it. It's in the margin or on the edge. And so it's the total areas here. So if we want to look at marginal distribution for weight lost, that would just be this whole area right here. This sums up each column. So we can see that 18% of our participants lost between 0 and 2 pounds, 31% between 2 and 4 pounds, etc. So this gives us the full distribution for weight lost. It's the marginal distribution for weight lost. And of course, the marginal distribution for weight loss basically ignores the distribution for hours spent exercising. It eliminates all of that detail. In the same way, the marginal distribution for hours spent exercising is this over here. It's the total column, because this 9%, 19%, 32%, this area here gives us the distribution for hours spent exercising by totaling up each row. So we can say 9% of the participants spent between 0 and 3 hours exercising, 19% between 3 and 6 hours exercising, and on down the column. This distribution completely ignores the breakup by weight lost. It only gives us the totals for hours spent exercising. So those are our marginal distributions. And that's what we had before when we looked specifically at those total tables. This total table was the marginal distribution for weight lost. And notice that it doesn't give us any information at all about hours spent exercising. This table was the marginal distribution for hours spent exercising. And notice that it doesn't give us any information about the amount of weight lost by the participants. So those are our marginal distributions. The other thing that we can get from our table is what's called a conditional distribution. And in the same way that the marginal distributions were these total row and column, the conditional distributions are going to come from the data in the interior or in the body of the table. For example, this here would be a conditional distribution. It's called a conditional distribution because it's a distribution that is conditioned upon something or that depends on a particular condition. So what I've highlighted here is a conditional distribution of weight lost for the participants who spent between 6 and 9 hours exercising. So this distribution is specifically for one exact condition. This distribution is conditional upon 6 to 9 hours spent exercising. So in the same way that this is the conditional distribution for weight loss for 6 to 9 hours exercising, this is the conditional distribution for hours spent exercising based on 4 to 6 pounds of weight loss. So this column here is the distribution that shows us, assuming that we are looking at the participants who lost between 4 and 6 pounds, how much time did they spend exercising? So we're really just zooming in and examining in detail that group in our study who lost between 4 and 6 pounds, and then examining the different hours that they spent exercising. In the same way that here, we zoomed in on the group that spent between 6 and 9 hours exercising, just looked at those folks, and then looked at the weight lost for that specific group only. So this is the conditional distribution for exercise based on 4 to 6 pounds of weight loss. So just remember that we call this kind of a table a joint distribution because we are joining together two distributions and comparing them against each other. Remember that marginal distributions come from the totals, either the total row or the total column. They're called marginal distributions because it's the area in the margin or on the edge, and it just shows us the distribution for one of the variables only. So if we look at the marginal distribution across the row, we only get information about weight lost, which we see in this table. If we look at the marginal distribution down the column on the right-hand side, we only get the totals for hours spent exercising. We lose all the detail about weight loss. Conditional distributions come from either rows or columns in the interior of the table, and they're called conditional distributions because they are based on a specific condition. This is the distribution for weight loss based on the specific condition that we're looking at, just those folks who spent between 6 and 9 hours exercising. This is the conditional distribution for hours spent exercising based on the specific condition that we're just looking at those folks who lost between 4 and 6 pounds. In this video, I just want to talk really briefly about frequency tables and dot plots. So a frequency table is something that looks like this, and it should look really similar to a one-way table. We could think of this on the left here as the individuals, and then this count here on the right as the variable. It's called a frequency table specifically because it tells us the frequency with which each individual occurs, and that's not always the case with just a simple one-way table. So in this frequency table, I just looked in a parking lot. I made categories for each type of car, so a compact car, a sedan, an SUV, a van, a truck, or another kind of car. And then I counted how many times each of those occurred, and I recorded that in the table. So it's a frequency table because I can see how frequently compact car occurs in my data. I can see how frequently sedan occurs in my data. So it's a frequency table about the number of cars in the parking lot. Whenever you have a frequency table, you could of course display it as a bar graph or as a pie chart. Both of those would be good options, but we can also display it as a dot plot, and we'll look at dot plots more later on in the course, so I want to cover that here. So when we make a dot plot from a frequency table, what we want to do is first draw a horizontal line, and then below that we want to indicate each individual here in our frequency table, so compact, sedan, SUV, etc. So we show those beneath the line. And then we just sketch in a dot for each occurrence in our frequency table. So because there are 7 compact cars in my parking lot, I want to put 7 dots here above compact. So I could do that. That would be 1, 2, 3, 4, 5, 6, 7. So 7 dots above compact indicates that the frequency of compact in my data is 7. I have 4 sedans in the parking lot, so I just want to plot in 4 data points there. I have 12 SUVs, so I sketch in 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 SUVs, 9 vans, so that should be, 3 less than 12 here, so 9 vans, and then 1, 2, 3 trucks, and 1 in the other category. Keep in mind that dot plots are, of course, really similar to bar graphs in the sense that without even counting the dots exactly, we get a really quick visual picture of the most frequently occurring category in our data. So without even counting these dots, we can easily and immediately say that there are more SUVs in the parking lot than any other type of car. We can say that there are fewer trucks or other cars than any of the other categories. We could maybe say that there are approximately a roughly equal number of compact cars and vans because those bars are roughly the same height, or that there are an approximately equal number of sedans and trucks. And we can clearly say things like there are many more SUVs than sedans, or there are fewer trucks than vans. So we can make all of those really quick judgments just by looking at the visual representation of this data in a dot plot. And then, of course, if we want an exact number for any one of these categories, we can actually count the dots themselves. So if we wanted to know how many compact cars there are, and we don't have the table at all, we just have to count the number of dots, 1, 2, 3, 4, 5, 6, 7, and we know that there are 7 compact cars. In this video, I want to talk about 2 more kinds of charts or graphs, histograms and stem and leaf plots, and we're going to start with histograms. So histograms look exactly like a bar graph, except that in a histogram, we're grouping the data into buckets. One example of when a histogram can be useful is when you have too many data points to graph in a simple bar graph. So let's say, for example, that we want to create a bar graph of population age in San Francisco. And let's say there are roughly between 800 and 900,000 residents of San Francisco. If we want to put all of their ages into a bar graph, we would have to graph separately all of the residents of San Francisco who are less than 1 year old, then all of the 1-year-olds, all of the 2-year-olds, all of the 3-year-olds, etc., all the way up to the oldest resident, who's probably somewhere between 100 and 110, I would guess. If that's the case, we're going to have more than 100 bars in our bar graph, and it might be a little overwhelming. And so a histogram is a great substitute for that. What we can do is sketch our axes exactly like we would in a normal bar graph, and then we label here both the horizontal and the vertical axis. So what we've done here is group together all of the ages between 0 and 9 years old. So I have 0 plus here, but I really mean 0 to 9 years old. 10 plus really represents 10 years old up to 19 years old. 20 plus represents all the 20 to 29-year-olds, etc. As you can see, this is grouping all of the ages together by decade. So instead of showing a bar for every single age year, we're showing a bar for every single age decade. And that's going to consolidate our data significantly and simplify it. One of the really important things to know about a histogram is that your buckets or your categories, the things that you group together, they always have to be the same size. So each of these buckets has to represent the same interval of ages. So I couldn't have one bucket that was 0 to 20-year-olds, a 20-year span approximately, and then another bucket that represented 20 to 30-year-olds, because my first bucket would be an age span of 20 years. The second bucket would be an age span of 10 years. My buckets would be different sizes, and in a histogram, they always have to be the same size. So I've grouped all of these ages by decade, so every interval, every bucket is exactly 10 years. So then if I took my population and I graphed it, it might look something like this. So I can see that there are more 40 to 49-year-olds living in San Francisco than any other age group. The second largest age group is 30 to 39-year-olds, and you can see here the smallest age groups are 0 to 9-year-olds, 90 to 99-year-olds, and people who are older than 100 years old. Keep in mind that because in a histogram, we're always talking about consolidating buckets here, you really need to have quantitative data or data with numbers in order to create a histogram. If you have qualitative, categorical data that is non-numeric, it's not numbers, then it's much more difficult or impossible to come up with precise bucket sizes that are all the same. But when you have quantitative data like this, where we have ages, you can easily say 0 to 9 years old is the same size interval as 10 to 19 years old, which is the same size interval as 20 to 29 years old, etc., on up to 100 plus. And the spread of the data that we have here between our smallest bucket and our largest bucket, this is called the distribution of the histogram, which makes sense because it shows us how our data is distributed across all of these buckets that we've created. The other kind of chart I want to talk about is a stem and leaf plot, which is also sometimes called a stem plot. And like all of the other graphs and charts that we've talked about, it's just another way to organize or visualize data. So let's say, for example, that I have a set of golf scores. So golf scores are usually in the 60s or 70s for professional golfers. So let's say that I have data that looks like this, maybe a score of 66, 2 scores of 67, 4 scores of 68. So these are separate golfers in the tournament and their scores for one round of golf. I have 4 people who scored 69, and then 2 people who scored 70, 2 people who scored 71, a 72, a 73, and a 75. What we want to do is create a stem plot that organizes this data. So let me show you what that would look like, and then we'll go through it. So here is a stem plot of all of our golf scores. All we've done here is notice that all of our golf scores fall in either the 60s or the 70s. So these scores here were all in the 60s, and these scores here were all in the 70s. Everybody fell somewhere in the 60s or in the 70s, which means that the first digit of each score is either a 6 or a 7. So the first digit of 66 is a 6, the first digit of 67 is a 6, the first digit of 68 is a 6, you get the idea. So we either have the first digit as a 6, or for all the scores in the 70s, of course, the first digit as a 7. So that means that we have 2 stems, a 6 or a 7. So those first digits, that's what we call the stem. And we put our stems, as many of them as we have, here as a 6, and then here as a 7. Then we take the second digit of each score, and we plot that on the other side of the line here. So notice that we have the 6 and 7, and then we draw a line in between those, like this, and then another line over the top, which kind of looks like a header here. We put the 6 and the 7, the stems, on the left, and then all of the leaves, which is what they're called, the second digits are the leaves, we put over here on the right-hand side. So for all of the 60s, where the stem was a 6, now we look at the second digit. And we have here for the second digit a 6, a 7, another 7, and you see those starting to come out in our leaves here, a 6, a 7, a 7. Then we have 4 8s, 1, 2, 3, 4. So we have 4 8s in our stem plot, 1, 2, 3, 4, and then 4 9s, 1, 2, 3, 4 9s, which go in here as the 4 9s. And then for the 70s, we have 0, 0, 1, 1, which you see here as 0, 0, 1, 1, and then 2, 3, and 5, which you see here at the end as 2, 3, and 5. So a couple things we want to say here. Because we've got 2-digit numbers, we use the first digit as the stem, and that goes here on the left-hand side. We use the second digit as the leaf, and those go on the right-hand side. We should be able to take every pair and match it up together to create a score. So for example, if we take this 6 here and put it together with this 6, we put those together to create a score of 66. Or we take the 6 and then we take this 9, and that becomes a score of 69. Or we could take 7 and 2, and that becomes a score of 72 to get back to our original data set. So each of these together, the stem plus the leaf, represents an individual data point in our set. Now, usually to go along with a stem and leaf plot, we include a key or a legend, and it might look something like this. So we could say 6 and 6, and then we would say that equals 66. So what the legend here tells you is that when you have a stem of 6 and a leaf of 6, that means a value of 66. And the reason that we include a legend is because we can use the stem to mean something other than just the first digit. So, for example, if our data instead of 66, 67, 67, etc., was something like 606, 607, 607, 608, we kept going all the way to 705, we could still plot that in this same exact stem and leaf plot that we have, except that the 6 would represent the first 60 here, and the 7 would represent 70. And in that case, our legend would be 6, 6 is equal to 606. In other words, this is just the difference between the stem here representing 60, 10 times 6, and this stem representing 600, or 100 times 6. So we always want to include a key just to clarify exactly what we mean here in our stem and leaf plot. And there are just a few other tricky things about stem and leaf plots that we want to mention briefly. The first is that the leaf is always only one digit. You never put more than one digit into a single leaf. So, for example, if we added a score to our data set here of golfers, we had one really terrible golfer who scored a score of 103, we would not put in a stem of 1 and a leaf of 0.3, because we always only take one digit for the leaf. So we can only take the 3 for the leaf, which means 10 has to be the stem. So if we were going to add that into our stem and leaf plot, it would look like this, where we put the 10 in as the stem, and we just show the leaf as a 3, and this represents a score of 103. So if you run into a problem like this one, then you want to remember to only take one digit for the leaf, put the rest of the digits out here for the stem. And then the last question that comes up a lot is what you do when you just have a single digit number. So not that this would be possible with a golf score, but if we added to our data set the values 5, 7, and 9, these are all single digit numbers. So what do we do? What do we make the stem and what do we make the leaf? Well, you always take the single digit for the leaf. You'll always take a leaf before you have a stem. So because we need a single digit for the leaf, you'll make 5 a leaf, 7 a leaf, and 9 a leaf. So then what do you put for the stem? Well, you have two options. You can either leave it blank. So in this case, we put the 5, 7, and 9 here as leaves, and we just leave this stem area blank. Or alternately, it's acceptable to put a 0 in for the stem. So the same 5, 7, 9 as the leaves, and put a 0 in for the stem. You'll notice that in all of our stem and leaf plots, we listed our stems from smallest to largest. So we started with smallest at the top and went to largest at the bottom. So you want to make sure to do that. Here we had 6, 7, and 10, and we wrote them in that order. 6, then 7, then 10. Or here we had 0, then 6, then 7, then 10. So you want to rank those in order from smallest at the top to largest at the bottom. And same thing with our leaves. You always want the smallest value on the left. So here we started with 6 and we worked our way all the way up to 9. The smallest value is on the left, all the way up to the largest value on the right. Same thing with the leaves for 7. We started at 0, we went up to 5 on the right. So you want to make sure that you put your stems in order and you put your leaves in order. And those are two more ways to represent data visually: the histogram, which is just the version of the bar chart where we collapse our data into same size buckets or intervals, and the stem and leaf plot, where we take the first digit of every data point to make it the stem, and the last digit of every data point to make it the leaf. We've talked a lot about how to visualize or organize data in charts and graphs and tables, but now we want to start talking about some of the things we can do mathematically to better understand our data. And the first thing we need to talk about is what we call measures of central tendency, which are different ways that we've come up with to kind of describe the middle of the data. You might think there's really only one way to describe the middle, but in fact we've come up with several, because sometimes, depending on our data set, there's a better way to describe the middle than maybe another way that we would have used in a different situation. So the first one that you hear about all the time is the mean. And a lot of times we say average, but technically when we're talking about average, we're actually talking about the mean or arithmetic mean. And if we have a data set, first of all, let's say here, mean. If we have a data set something like 2, 4, 7, 7. We'll just pick a really simple data set. The mean is what we get when we add up all the data points and then divide by the number of data points that we have. We usually denote the mean with the Greek symbol mu, and like I said, the way we calculate it is by taking the sum of all data points and dividing that by the total number of data points. So in the case of our data set here, we would add up all of the data points to get the numerator. So we would say 2 plus 4 plus 7 plus 7, and then we would divide that by the number of data points we have. We have 1, 2, 3, 4 data points, so we would divide that by 4. And the result there is 2 plus 4 is 6, plus 7 is 13, plus 7 is 20. So we would end up with 20 over 4, or 5. So the mean of this data set is 5. Now the fancier way to write this formula is like so. We use summation notation, the sigma symbol, and we say I equals 1 to n of x sub I, and we divide that by n. Now this looks really fancy, but basically all we're saying is we're pretending that x is a data point in our series. When we say I equals 1 down here at the bottom, what we're saying is start with the first term. If we had I equals 2, it would mean start with the second term. So if x just represents a generic term in our data set, or a generic data point, x sub 1 is the first point in the data set. X sub 2 is the second point, x sub 3 is the third point, and on until the end of the data set. So we're saying start with the first term when we say I equals 1. And then the summation notation, the sigma symbol, means add up all the data points. Start with the first data point and keep adding and adding and adding until you get to the nth data point, which is the last data point. So this numerator here just means add up all the points, find the sum of all the data points, which is what we already had here in plain English. And then it says divide that by the total number of data points, n. So this is the technical way to write the formula for mean. This is just the intuitive way, but no matter how you remember it, you always just do the same thing. You add up all the data points in the numerator, you divide by the total number of data points you have, and then you simplify that fraction as much as you can, and that is your mean. One way to intuitively understand the mean is as a balancing point of the data. And what we mean is that the distance of all of the points in our data set from the mean will be equal on the left and right of the mean. So for example, let's say here we know our mean is 5. We'll use the same data set we did before. So the mean is 5. Think of this as a balancing point, like this is a seesaw and it's balancing perfectly on this fulcrum in the center. The mean of the data set is 5, so it's right at the center. If we imagine here a number line where we have 4, 3, 2, and we could keep going 1, 0 all the way on, or on this side, 6, 7, 8, like so. Our data points are 2, 4, 7, and 7. So let's go ahead and say here 2, 4, 7, and 7. If we imagine the mean extending up like this, our mean is at 5. The distance that we have from the mean to this data point here is 1 unit. From 5 to 4, that's 1 unit. And from 5 all the way down to 2, well, 5 minus 2 is 3. So that distance is 3 units. So we have a total distance of our data to the left of the mean from the mean of 4 units. On the right-hand side, this point is at 7. The mean is 5. 7 minus 5 is 2. So the distance here is 2 units. The distance here, since this point is 7, is also 2 units. So if we add up our total on the right-hand side, 2 plus 2 is 4. And we can see that we also have 4 units of distance on the right-hand side. So the mean is just the value that balances the amount of distance on the left-hand side with the amount of distance on the right-hand side. It makes them equal to each other. The median of a data set, the median is another measure of central tendency, it's a different way to measure the center of a data set. We'll again use the set 2, 4, 7, 7. So let's just go ahead and write that over here, 2, 4, 7, 7. In order to find the median, we always want to follow the same process every time. We take all of the values in our data set and we line them up in a row from smallest to largest. We've already got that done here, but sometimes our data isn't in order. It'll be all mixed around. It needs to be from smallest to largest. Once we have it in that form, then all we're doing to find the median is looking for the middle number. So in this case, what we would do is we would cross out the first number on the left, cross out the first number on the right, and we would keep going until we find the center. Now here, once we cross out those two numbers, we're just left with these two numbers here. If you get to a point where you only have two numbers left in the middle, then what you want to do is then find the mean of these two numbers in order to get the median. And so again, finding the mean is just adding up all the data points, in this case just the 4 and the 7, so 4 plus 7, and then you only have two data points there, so you divide by 2. 4 plus 7 is 11, 11 over 2, or that's the same as 5.5. So the median in this case would be 5.5. Keep in mind that if we had many more data points, for example, let's say we had 1, 1, and then another 2, and let's say over here we had another 7, and then an 8, and then a 9, we would have started crossing out the endpoints here and worked our way in like this, and crossed out the 2 and the 7, and then this 2 and this 7, and ended up with just the 4 and the 7. Take the mean, and then this value here gives you the median. This is what happens when we have an even number of data points in our set. So we can see we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points in this set. The reason it always works out that way when you have an even number is because you cross out an even number on the left-hand side. We were able to cross out 4. With the same number on the right-hand side, you cross out 4. And you're always still left with 2 data points in the middle of the set that you then have to find the mean of in order to get the median. But sometimes we'll have a data set like 1, 2, 3, 4, 5. Let's say this is our data set. We have in this set an odd number of data points, not an even number. In that case, when we start crossing things out, so the first value on the left with the first value on the right, then the next one with the next one, we're just left with one number. And then it's really easy because we just take that one number and that becomes our median. So when you have an odd number of data points, just line everything up in order from smallest to largest value, and then cross out values till you get to the center number, and that is your median. If you have an even number of data points, line them up from smallest to largest value, cross out data points on the left and the right in equal number until you get to what will be left, which is just 2 numbers in the center, then find their mean, and that will give you the median. The last measure of central tendency, and this is probably the easiest one, is the mode. This is just another way to measure the tendency of the data. And mode is simple because it's just the number that occurs in our data set most often. So, for example, if we have the original data set here, 2, 4, 7, 7, so 2, 4, 7, 7, the number 7 occurs in our data set more often than any other number. So 2 occurs once, 4 occurs once, and 7 occurs twice. So because 7 is the number that occurs the most, our mode for this data set is 7. It doesn't matter if we add more data points to this. Let's say, for example, instead of our set being 2, 4, 7, 7, it was 1, 2, 4, 7, 7, 8. 7 is still the number that occurs most often in the set, so the mode is still 7. In this data set up here that we used for the median, 1, 1, 2, 2, 4, 7, 7, 7, 8, 9, 7 would also be the mode of that data set because 7 occurs 3 times, whereas all of the other values only occur once or twice. 1 occurs twice, 2 occurs twice, 4 only occurs once, 8 and 9 both only occur once, 7 occurs 3 times, more than any other value in the set, so the mode there is also 7. If you have a data set like this, let's say 1, 1, 2, 3, 7, 7, there are 2 ways you could describe the mode here. You know that 2 and 3 are definitely not the mode because they only occur 1 time each, where 1 and 7 both occur twice. So then the question becomes, which is the mode? Is it 1? Is it 7? Is it both? Is it neither? Well, there's really 2 acceptable ways to answer it. You can either say that this set has no mode because there's no clear winner. 7 does not occur more than 1. 1 does not occur more than 7. There's no single number that occurs more than every other number in the set. And so we just say the set does not have a mode. It doesn't have a clear winner. And that would be okay. Or sometimes people will say that this set is bimodal. So they'll say bimodal. Remember that bi means 2. So bimodal means 2 modes. And you would say, of course, 2 modes because 1 occurs twice, 7 occurs twice. They're tied for the lead, so it's kind of like having 2 modes, and sometimes it's helpful to describe the set this way to indicate that there are 2 numbers that emerge as the mode. Now keep in mind that if we had, for example, the set 1, 1, 2, 2, 3, 3, 7, 7, we wouldn't say that this is quad modal. We wouldn't say that the mode is 1 and 2 and 3 and 7. All of the values in the set occur an equal number of times, so there's no real winner at all. We don't really say anything beyond bimodal, that there are 3 modes or 4 modes or more. This is just a special case where we may choose to say, you know what, there are 2 values that tied for the win, so we'll call the set bimodal. But for the most part, if there's no clear winner, we say that the set has no mode. We really want any mode that we mention to be the true clear winner of the set, like the 7 was in this set. We already talked about measures of central tendency, like mean, median, and mode, which are different ways that we measure the middle or the center of a data set. We also want to talk about measures of spread, which are kind of the opposite. It's how much and how is our data spread out around its center. So just as an easy example, is it really tightly clustered around the center in sort of a uniform distribution, a uniform way? Or is it scattered far away from the center and in an uneven, unbalanced sort of way? So those are the kinds of things we're talking about when we say measures of spread. In this video, we're going to talk about the 2 most basic kinds of measures of spread, which are range and interquartile range. Variance and standard deviation are also measures of spread, but we'll talk about those later on in the course. So let's go ahead and start with range, the range of a data set. Let's borrow a data set that we've already used. This is a stem and leaf plot of golf scores made by professional golfers in one day at a golf tournament. And the range of a data set is really easy. It's just the difference between the smallest value and the largest value. So we know from this stem and leaf plot that the smallest value in the data set, the lowest score, was given here by 66. The largest score was given by here, the 7 and the 5. So the highest score was 75, the lowest score was 66. So to find the range of this data set, we simply take 75, the largest value, and we subtract the smallest value, in this case 66, and the result is 9. So the range of the data set is 9. And it doesn't matter what your data is, what order it's arranged in, whether it's arranged here from smallest to largest. It doesn't matter the arrangement, the order, the values that are in your data. It's just always the largest value minus the smallest value, and that gives you the range. We talked before about the data set of the residents of San Francisco. if the oldest person who lives in San Francisco is, let's say, 106, and the youngest person who lives in San Francisco is, rounded to the nearest year, 0 years old, then our range for that data would be 106 because we took the largest value minus the smallest value. If we look at the heights of people in our class, and the tallest person in our class is, let's say, 72 inches tall or 6 feet tall, and the shortest person in our class is 5 feet tall or 60 inches tall, then we would take 72 inches minus 60 inches, the tallest person minus the shortest person, and the range of our data would be 12 inches. So this tells us that everyone in our data set is either between 60 inches and 72 inches. The entire interval or range that encompasses all of the people in our set is 12 inches wide. The number of years that encompasses the ages of all the residents in San Francisco is from 0 to 106 or 106 years. The range of golf scores scored by the golfers today in this tournament is a spread of 9. The difference between the lowest score and the highest score was 9. So all of the golfers in our tournament today scored somewhere in this 9-point range. Now let's talk about interquartile range. We write that as interquartile, like this, range. And we abbreviate interquartile range as IQR. When we talk about interquartile range, we want to think about this part of the word here, quartile. Quartile is a quarter. So when we're talking about interquartile range, what we're doing is we're measuring the distance between one quarter of the data and another quarter of the data. It's actually a little more specific than that. So let's look at this data set here. So this is just the data set of the golf scores. We've just broken it out from the stem and leaf plot and listed all of the scores in ascending order from lowest score to highest score. And here's how we find interquartile range. So first, we need to know how many data points we have. So if we count these up, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 golf scores. Which means that if we want to cut this data set in half or separate it into halves, we want to take the lowest 9 scores and the highest 9 scores. So we want to say 1, 2, 3, 4, 5, 6, 7, 8, 9. Because there are 18 scores, if we draw a line here, we have 9 scores on the left, 9 scores on the right, so we've separated the data into halves. Then we want to cut each half in half again. So we have 9 scores here on the left, which means we can't cut the data in half exactly because we have an odd number of data points. So we'll just take the midpoint. Since there are 9 scores on the left, that means that this is going to be the midpoint because it leaves 4 scores to the left of it and 4 scores to the right of it. Same over here, we had 9 scores to the right of the line, so we want to say 1, 2, 3, 4, which means this is our midpoint here of that, and then 4 scores to the right. So you can see here that we've now, in a way, divided our data into quarters. Roughly, this is the first quarter of the data, this is the second quarter of the data, the third quarter of the data, and the fourth quarter of the data. And these are called quartiles. The interquartile range is going to be the difference between this value we found here and this value we found here. In other words, the dividing line between the first and the second quartile, or the top of the first quartile, the bottom of the second quartile, is this number right here. This 71 score here is the top of the third quartile and the bottom of the fourth quartile. It's the dividing line between the third and fourth quartiles. And that interquartile range is specifically the difference between those two numbers. Therefore, in this case, to find the interquartile range, we just take 71 minus 68, and we get an interquartile range of 3. Interquartile range is helpful in measuring spread because it tells us that if the interquartile range is large, then the data is spread out far away from the median. If it's small, it tells us the data is more tightly clustered around the median. Now notice here that in this example, we had an even number of data points. Remember, we had 18 golf scores in our data set here, so we had an even number of data points, which means that when we went to find the median, we would have had to take the mean of these two numbers right here, which would have been 69. But either way, we would have known that the median lies in between these two numbers because at this spot, the median separates an equal number of data to the left as it does to the right. When that's the case, when we then go to find the median of just the left side and the median of just the right side, we're going to have an odd number of data points on both sides, which means that we're just going to be able to locate an exact value, the value in the middle, as sort of the median of the lower half and the median of the upper half. So it'll be really easy then for us to find the difference between those two numbers. But if we take a different data set, a data set that has an odd number of values in it to begin with, we see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're starting with an odd number of values. Then when we go to find the median initially, since we have 9 values, that means that this value here is the median because it leaves 4 data points to the left of it and 4 data points to the right of it, an equal number on both sides. So finding the median doesn't require us to calculate a mean or to put this line here between the two numbers. We can just grab an exact value here for the median. But then when we go to look at the lower half and the upper half, this time we'll have to take a mean like we did initially with the middle, because now our left and right halves have an even number of data points. So here we started with an even number of data points and we were left with an odd number of data points on each side. Here we start with an odd number of data points, which is going to leave us with an even number of data points on both sides. So here, to find the median of the lower half, since we have 4 data points, the median is going to be somewhere in between here, which means we need to calculate the mean of these two values. So that'll give us 68 plus 69 divided by 2 is equal to 68.5. And then if we look at the upper half, since we have 4 values, the median is going to be in between here, 2 values on the left, 2 values on the right, which means that in order to find that median, we need to calculate the mean of these two numbers. So 71 plus 71 divided by 2 is going to be equal to 71. So then the interquartile range in this case is going to be the difference between these two values that we found, or 71 minus 68.5 will be an interquartile range of 2.5. So just remember that when you're calculating interquartile range, if you start with an even number of data points, go ahead and draw your center median as just a line to separate the data into 2 perfect halves. That'll leave you with an odd number of data points on each half, and you can go ahead and quickly grab the median number. But if you start with an odd number of data points, you'll find your first median in the center easily. And then once you've got that median, splitting the data into 2 halves, just ignore that value from both halves. Just take the values on the left half and the right half and go ahead and find the center line that represents the median of both of those halves. That one, because you have an even number of data points on both sides, will fall in between 2 values, so you'll have to calculate means for both sides before finding the interquartile range. Now that we know about mean, median, and mode as measures of central tendency, and range and interquartile range as measures of spread, I want to talk about how those 5 measures will change if we make modifications to our data set, because this should give us a good intuitive idea of how those measures reflect changes in the data. Now, there are 2 ways that we can make modifications to our data set. One is called shifting, the other one is called scaling, and I want to start by talking about shifting. Shifting is what happens when we either add a value or subtract a value from every point in our data set. So, for example, let's say we have the data set 3, 3, 7, 9, and 13, so just a 5-point data set. We could calculate our mean, median, mode, range, and interquartile range for that data set. So for example, the mean would be 3 plus 3 is 6, plus 7 is 13, plus 9 is 22, plus 13 is 35, and we have 5 total data points, so 35 divided by 5 is a mean of 7. The median, we can see our data is already listed in ascending order from smallest to largest, so we can see that the middle number is 7, the median will be 7. And then the mode, we can see that 3, the value 3, occurs more in our data set than any other. 7, 9, and 13 all occur one time, but 3 occurs twice. So the mode of the data set is 3. The range, remember, is the largest value minus the smallest value. So 13 minus 3 is 10. And the interquartile range we could find if we do a little manipulation here. So we know that the median is 7, which means that to find the median of the lower half of the data, the lower half being 3 and 3, the interquartile range will be the mean of 3 and 3, which is just 3. And the median of the upper half of the data, so the upper half is 9 and 13, the median of 9 and 13 is going to be the value in between here, which is the mean of 9 and 13. So the mean of 9 and 13, 9 plus 13 is 22. 22 divided by 2 data points is 11. So we get 11 for the top half, 3 for the bottom half. So 11 minus 3 will be 8. So the interquartile range is 8. Now remember we said for shifting that we would be adding a value or taking a value away from every data point in the set. So for example, I could choose to add 6 to every data point in my set. That's just an arbitrary number I picked. I could choose to add any value or subtract any value. Let's just say I'm going to add 6 because I want to know what happens to my data when I add 6 to every value. So then my new data set will be this. 3 plus 6 is 9, 3 plus 6 is 9, 7 plus 6 is 13, 9 plus 6 is 15, and 13 plus 6 is 19. So I've shifted my entire data set by a positive constant, 6, and this is then my new data set. So if we calculate the same mean, median, mode, range, IQR for my new data set, here's what happens. The mean is going to be 9 plus 9 is 18, plus 13 is 31, plus 15 is 46, plus 19 is 65. When I divide 65 by the number of data points I have, 5, I get 13. So the mean is 13. The median, I can already see, is my middle value right here. So the median is 13. The mode is the value that occurs most often. That's going to be 9. The range is the largest value minus the smallest value. 19 minus 9 is 10. And the interquartile range, we already have the median. We look at the upper half of the data, 15 and 19. We need to find the median of 15 and 19. Well, that's going to be the mean of 15 and 19. So 15 plus 19 is 34. 34 divided by 2 is 17. So I get 17 for the upper half. And then the mean of 9 and 9 is 9. That's the median for the lower half. So 17 minus 9 is going to be 8. So in order to shift our data set, we added 6 to get from the original data set to the second data set. And look what happened. Our mean, we added 6 to get the new mean. We added 6 to get the new median. So 7 plus 6 is 13, 7 plus 6 is 13. And we added 6 to the mode to get the new mode of 9. In other words, the mean, median, and mode all changed in the same way that we changed the data set. So we added 6, which means to find the new value of the mean, median, and mode, we also have to add 6. But the range and interquartile range stayed exactly the same. And that should make sense to us because the mean, median, and mode are all measures of the middle, and we've taken this whole data set and shifted it up or shifted it to the right on the number line, so the middle is going to change. But the spread of the data set stays the same. We just move the whole group of data up together, so the range is going to stay the same. The interquartile range is also going to stay the same. So the punchline is what I already had written here, that when we shift the data set either by adding a constant like we did here with +6, or by subtracting a constant, in both cases, the mean, median, and mode will change by that same constant value, but the range and the interquartile range will stay the same. Now, what about if we multiply or divide our data set by some constant value? So here we added 6, but what if, for example, we multiplied everything by 2? Well, this time I'll give you the punchline up front. This is called scaling, when we multiply or divide by a constant. And when we do that, we're going to get all 5 measures, mean, median, and mode, and range and IQR, to change by that same constant value. So if we multiply the entire data set by 2, that means we're also going to multiply the mean, median, mode, range, and IQR by 2. If we were to divide the entire data set by 4, that means we would divide the mean, median, mode, range, and IQR by 4 to get the new mean, median, mode, range, and IQR. If we want to prove it, let's take again the same data set, 3, 3, 7, 9, 13. We already know that the mean, median, mode, range, and IQR are 7, 7, 3, 10, and 8. Let's say we want to multiply by 2 to get our new data set. So we're going to multiply by 2. Our new data set will be 3 times 2 is 6, 3 times 2 is 6, 7 times 2 is 14, 9 times 2 is 18, and 13 times 2 is 26. So we have our new data set. Now let's quickly calculate those new values. So for the mean, if we add these together, 6 plus 6 is 12, 12 plus 14 is 26, 26 plus 18 is 44, and 44 plus 26 is 70. 70 divided by the number of data points 5 is 14. So we get a value for the new mean of 14. The median, we can see here, is still the middle number, so the median is still going to be 14. The mode of the data set, 6 occurs more often than any other value, so the mode is going to be 6. The range will be the largest value, 26, minus the smallest value of 6. 26 minus 6 is 20. And the interquartile range, again, because we have just 2 data points on the left here, we'll find the mean of 6 and 6. That's going to be 6. And then the mean of 18 and 26 is 22. So 22 minus 6 gives us 16. And what we can see happened here, when we multiplied the data set by 2, we multiplied the mean by 2 to get the new mean. We multiplied the median by 2 to get the new median. We multiplied the mode by 2 to get the new mode. And the range and IQR got multiplied by 2 as well to get the new range and new IQR. So to summarize, we can say that when we shift the data, the mean, median, and mode change, but the range and IQR stay the same. And when we scale the data, meaning multiply or divide, the mean, median, mode, range, and IQR all change. The last thing we want to talk about in this video are outliers. And outliers are values in the data set that are much higher or much lower than any of the other values. So let's take an easy example and pretend that we have the data set 1, 2, 3, 1,000. So we have 4 points in our data set. And what we can say is that 1,000 is clearly an outlier. So if we were to graph this on a number line, what we would see is that the bulk of our data, 3 out of the 4 values, are clustered right here around 1, 2, 3. They're all together. And then way, 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 way out to the right, we have this data point 1,000 all by itself. So it's an outlier. It lies way outside of the rest of the data all by itself. What we want to do is use this outlier to show the effect on the mean and the median, and to prove that the median is more resistant to change than the mean is. So here's what we mean. Let's pretend for a second that we actually only have the data set 1, 2, 3. 1,000 is not included in that data set. So if we just have 1, 2, and 3, and we want to calculate mean and median, here's what we get. The mean will be 1 plus 2 is 3, 3 plus 3 is 6, 6 divided by 3 terms, so 6 divided by 3 is going to be equal to 2. So the mean of the data set is 2. The median of the data set is also 2, so we already have our data set listed in ascending order from smallest to largest, and the middle number is 2. So the median will also be 2. Now, if we suddenly expand our data set to include the 1, 2, 3, and the 1,000, so now we have all 4 terms in our data set, what do you think is going to happen to the mean versus what do you think is going to happen to the median? Well, it'll become obvious pretty quickly. If we calculate the new mean, so we have here the new mean, we got 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 1,000 is 1,006. So the sum of the terms is 1,006. And then we have 4 terms in the data set, so we want to divide that by 4. Well, 1,006 divided by 4 is approximately equal to 252. It's right about that. The median of the new data set, on the other hand, so the median of the new data set, we have our terms listed in ascending order, 1, 2, 3, 1,000. So the middle number, let's see, 1 and 1,000 are on the ends, then 2 and 3. So the median is going to be right here between 2 and 3, which means that in order to find the median, we need to take the mean of 2 and 3. Well, the mean of 2 and 3, let's see, 2 plus 3 is 5. So 5 divided by 2 terms is equal to 2.5 or 2.5. So look what happened. We added this huge outlier above the data set, so a number that was much larger than the rest of the data. And the median barely changed. The original median was 2, the new median is 2.5. It's almost the same thing. The mean, on the other hand, went from 2 all the way up to 252. These are totally different means. Adding the 1,000 outlier totally skewed the mean and pulled it all the way up from 2 to 252. And that should make some intuitive sense to us because when we look at this data set, we can tell just by looking at it that the 1,000 is really going to pull up the mean way above the 1, 2, and 3. But the median, because we're still just talking about the middle number in the data, we could have a huge outlier or even 2 huge outliers way above the data set or 2 huge outliers below the data set, and the median might barely change because it's still just this number right here in the middle. So the way that we describe what's happening here is that we say that the median is much more resistant to change than the mean. So it's much, much harder to move the median. The median is much more likely to stay steady, stay around its original value than the mean is. It doesn't take much at all. We can just add 1 data point and totally throw the mean off to make it something way different than it was originally. So the mean is very easy to change. The median is much more difficult to change. So we say that the median is more resistant to change. And then regarding outliers, we want to take away this idea that if we add an outlier way above the data set, then it's going to skew the mean up higher than it would normally be without the outlier, and the mean will change more than the median. If we add a data point way below the data set, for example, let's say our data set instead were 98, 99, 99, and then we went and added the outlier 1 way below the data set, that's going to pull the mean down drastically. The mean's going to go from something around 98, 99 way down closer to 1, but the median will stay very similar. And then the same would be true in the opposite case. If we start with a data set like this, 1, 98, 99, 99, and we eliminate an outlier, so we get rid here of this 1, and now we just have 98, 99, 99, that will let the mean come back up to be much closer to this tightly clustered group of data. So again, the mean will move a lot and move up much higher. The median, again, will retain its original value much more closely versus the mean will jump a lot. So overall, we're just saying that adding or removing a high outlier, an outlier that's way above the data, or adding or removing a low outlier, an outlier that's way below the data, is going to shift the mean much more than it will shift the median. Since we're on this topic of measures of central tendency and spread, I want to talk about box and whisker plots, which are a kind of graph or plot or picture, a great way of showing us some of these measures. So here's an example of what a box and whisker plot might look like. I just want to jump right into it because I think this is the easiest way to illustrate what it actually is. So you'll notice here that you have a number line along the bottom. You always have that as part of a box and whisker plot, but it doesn't necessarily run always from 0 to 15. You could have a range here of any set of numbers depending on your data set. The data set is represented in this figure up here, which is the box and whisker plot itself. This plot, this picture, is always going to have this box in the center, which is where the box part of box and whisker comes from. And then it's always going to have these lines out to the side. They can be varying lengths, but they'll have the lines out to the side and then very often a little dot on the end. These lines with the dots on the end, these are the whiskers of a box and whisker plot. So you have the box in the center, you have the whiskers on either side, and then you're always going to have this vertical line here somewhere inside the box. Now here's what's so great about a box and whisker plot, even though this doesn't look very interesting as is. This little line in the middle represents the median of the data set. So we know just by looking at the plot that our median is at 11. So we can call the median here, that is 11. So the median is represented by this line, and we can always see where that is. The range of the data set is always going to be given by the rightmost point of this right whisker minus the leftmost point of the left whisker, because this rightmost point here represents the largest value in the data set. So this here is the largest value, and this point is the smallest value. So in order to find the range, we just take the largest value, which it looks like is 14, so 14, minus the smallest value, which it looks like is 2. So the smallest value is 2. The range will be 14 minus 2, or 12. So it's really easy to see the range from this plot as well. Remember before that we also talked about the quartiles of the data when we were talking about the interquartile range. Well, this whisker here always represents the first quartile, or Q1. The part of the box that's to the left of the median represents Q2, the second quartile. The right side of the box, so the box to the right of the median, will be Q3, and then the whisker here on the right side will be Q4, the fourth quartile. So what this tells us is that a quarter of all of the values in our data set fall somewhere here in the first quartile, so somewhere between 2 and 5. A quarter of our data lies in that interval. A quarter of our data lies in the interval 5 to 11. A quarter lies in the interval 11 to 13. And then the last quarter lies in the interval 13 to 14. Therefore, to find the interquartile range, we just take this point right here, the right edge of the box, the value that's between the third and fourth quartiles, and we subtract the value that's between the first and second quartiles, which is the left edge of the box. So the interquartile range will be 13 minus 5, or 8. What we can't tell from a box and whisker plots are the mean or the mode. We're not able to tell where the mean is and where the mode is in a box and whisker plot. We can't calculate their exact values, but we can get the median, the range, the interquartile range, the smallest value, the largest value, and the range of each quartile, the first, second, third, and fourth quartiles. because we collect all this information from a box and whisker plot, we oftentimes will summarize this data in what's called a 5-number summary or 5-figure summary. So we call this a 5-number summary. And this is basically just another way of displaying the same information that we get from a box and whisker plot. So both of these kind of give us the same information. We get the minimum value here of 2, which we can get from the end of the left whisker. We get the maximum value from the rightmost point on the right whisker, and so we list that maximum value there. We also know that we have the median here at the vertical line, and we give the median here. And then we give the endpoints of the box, or this dividing line between the first and second quartiles, as Q1 here, and then the dividing line between the third and fourth quartiles as Q3 here. And so this 5-number summary really gives us the same picture as the box and whisker plot, because we can essentially see here the endpoint coming here to the edge of the box, coming here to the median, coming here to Q3, and then coming here to the maximum point. So we get those values, they correspond to these points on the box and whisker plot, and we can really express this data either way. So they both give us these key points of minimum and maximum values and the median, and the first and third quartile values. Before we talk about mean, variance, and standard deviation, which is going to be the subject of this video, we need to talk briefly about the difference between a population and a sample. So when we say population in statistics, we really mean the entire group or all of the subjects in a population. So a lot of times, because we can't or don't want to study every single person, subject, object, whatever, in the population, we just look at a subset and call that the sample. What we hope is that if we have the entire universe of the population, so we call this whole thing here the population, and then we just extract just this portion here, we take that out, and we call that the sample, we're hoping that this sample will be somewhat representative of the population as a whole. So if we just study a few of the subjects, then maybe that will give us an idea of what the population looks like. So in the polar bear example, maybe we find 100 polar bears. We use that for our sample. We study them, we collect data about those 100. We use them as our sample, and then we make inferences based on the data that we find about those 100 about the population. So maybe we would measure the height of all 100 polar bears in our sample, get a mean height for the sample, and then guess or infer that the population height is pretty similar to our sample, hoping that the sample was representative of the population. When it comes to mean, variance, and standard deviation, it's really important that we know whether we're talking about a population or a sample, because the formulas that we'll use to calculate mean, variance, and standard deviation differ from each other depending on whether we're looking at the population or the sample. So let's go ahead over here and make a chart. So we'll call this population, and then we'll call this sample. And then the first thing we want to differentiate is the number of subjects, or we'll just say subjects here. So when we talk about the number of subjects in a population versus a sample, when we're talking about the number of subjects in a population, we denote that with a capital N. So if you see that capital N, it means we have a population. We're looking literally at every single person, object, subject, whatever it is, in our population. When we have a sample, we use lowercase n, which means that we took a sample and the number of subjects in our smaller sample, our subset of the population, we describe with lowercase n. Which means then that when we're talking about the mean of a population versus a sample, the formula for the mean of a population and a sample is the same except for this capital N versus lowercase n. So remember before we found that the mean was the sum of all of the data points divided by the number of data points. Or to write that technically, we said mu, the mean, is equal to the sum from I equals 1 to n of x sub I, all divided by n. So for a population mean, we make both of these n's capital N's. But for a sample mean, we usually use, instead of mu, we usually use x bar, which means the mean of the sample. And the formula is exactly the same, except that we use lowercase n instead of capital N. So we have the lowercase n up here, and then we have the lowercase n in the denominator. Now, as we go here, we've already got the formulas for mean. We're going to go through variance and standard deviation, but let's work through an example on our way. So let's bring back our golf scores example. These are 18 golf scores from professional golfers. Let's say we had 18 golfers in our tournament. These are the scores that they shot today. So the number of subjects, n, if we're just interested in golf scores from this tournament from today, it would be the population, capital N. So we would say that capital N is equal to 18 because we have 18 scores. Then if we want to find the mean, we would say that mu is equal to, we would add all of these together, and 68 plus 67 plus 67 plus 68 plus 68, all the way on, we keep adding up to 75. We add all those golf scores together, we get a total of 1,250. And then we know that we have 18 data points, so we divide that by 18. When we take 1,250 divided by 18, we get approximately 69.4, which means that the mean score in our population was 69.4. That should be pretty familiar to us because we've already talked about mean. But what about variance? Well, think about variance as a measure of spread. It tells us how our data is spread out around the mean. The formula here for population variance, and let's kind of unpack it together, is x sub I minus mu. So first of all, remember that x sub I represents any single data point in our set. So for example, we could plug in 66 as the first value of x sub I, then plug in 67 as the second value of x sub I, then the other 67 we could keep going through. So basically we take each data point and we plug that in for x sub I, and then we subtract from that the mean that we found, mu. So what's that telling us? Well, it's really just giving us the distance between each data point and the mean. So for example, if we took this lowest value here of 66, and we subtracted from that the mean, 69.4, we would get a value of negative 3.4. If we took the largest value in our data set, 75, and we subtracted the mean, 69.4, we would get a value of 5.6. So what that tells us is that 66 is 3.4 below the mean, and 75 is 5.6 above the mean. In either case, we're just getting distance away from the mean. Then in the variance formula, we go ahead and square that distance. So when we square that, first of all, whether we took a data point that was to the left of the mean, like 66, and got a negative value here, or took a value that was to the right of the mean and got a positive value, when we square it, we're going to get a positive value in either case. So this value will always become positive, and then whenever we square a distance, what we get is an area. So if we have some distance, like 5.6 units, so we say this distance is 5.6 units, let's say. When we square it, really, we're just creating a square that is 5.6 by 5.6, and we're creating area instead of distance. So this x sub I minus mu squared gives us a piece of area. One of the reasons that we square this value in the variance formula is because it's really going to give more weight to outlier data. So the farther the data point is from the mean, the bigger square it will create. Later on in the course, we're going to see why this is helpful, because what we're going to try to do is minimize the size of all our squares. Obviously, every single one of these points will create a square of a different size. We're trying to minimize the size of the squares in order to minimize the variance. So that's what we do. We square the distance to get an area, and then we add all of those together. So we say starting with I equals 1 and going up to the very last data point in the population, capital N. And then we divide that whole thing by the number of data points we have, capital N for our population, and the variance is equal to sigma squared. The reason that we call the variance sigma squared instead of sigma is because standard deviation is just going to be the square root of this value, and we want that to be just sigma. So we keep the variance squared. We always define the variance as sigma squared, and then this is the formula for the population. The formula for the sample is going to be similar. So instead of sigma squared, which is what we use for the population, we usually use capital S squared for the sample. And we define that as the sum from the first term to the last term in the sample, lowercase n, and we still say x sub I, but now we're subtracting the mean of the sample instead of the mean of the population. So we subtract x bar instead of mu, and we square that, and then we divide that by the number of the subjects in the sample, lowercase n, instead of capital N. When we're dealing with a sample, and this is something that I won't go into in this video, but using just the number of subjects in the sample, n, actually creates a biased value for sample variance. In other words, it doesn't give us a super accurate value for the sample variance. And again, I won't use this video to talk about why. I just want to tell you that when we find sample variance, instead of using just lowercase n, the number of subjects in the sample, we want to use n minus 1. N minus 1, surprisingly enough, is what gives us the most accurate value for sample variance. So when we just have n in the denominator, we call that formula biased sample variance because it gives us a biased value. When we add in the minus 1 here, that sort of corrects the error that's in the formula, and so we call this formula here with the n minus 1 unbiased sample variance because it gives us the most accurate value of sample variance. Therefore, when people say that they're finding sample variance or they're using the sample variance formula, what they usually mean is the unbiased version because, of course, they're going to try to get the most accurate value they can. So this formula is the one that we use by default for sample variance because it's the unbiased version or the most accurate version. Now, if we want to find the variance for this population of golf scores, here's what that would look like. We would call that sigma squared. So sigma squared is equal to, and then we are going to sum up from the first term all the way to the 18th term because we have 18 subjects here in our sample. And we're going to find all of the squared distances. So again, 66 minus the mean, 69.4, gives us negative 3.4. Negative 3.4 squared is 11.56. So 11.56 is the value of x sub I minus mu quantity squared for the first term. Then we would find 67 minus 69.4. That's negative 2.4. And if we square that, we get 5.76. That means we'll get 5.76 for this 67 as well. So 5.76. If we take 68 minus 69.4, we get negative 1.4. And if we square that, we get 1.96. There are 4 68 scores, so we'll get 4 times 1.96. 69 minus 69.4 is negative 0.4. Negative 0.4 squared is 0.16, and there are 4 scores of 69, so plus 4 times 0.16. And what we would do is we would keep going with 70, 70, 71, 71, 72, 73, 75, until we got to the last score of 75. and we would add all of these together. Once we have that whole sum, we just want to divide it by the number of subjects that we have in our data set, which again is 18. So we divide that whole thing by 18, and we get from that 88.48 divided by 18, or approximately 4.92. So the variance then of this population of golf scores is 4.92, and now we just need to find the standard deviation. And I mentioned briefly before that the standard deviation was just going to be the square root of the variance, and that's true. It's as simple as taking the square root of the variance that we already found. So if you need to find standard deviation, the hard part is finding the variance, and then all you have to do is take the square root of it in order to find standard deviation. So standard deviation is going to be the square root of sigma squared here, which of course, when you take the square root of something that's squared, the exponent and the root cancel with each other, and we can just say that the standard deviation is equal to sigma. And then same thing here, sample standard deviation, because that was standard deviation for the population, sample standard deviation is going to be the square root of s squared, which will just be equal to capital S. When we take the square root of 4.92, we get a standard deviation for our golf scores of approximately 2.22 if we round to the nearest hundredth. So that tells us that for our population of golf scores, we got a mean of about 69.4, a variance of about 4.92, and a standard deviation of about 2.22. In this video, we're looking at the relationship between histograms and density curves, because going forward in the course, we're going to be using density curves much more often. So what I want to do here is show you how we essentially build a density curve from a histogram, because that's essentially what a density curve is. It started out as a histogram, and we transformed it so that it became a density curve. So I want to walk through that process in this video. So let's say, for example, that we're looking at the population of San Francisco by age. So we have all of the citizens of San Francisco. There's between 800 and 900,000 of them. And we've graphed them in a histogram by their age. So everyone between age 0 and age 9 is represented in this bar. Everyone between age 10 and 19 is in this bar. Everyone from 20 to 29 years old is in this bar, etc., all the way up to the oldest people in the group, who are 100 to 109 years old. And this histogram, and we know it's a histogram instead of a bar graph because we've grouped the ages into buckets of a decade each, or 10 years each. This first bar represents 10 years, the second bar represents 10 years, the third bar represents 10 years. So we have equally sized groups, and therefore this is a histogram instead of just a bar graph. Each bar here is population in thousands, and so if we put in our vertical axis, this is in thousands here. So this is 200,000 people, 150,000 people, 100,000 people, etc. So what we could say is that all of the people ages 20 to 29, maybe there are, 80,000 or so of them, versus there are just over 150,000 30 to 39-year-olds. So this is our histogram, and it's important to know that we also call this a frequency histogram. So histogram and frequency histogram are more or less synonyms because each bar in our histogram really shows the frequency at which that value occurs. So what is the frequency at which 30 to 39-year-olds occur in our data? Well, about 150,000 or so are ages 30 to 39. So this is a histogram. It's also called a frequency histogram. Now, from here, we can change this into what's called a relative frequency histogram just by changing the vertical axis. So here's what we would do. We would take the number of people represented in each bar, and we would divide that by the total number of people represented in the histogram. So for example, let's say people ages 80 to 89, there are just over 50,000 of them, but let's just say that there are 50,000. So there are 50,000 80 to 89-year-olds. And we know that this chart represents a total of 865,000 people. So if we divide 50,000 by 865,000, so 865,000, we get approximately 0.06 or 6%. So about 6% of the total population are people ages 80 to 89. And what we would do is we would go through for each bar and perform that same calculation. So for example, the 30 to 39-year-olds, there's about 150,000 of them. So we'd take 150,000 divided by 865,000, and we would get a percentage just like we did for the 80 to 89-year-olds. After we have a percentage for every interval, then to turn this into a relative frequency histogram, we just swap out the vertical axis. So our vertical axis here goes away. We change it out for this one. So what you notice here is that we have a value of 0.05. Well, that's the same as 5%. So we could also write this 5%. 0.1 is 10%, 0.15 is 15%, and 0.2 is 20%. So what the vertical axis is allowing us to see then is that instead of knowing that there are about 150,000 30 to 39-year-olds, now our vertical axis allows us to quickly see that about 15% of our total population are 30 to 39-year-olds, or just over 5%, about 6%, are 80 to 89-year-olds. So it just changes the axis so that we're seeing, instead of the actual number of people, we're seeing the percentage of the total data set. So you can see here that 40 to 49-year-olds, they make up the largest group in our population. Since this line is 15% and this line is 20%, they're maybe at about 17%. So the largest group in our data set only makes up 17% of the total data. All of the other groups are some smaller percentage than that. So here about 15% of the data is in 30 to 39-year-olds. Maybe about 13% or so is 60 to 69-year-olds, 12% maybe is 50 to 59-year-olds, etc. So it just lets us see the data in a different way. When you have these percentages here as the vertical axis, that's what makes this a relative frequency histogram. Now, if we show this as a line graph instead of as a bar graph, in order to turn it into a line graph, all we need to do is plot a point at the top of each bar. So we plot a point at the top center of each bar, and then we connect each of those points with a straight line like this. Now, if we remove the bars and we just take the line part of the graph and we bring it over into its own graph, this is what's called a frequency polygon. So we'll go ahead and label that. This is called a frequency polygon. It's a polygon because, remember, poly means many, so this is a many-sided figure. We have straight sides, so it's a many-sided figure. And the reason a frequency polygon is important is because sometimes if we have, for example, a perfectly triangular frequency polygon or a perfectly rectangular frequency polygon, we can use simple geometry to find the area under the frequency polygon over a certain interval. Now here's where we go from a histogram or a frequency polygon to a density curve. So notice that when we started here with our histogram or a frequency histogram, we were grouping all the people in San Francisco into buckets by decade. So all of the kids under 10, all the kids between 10 and 19, all of the people between 20 and 29, etc. Well, the fewer buckets we use, the more inaccurate our polygon is going to be. If we only used 3 buckets instead of what we have here as 11, if we only use 3 buckets, then our polygon might be really abrupt connecting the tops of those 3 bars. But since we've used 11 buckets, our polygon can follow this a little more closely. The more buckets we use, the more bars we have here, the more closely these straight lines, the more closely our polygon is going to follow the tops of the bars. And you can imagine, if this were possible, if we start using more and more and more and more and more bars to show the data in this histogram, then our polygon really starts to smooth out because the distance from one bar to the next is a lot closer. So we're going to get a smoother and smoother curve the more buckets or the more bars that we have. So the idea is that if this were possible and we could use an infinite number of buckets to show our data, our polygon would get totally smooth, and when it's totally smooth, that's when it becomes a density curve. So for this example, and this is totally rough, but the density curve might look something like this. It would follow the data as it goes along and become a smooth curve. And this is the density curve for the data. Once we have the density curve, we can start thinking more clearly about the area under the curve. So for example, if we wanted to know how many people in San Francisco are age 70 or older, so right at about this cutoff right here, everybody 70 or older, we would want to look at the total area that falls under that curve, because remember, the amount of data will always add up to 1.0 or 100%. Remember before over here we said the 40 to 49-year-olds made up about maybe 17% of the population, and then the 30 to 39-year-olds made up about 15% of the population. Well, if we were to add those all up, so 15 plus 17 is 32, so these two groups together make up 32% of the population. If we add all those bars together, we're going to get to 100%. The whole population is 100% of the population. So then we can say things like, if we want to know the 70-year-olds or older, we can shade in about that area of the density curve. And since we're saying that all of the area under the curve will make up 100% of the population, then we can estimate things like the fact that this area maybe looks like it's approximately 25% maybe of the total area under the curve. I mean, you could say it's a little more, 30% maybe it's less, 20%, since it's just this little tail piece here. But let's just say that this is 25% of the total area under the curve. That tells us that 25% of our population is going to be 70 years or older, because this is the 70 years or older mark in our interval right here. So we would shade in that area, and then based on how much area is there under the curve, that's how we would estimate total percentage of our population. In this video, we're going to talk about symmetric distributions and skewed distributions, and even though we've already talked a little bit about outliers, we're going to come back to them to show how skewed distributions and outliers are related. So in statistics, we deal a lot with symmetric distributions, which might look something like this. So we could plot lines here and then graph a curve that looks something like this. This is called a symmetric distribution because it is symmetric or symmetrical about some center line. So if I look here at the center line, the distribution is a mirror image of itself on both sides of the center line. So this left half of the distribution is a mirror image of the right half and vice versa. So it's a symmetric distribution. This curve in particular is called a normal distribution. It's a really special kind of distribution with this bell-shaped curve here. And we talk a lot about this normal bell-shaped distribution later on in the course. But a symmetric distribution doesn't always have to be the normal bell-shaped curve. In fact, it can take on any shape as long as it's symmetric about the center line. So no matter what it looks like, if the left-hand side is a mirror image of the right-hand side, you can call it a symmetric distribution. Now with a symmetric distribution, the center line that creates the mirror image on the left and right-hand side, so the line right down the center, will always be where the mean occurs. So the mean of the distribution is right here at the center line. It just so happens that the median is also right along the center line as well. So both the mean and the median have this value of the center line, the line that makes the distribution a mirror image, regardless of what that value is. In contrast, we can also look at a skewed distribution. So again, we'll just have the same plot, but our distribution might look something like this. So instead of the area under the curve being equally distributed on either side of some center line, in a skewed distribution, the area under the curve is either shifted to the right side or shifted to the left side. When we look at a skewed distribution like this smaller area over here on the left, this low area right here, we call the tail of the distribution. Therefore, because this tail, the tail of this distribution, is on the left-hand side, we would call this distribution a left-skewed distribution. Sometimes we call it a left-tailed distribution, or we could also call it a negatively skewed distribution. All of these are synonyms for the same kind of distribution. So this distribution is left-skewed, left-tailed, or negatively skewed. They all mean the same thing. It means that this tail is on the left-hand side. So when you're trying to remember what to call the distribution, just think about where the tail is. Now, unlike a symmetric distribution where the mean and median occur right along the center line here, in a skewed distribution, mean, median, and mode will all occur at different points along the distribution. Now, I've just sketched these in roughly to be representative. I don't know if they're actually at these points. What matters here is the order of the mean, median, and mode, because the order will always be the same. So with a left-skewed distribution, the mean is always going to be over here on the left side, closest to the tail. That's because there are values over here within our data set at the end of the tail that are outliers in the data set and are pulling the mean toward those outliers. They're pulling the mean this way. The center line here is the median of the data set, and the median specifically is going to be at whatever point divides the area under the curve in half perfectly. So the median will be wherever all the area on the left-hand side of the line is equal to all the area on the right-hand side of the line. And the median will always be to the right of the mean in a left-skewed distribution. And then this point here is the mode. The mode will occur at the peak of the distribution. So wherever the distribution is highest, that's where the mode will be. So for a left-skewed distribution, the order will always be mean on the left, then median, then mode. We can contrast this with a right-skewed distribution, as you may have guessed. So again, we would draw lines here, and our right-skewed distribution would be sort of a mirror image of the left-skewed distribution, and we would again put in our 3 lines here. So we would call this a right-skewed or right-tailed, because the tail is on the right, or positively skewed distribution. And then our mean, median, and mode are flipped. So now the mean is on the far right because the outliers in the data set that are in the tail here are pulling the mean toward the outliers. They're pulling the mean toward the tail. The median will be in the center. Again, it is the line that divides all of the area under the curve in half completely, such that 50% of the area is to the left of the median, and 50% of the area is to the right of the median. And then this far left line will be the mode. And again, the mode will occur wherever the data peaks, the highest point here of the right-skewed distribution. Now, since we've been talking about outliers that exist here in the tails of these left and right skewed distributions, and these outliers are pulling the mean of the data towards themselves, let's go ahead and take a second to talk a little bit about outliers. So if we want to give an example of a real data set that has a skewed distribution because of an outlier, we could look at this data set here. We've created a dot plot for it, and you can see that the vast majority of the data is clustered between 66 and, 71, 2, 3, and 73. We have one value here at 75, and then we have a value all the way up here at 103. This would be an example of a data set that would create a skewed distribution. Because if we were going to draw a distribution for this, and this is totally rough, but it might look something like this, where we have the bulk of our data coming here, and then we have this coming here, and the tail, drifts off this way, something like that. So we can tell right away this is a right-skewed, right-tailed, or positively skewed distribution. And if it weren't for this outlier up here, we wouldn't have this long tail on the right-hand side. If we can imagine that data point gone, and we just have all of our data tightly clustered here, it wouldn't be a perfectly symmetric distribution. We can see our data isn't perfectly symmetric, but it might look roughly normal or roughly symmetric because all of the data is, pretty tightly clustered around this area. It's when we have an outlier like this that this tail can be created along the right-hand side of the distribution and skew it out to the right side. Now, whenever you have a skewed distribution like this one, where you have an outlier that's pulling the data to one side or the other, your median is going to be a better measure of central tendency than the mean, because the mean is getting skewed by the outlier. Like we saw in our distributions here, the mean is either this far left line or the far right line, the line closest to the tail, because it's getting skewed by the outliers. So if you have a skewed distribution and you want an accurate representation of central tendency, the median is going to be a better bet than the mean. And similarly with spread, measures of spread, the interquartile range will be a better measure of spread than the standard deviation. That's when you have a skewed distribution. When you have a symmetric distribution, mean and standard deviation are going to be better measures of central tendency and spread. So you could almost say it this way. You could say median and IQR that we put with green check marks, those are better for skewed distributions, whereas mean and standard deviation are going to be better for symmetric distributions. Now with this data set up here that we have the dot plot for, if we actually found the median of the data, we would see that it's 69. The interquartile range is 3, and we know that the mean is 71. Standard deviation would be approximately 7. Because this is a skewed distribution, we would expect median and interquartile range to be a better measure of central tendency and spread. We can see that that looks like a pretty good measure of central tendency, 69 here, right at about the center of the data, it looks like. So that feels like a roughly good measure of central tendency and spread. On the other hand, a mean of 71 would put us about here, which doesn't really feel like the center because most of the data is over here to the left of that value. There are fewer data points to the right of that. And then a standard deviation of 7 really includes almost everything. We'd go out 1, 2, 3, 4, 5, 6, 7, all the way to here. So standard deviation, one standard deviation that way, and then 1, 2, 3, 4, 5, 6, 7, so all the way out to here. And from what we're going to learn about standard deviation in the next few lessons, this doesn't really make very much sense. Median and IQR are definitely better measures for the skewed distribution. The last thing we want to say here about outliers, like this point up at 103, is that a lot of times we feel like we can just eyeball an outlier because we see this data point and we can tell it's really far away from the bulk of the data or all of the rest of the data. So we would feel pretty comfortable calling that an outlier. But there is actually a technical way that we use, or a rule that we use, to calculate what is an outlier and what's not an outlier. The rule is called the 1.5 IQR rule, where IQR is interquartile range. And what it says is that, first of all, we can have low outliers and high outliers. So low outliers are outliers that are below the data. So most of the data is here in one spot, and then we have an outlier that's way below the bulk of the data. That would be the case in a left-skewed distribution. And then in a right-skewed distribution like this one, we will have one or more high outliers, which are outliers that are above or higher than the majority of the data. Remember before when we talked about box and whisker plots, we were able to come up with values for the first, second, third, and fourth quartile, and we called those Q1, 2, 3, and 4 respectively. Well, to calculate a low outlier, we would use the formula Q1 for the first quartile minus 1.5 times the interquartile range. So we would take our interquartile range, in the case of this data set, it would be 3. We would multiply 3 by 1.5, so we get 4.5 there. And so we'd say that low outliers are any values less than Q1 minus 4.5. The formula for high outliers is going to be Q3 plus 1.5 times the interquartile range. So any value above this value or higher than this value is going to be a high outlier. So again, we'd take the interquartile range of 3, we'd plug it in here, multiply by 1.5, we'd get 4.5, so we would say a high outlier for this data set is going to be any value larger than Q3, the third quartile, plus 4.5. And that's just a rule that we can use to define outliers in a specific way. But as the takeaway for this video, just remember how high outliers will skew the data to the right, creating a right-skewed distribution, and low outliers will skew the data to the left, creating a left-skewed distribution. We've talked about probability distributions with different shapes, including the normal distribution that looks like this. We've also talked about skewed distributions, where the distribution is left skewed, where we have the tail on the left and then the big hump that comes up on the right-hand side. And then right skewed distributions, where we have the big hump on the left and the tail on the right-hand side. I want to spend some extra time focusing on normal distributions and some other things that we know about them, because normal distributions come up all the time in both probability and statistics, so they become extremely important for us to understand in detail. So again, this is a probability distribution curve for normally distributed data. The mean of a data set for normally distributed data will always fall right in the middle of the normal distribution. So the mean is right here at the center. This is also where the median is located. So both the mean and median will divide the area under the distribution curve in half exactly. Remember also that the area under a distribution curve will always be equal to 100%, or 1.0 if we write it as a decimal. So we really have to think about the area under the curve in terms of percentages. For example, because the area under the curve will be 100% of the probability, we could say that we have 50% of the probability to the left of the mean or median, and 50% of the probability to the right of the mean or median, because we have 50% of the area to the left and 50% of the area to the right. Similarly, normal distributions follow what's called the empirical rule. So we'll go ahead and write down here the empirical rule, which is also called the 68, 95, 99.7 rule, which is a funny name for a rule, except that it's very practical, because what it tells us is that specifically for normal distributions only, we'll always have approximately 68% of the area within one standard deviation of the mean. In other words, let's go ahead and say, for example, that one standard deviation away from the mean looks like this. So if we head from the mean and we head in this direction, this distance is one standard deviation, sigma. And then in this direction, the exact same amount of distance, we have one standard deviation. So one standard deviation to the left, one standard deviation to the right. And what the empirical rule tells us is that 68% of all the area under the curve is going to be in this interval. So between these two outer lines here, between one standard deviation to the left and one standard deviation to the right of the mean, we're going to capture 68% of the area. If we go 2 standard deviations away from the mean, so we could think about this here as 2 standard deviations away from the mean on the right, and then over here, 2 standard deviations away from the mean on the left, that the area under the curve between this line on the left and this line on the right is always going to be 95% of all of the area under the curve. So almost all of it, everything but 5% of the total area. And then within 3 standard deviations of the mean, so again, if I go from the mean over here to the right, a distance of 3 standard deviations, and then over here to the left, a distance of 3 standard deviations, that the area under the curve between this line on the left and this line on the right is going to be 99.7% of the area. Now, the empirical rule is really powerful because now that we understand that the area under the curve is 100%, and the empirical rule lets us divide the area into different percentages based on standard deviation, we can say things like this. Well, if 99.7% of the area is between 3 standard deviations to the left and right of the mean, then that must mean that the little tails here at the end, outside of 3 standard deviations, together is only going to make up 0.3% of the area, because we can take 100% minus 99.7%, and the result there is 0.3%. But we have the 2 tails, the one on the left and the one on the right, and they're equally divided because remember we have an equal amount of area to the left and right of the mean and median, and this distribution is symmetrical. Normal distributions are always symmetrical, which means that the area in this little tail on the right here is exactly half of 0.3, or 0.15% of the area. And then same thing over here on the left-hand side, this is 0.15% of the area. Since we know that 1 standard deviation away from the mean on either side captures 68% of the area, if we just wanted to know this area right here of this region, that would be half of 68%, or 34%. Or if we wanted, for example, to know the area under the curve that's outside of 1 standard deviation, but within 2 standard deviations, that would be the area of this region here plus the area of this region here. Well, how would we find that? Well, we know that within 2 standard deviations, we have 95%. So we could say 95%. And then within 1 standard deviation, we have 68%. So we could say minus 68. And the result there is 27%. 95 minus 68 is 27. Then if I wanted, for example, just this area here, that would be exactly half of 27%, because the 27% again is this region plus this region here. But if I just want one side, I would take half of that. 27 divided by 2 is 13.5. So I know that this area here is 13.5%. So we can do all kinds of area calculations like that using the fact that the area under the curve is 100% and what we know about the area within each standard deviation from the empirical rule. So just keep that in mind because we'll use this over and over again to calculate specific portions of area under a normal curve. When we talk about a normal curve, we can also talk about percentile. And the concept of percentile is really closely related to the z-score, which we're going to talk about in a second. When we talk about percentile, something like the 95th percentile would be the spot under the normal curve where 95% of the area lies below that value. So if we think about this for a second, here at the mean, we know that 50% of the area lies below or to the left of the mean. We know that this area right here is 34% because we calculated it right here. So 50 plus 34 gets us up to 84. We know that this area here is 13.5, so 13.5 plus 84 would be 97.5. So right here, 2 standard deviations above the mean, we're in the 97.5 percentile, which means that the 95th percentile might be something like right here. So that might be the 95th percentile, because that is the point under the curve where 95% of the area is below this line. So with that in mind, let's talk about the z-score, because the z-score will give us the value in terms of standard deviations for any percentile that we want. So if we know that we're in the 95th percentile, we know that we're right at that point that's just above 95% of the data under the curve. And we can see right here that that's a little bit less than 2 standard deviations above the mean. What we'd like to be able to do is have a value, and this is going to be the z-score, that consistently gives us that spot, that 95th percentile, that spot where 95% of the data is below it, because that way we can always refer to that particular z-score, and we'll know that that is the point. Maybe it's 1.7 or so standard deviations, because we can see where this is, that gets us to just above 95% of the data. So the formula that we use for the z-score is z is equal to x minus mu divided by sigma, where mu is the mean, so right here at the center. X is the particular point that we're interested in, so x might be this point right here. And so when we take x minus mu, the mean, we're really getting this distance right here, the distance between the mean and the point that we're interested in. And then we divide that by 1 standard deviation, which means that we're going to get a value, maybe like for this spot right here, something like 1.7, that will tell us that we're 1.7 standard deviations above the mean. So the z-score for a data point, x, is just how far that data point is from the mean in terms of standard deviations. So let's say that we know for some normal distribution curve that we have, let's say we know that the mean is maybe 16 and the standard deviation is 1. So a standard deviation of 1. And then we have the value 17.5. So let's say 17.5. And so what we do is we take 17.5, subtract the mean. So again, we're finding some distance here. We get 1.5. So we get 1.5 divided by 1, which is 1 standard deviation. And this isn't just 1 because we're talking about 1 standard deviation. We just assigned the standard deviation to have a value of 1. It could have been 0.8 or it could have been 2.7 or whatever. But we just said 1 standard deviation is 1. And so then the value we get here is 1.5. So 1.5 is our z-score. Then what we do with our z-score is we go to what's called a z-table. And this is going to look overwhelming at first, but you will use it a lot, so we want to get used to it. So what we're going to do is we're going to come here to our z-table, and we have this z-score of 1.5. So what we want to do is we want to go down the left-hand side here until we get to 1.5. So if we go all the way down, we get to here, 1.5. And then in our case, we just have 1.50. We don't have a decimal place in the hundredths, so it's just a 0. If we had, for example, 1.53, we would come across to the 0.03, and we'd look here, and then we'd come to the intersection. But in our case, we have 1.50, so we're looking in this first column here. So when we find the intersection of those two, we can see that it's this value right here, 0.9332. So what that tells us is that on a normal distribution here, if our mean is 16 and 1 standard deviation is 1, so this distance right here is a distance of 1, that's 1 standard deviation. And then we're up here at 17.5, so maybe we're right here at 17.5. then the z-score of 1.5 tells us we are 1.5 standard deviations above the mean. The fact that this value is positive tells us that we are above the mean as opposed to below it. So the z-score says you're 1.5 standard deviations above the mean. But in a normally distributed curve, 1.5 standard deviations above the mean is always going to have the same amount of area below that spot. In fact, according to our z-table, it's going to have 93.32% of the area below it. In other words, a z-score of 1.5 tells us that we are in the 93.32 percentile, or approximately the 93rd percentile, or that 93% of the area is below that spot. So it would tell us that if we come here to 1.5 standard deviations where our 17.5 is, that all of the area under the curve below that 1.5 standard deviations, so all of this, is 93.32% of the total area under the curve. And keep in mind here that because the full area under the curve is 100%, if I want to find the area above 1.5 standard deviations above the mean, so everything here that's not shaded in green, I would just take 1 minus 0.9332, because 1 represents all of the area under the curve, and I know that everything to the left of 1.5 standard deviations above the mean is 93% of the area, or 0.9332, and I would just get here 0.0668, and that tells me that only 6.68% of the area is to the right here, or above 1.5 standard deviations above the mean. So I hope you're starting to see how this z-table standardizes the area under a normal distribution. Now remember we said before that a positive z-score indicated a value that was above the mean or to the right of the mean. Well, if we have a negative z-score, it indicates a value below or to the left of the mean. And that's because, again, going back to our example here, remember we said that the mean was 16 and we looked up a value of 17.5. So when we took 17.5 minus 16, we got a positive 1.5. But if we were somewhere down here, let's say at 14, below the mean of 16, then our z-score here would be 14 minus 16 over 1 is equal to a negative 2 in the numerator divided by 1, or just a negative 2.0. So notice how, because we found a value below the mean, we get a negative z-score. When you have a negative z-score, you want to look that up in the z-table with negative z-scores. Notice here we had positive z-scores on the left side, but here we have negative z-scores on the left side. So a z-score of negative 2, again, we come down here on the left to this point right here, negative 2.0. And again, because we don't have an additional decimal place, this is negative 2.00. We're just looking up this column right here. And the intersection of those two is this value right here, 0.0228. And what we need to keep in mind here is that z-tables always give you the area to the left of this particular value. So 0.0228, well, if this is our value here, 14, that 0.0228 is this area right here to the left of this 14. And we can see that that's 2.28%, or 0.0228. So we would say that 14 in this imaginary data set that we made up is in the 2.28 percentile, or if we rounded it, in approximately the second or third percentile, as opposed to, on the other end, the 93rd percentile, which we calculated for 17.5. And again, if we wanted to find the area above this value of 14, we would just take 1 minus this 0.0228. The last thing, though, that I want to mention is that we've done 2 examples now where we found a z-score. So we got a z-score of 1.50 and a z-score of negative 2.00, and we looked those up in our z-table by looking down the left-hand side here and then across to the appropriate column, finding the intersection of those, and getting a value from the body of the table. But we can also use z-scores in the opposite way. So for example, if I'm taking a test, maybe I'm taking the LSAT to try to get into law school, and I want my score to be in the top 5% of all test takers. If I know that test scores are normally distributed, and in fact tests like that are usually scored in such a way that they do follow a normal distribution, if I want to be in the top 5% of all test takers, that means that I want to be above the 95th percentile. So this time I could go to my z-table. Again, I want to be one of the top scores, which means I'm going to be on the right side of my normal distribution. I'm going to be up here in the high percentiles in the right tail. So if I look at the 95th percentile and I'm looking for 0.95, I can see that I find it right here. It's going to be somewhere right in here. Because what I notice is that when I have a z-score of 1.64, so this first value right here, 1.64, I would be in the 94.95 percentile, or just under 95%. But if I truly want to be in the top 5%, I truly want to be inside that top 5%, then 94.95 doesn't quite cut it, which means that I want this value right here, which gives me 0.9505. I am inside that top 5%. That's a z-score of 1.65, which means I could then plug into my z-score formula. So I know I need a z-score of 1.65. So if I plug into the formula, I could say 1.65 is equal to, and then if I just know the mean and the standard deviation of everyone who takes the LSAT, and I could maybe look up that data for a previous year, I would be able to plug in for both of those values. So then the only missing value, the only unknown, would be my actual score right here. So if I just plug in for mean and standard deviation, I would then be able to solve this equation for x, and I would know exactly what score I have to get in order to be in the 95th percentile, in order to be better than 95% of test takers. And so that's an example of how we would use the z-table in the opposite way, or working backwards, where we find a percentile or a value that's in the body of the table, and then look to find the associated z-score by following this across to the beginning of the row or to the top of the column. Statistics and probability go hand in hand because statistics is all about data and analyzing data. Probability is going to allow us to determine how reliable our statistical results actually are. So we really like to study them together. And in this video, we're going to start transitioning to probability, and we're going to start with the simplest kind of probability. So probability is basically just the likelihood of whether or not something will occur. So if I'm trying to figure out the probability that I get heads when I flip a coin, I'm really asking, how likely is it that I'll get heads when I flip a coin? Now, the probability of any event occurring, we can always express as either a fraction, a decimal, or a percent. But the value that we get will always be somewhere between 0 and 1, including 0 and 1. So in interval notation, we would express it this way. We would say probability is always going to exist on the interval 0 to 1, and these closed brackets here mean that the endpoints 0 and 1 are included. So here's what we mean by that. If we sketch out a number line, so let's say we have on our number line here 0 and 1, right in the middle is going to be 0.5. If we're thinking about our number line in terms of decimals, we could also call this 1/2, and we could call it 50%. If we're thinking about our number line in terms of percent, we would have 0% over here, we would have 100% over here. In fraction form, this would still just be 1, and this would be 0. So basically, we're just showing this number line in different ways here in decimal form, here in fraction form, and here in percentage form. So when we say the probability of any one event can take on the value 0 all the way up to 1 and all the values in between, let's think about what we mean. If we have a probability of 1 or 100%, that means our event is guaranteed to happen. There's a 100% chance that the event will happen. So if I asked you, what is the probability that I get either heads or tails when I flip a coin? Well, the probability of that would be 1, because there's no other value I can get if I flip a coin. It's either going to land on heads or it's going to land on tails. It's guaranteed to land on one of those two options. So the probability that we get heads or tails would be 1 or 100%. That event is guaranteed. If I say the probability of an event is 0, that means it's impossible or it's guaranteed not to happen. Maybe something like, if I roll a 6-sided dice and the faces are 1, 2, 3, 4, 5, and 6, what's the probability that I roll a 9? Well, none of the sides of the dice are 9, so it would be impossible to roll a 9, so the probability of that happening would be 0. If you see a probability of 0.5 or 1/2 or 50%, that means that an event is just as likely to happen as it is not likely to happen. So we could maybe say something like, same chance to happen or not happen. That would be something like flipping a coin. I have an equal chance of getting heads or tails. So if I asked you, what's the chance that I get heads when I flip a coin one time? It would be a 50% chance because I'm equally likely to get heads or not heads. I have an equal chance that heads happens versus doesn't happen, and we'll look more at that example in a little bit. So then any probability between 0 and 0.5, these could be values like 0.4, or maybe 1/5, or something like 25%. All of these values are somewhere between 0 and 0.5 or 1/2 or 50%, means I have a less than 50% chance that the event happens, which means it's more likely that the event doesn't happen than it is that it does happen. But if I have a probability value between 0.5 and 1, so these could be values like, let's say, 0.6 in decimal form, or maybe something like 7/8 in fraction form, or maybe something like 75% in percentage form, any value that's larger than 0.5 or 1/2 or 50% and less than 100% means it's more likely that the event does happen than that it doesn't. So we could say a greater chance that the event does happen versus a greater chance that the event doesn't happen. So hopefully that gives you an overview of all of the possible probabilities, from the probability of 0, where something is impossible, all the way up to the probability of 1, where something is guaranteed, and then everything in between. Let's go back for a second to our coin flipping example and build a formula for simple probability. So we said before we were interested in the probability of getting heads when we flip a coin. When we express probability, it looks something like this. So we do a capital P, and then in parentheses here, we put whatever event it is that we're interested in. So we could maybe express the probability of getting heads as P of H, the probability of getting heads. But if we wanted to just generalize this as a formula, we would say the probability of just some event. And the formula that we use, and this is somewhat intuitive, is just the outcomes that meet our criteria divided by all possible outcomes. So let's unpack this formula a little bit when it comes to finding the probability that we get heads when we flip a coin. So a lot of times it's easier to start with the denominator, all possible outcomes. So what are all of the possible outcomes that can result when we flip a coin? Well, if we flip the coin, it lands on the ground, we can get heads. It could land head side up, or we could flip it, it could land on the ground, and we could get tails. The tail side would be up. Those are the only two possibilities. We're going to assume that the coin can't land on its edge, that it's only going to land on one of the faces. So there's only two possible outcomes. It either lands on heads or it lands on tails. There's no other possibility. So all the possible outcomes when we flip a coin will be heads or tails. That's two possible outcomes, which means we could go ahead and put a 2 in our denominator. Now, outcomes that meet our criteria. Well, we want the coin to land on heads. We want coins to be head side up. So the outcomes that meet the criteria that we've specified would just be the one outcome, because you can think of tails as a failure. That's something we don't want. Heads would be a success. That's something we do want. So there's only one outcome that meets the criteria that we're interested in. It's when the coin lands head side up. So since there's only one outcome that meets our criteria, we put a 1 in the numerator. And now we've just calculated the probability that we get heads when we flip a coin. There was one outcome that met our criteria over two possible outcomes, so the probability of this happening is 1/2, or you could think about that as 0.5 or as 50%. If we go back to our chart here, and remember we talked about this when we built the chart, that means that there's the same chance of us getting heads as not getting heads because we're right at the 50% mark. Now, what about a different example? Let's take a deck of cards, for instance. So a deck of playing cards. Remember that there are 52 cards in a deck. So maybe we want to say, what is the probability that we pull a 7 when we pull one card from a deck of playing cards? Well, let's think about it. So again, let's start with our denominator first, because I think that's easier. How many possible outcomes do we have? Well, if we have a deck of 52 playing cards and we just put them all on the table and we pull one, there are 52 different choices that we have. We could pull any of the 52 cards off the table, which means there are 52 possible outcomes. So we could put 52 in our denominator. And then how many outcomes do we have that meet our criteria? Well, remember that there are 4 of each rank in a deck of playing cards. So there are 4 2s, 4 3s, 4 4s, 4 5s, 4 6s, 4 7s, 4 8s, all the way up to 4 jacks, 4 queens, 4 kings, 4 aces. So there's 4 of every number, 4 of every rank, which means that there are 4 7s. We're only interested in pulling a 7, and there are 4 cards that are 7s in the deck. So there are 4 outcomes we could have that would meet our criteria. So we would go ahead and call this 4 over 52. Now, whenever we calculate a probability in fraction form, we always want to make sure we reduce that fraction to its lowest terms. 4 over 52 is the same as 1 over 13. So we would say the probability of pulling a 7 is 1 over 13. If we want to convert this fraction to a decimal or a percent, we could take 1 divided by 13, and if we round to the nearest hundredth, we get about 0.08 or 8%, which means there's about an 8% chance that we pull a 7 when we draw one card randomly from a deck of cards. So 8%, 0.08, 1 over 13, that's going to be down somewhere around here on our chart, which tells us that it's more likely that this event doesn't happen than that it does, which makes sense because 8% is a pretty small chance. We have a pretty small chance of pulling a 7 versus any other card in the deck. Now, one thing we want to say about our probability formula before we go on is that this denominator of all possible outcomes really should say all possible equally likely outcomes. When we're calculating simple probability like this and we're using this formula, we are relying on the fact that all possible outcomes means all possible equally likely outcomes. So for example, when we flipped the coin, we're assuming that it's a fair coin and that we have an equally likely chance of getting heads as getting tails. When we drew a card from the deck, we were assuming that it was a fair deck with all 52 cards that were supposed to be there, and we have an equally likely chance of pulling any one card out of the deck. If our outcomes are not equally likely, for example, if the coin is a weighted coin where it's weighted to land on one side more often than the other, or something about our deck isn't fair, or we're rolling a dice and the dice is weighted to land on one or more sides more often than certain other sides, any kind of scenario where our outcomes aren't equally likely, then we can't use this simple probability formula. We have to use a different formula. This one is just when all possible outcomes are equally likely. So that's the one thing we want to say. And then the second thing we want to say is we just want to define all possible outcomes as the sample space of our probability. So we call this the sample space by definition. And it just means all of the outcomes that could possibly occur. So the sample space of flipping a coin is getting either heads or tails. The sample space of pulling one card from a deck of cards is all 52 options that are in that fair deck. Now let's talk through a bit of a tricky question when it comes to simple probability. Let's say that I have a fair coin, and let's pretend that I flip that coin 3 times in a row, and each time I get heads. So I flipped the coin once, I got heads. I flipped the coin again, I got heads. I flipped the coin a 3rd time, I got heads again. So I got heads all 3 times. And now I want to ask, what's the probability of getting heads? Well, we might look at that example and think the probability of us getting heads was 3 out of 3 because we flipped the coin 3 times and we got heads 3 times. So the probability is 3 out of 3 or 1 or 100%. So we would maybe say the probability of getting heads is 100%. But of course, intuitively, we know that that's not true. We have an equally likely chance of getting heads versus getting tails on any one flip. But this calculation would seem to imply that we're guaranteed to get heads every time we flip the coin. But that's not true. So what's going on here? Well, what's happening is we're creating here what's called an experimental probability. So flipping a coin 1 time is called an experiment. Drawing a card from a deck of cards 1 time is called an experiment. Rolling a dice 1 time is an experiment. So each time you perform an action, that is one experiment. And when we flip a coin 3 times in a row, we're performing 3 experiments on that coin. If we perform the same experiment over and over and over and over and over again, what we'll develop is an experimental probability. And of course, that experimental probability can change depending on our results. So let's say I flipped the coin 3 times and I got heads each time. I would say the probability of getting heads is 100%. But let's say instead that I had flipped the coin maybe 5 times, so probability of getting heads, I flipped the coin 5 times and I got heads 4 times. I might calculate that the probability of getting heads is 4 over 5, which would be 0.8 or 80%. So I'm getting a different probability of getting heads each time I run an experiment. This is different than what's called the theoretical probability. The theoretical probability is what we tend to think of when we think about probability, because it's the likelihood that something will occur if you run, really, an infinite number of experiments. You almost want to think about it as true probability or real or actual probability, because we all know that the probability of getting heads when I flip a fair coin is 50%. That means my theoretical probability of getting heads is going to be 50%. But I can run a bunch of experiments, and depending on how many experiments I run and what my results are of each experiment, I can get a different experimental probability. What we know is that the more experiments we run, the closer the experimental probability will get to the theoretical probability. And this is often what we call the law of large numbers. It tells us that the more experiments we run, the closer our experimental probability will get to our theoretical probability. In this course, we're going to be focusing mainly on theoretical probability because that's the probability that we're really interested in. We don't really care so much right now that if we run a different number of experiments, we're going to get different results for the probability of an event happening. We want to know the theoretical probability of that event. We want to know that the probability of getting heads when we flip a coin is 50%. We're interested in that expected probability, that theoretical probability. So that's the one that we're going to be focusing on. In this video, we're focusing on the addition rule, which is the rule that we use to find the probability that one event happens or that another event happens. For example, if I roll a pair of 6-sided dice, what's the probability that I get at least one 1 or an even sum when we add the dice faces together? That's an example where we're asking the probability that one event or the other event occurs when I roll a pair of dice. Sometimes this kind of probability is disguised as at least probability, because we could ask something like, what is the probability that we get at least one heads when we flip a coin 2 times? Well, really, at least one heads is the probability that we get either one head or 2 heads. So it's still the probability of one event or the other occurring, and in that case, we would use the addition rule. In fact, let's go ahead and take a look at that example, the probability of getting at least one heads. First of all, if we're flipping a coin 2 times, we can think about all of the possible outcomes. So if we flip a coin 2 times in a row, we can either get heads heads, we can get heads tails, we can get tails heads, or we can get tails tails. So there are only 4 possibilities when we flip a coin 2 times. Now, sometimes we might be tempted to do something like this. We're looking for the probability that we get at least one heads, so we might say, okay, well, I have to get either heads on the first flip, or I have to get heads on the second flip. One of those things has to occur if I'm going to get at least one heads. So I could say, what's the probability that I get heads on the first flip? I look at all my options here and I say, well, in both of these examples, I get heads on the first flip. So the probability of heads on the first flip, which maybe we'll call the probability of H sub 1, meaning heads on the first flip, is going to be 2 out of 4, or 1/2. And then I could say, well, what's the probability that I get heads on the second flip? Well, this outcome and this outcome both meet that criteria, so I could say the probability that I get heads on the second flip is, again, 2 out of 4, or 1/2. And then I might say something like, the probability that one of these occurs, probability that I either get heads on the first flip or heads on the second flip, is 1/2 plus 1/2 equals 1, or 100%. But I know that's not true. Saying the probability that I get heads on the first flip or heads on the second flip, or at least one heads, is not 100% because, of course, I know that I could get tails tails. I could get tails on both flips. So if I can get tails on both flips, of course, that means that the probability of getting at least one heads can't possibly be 100%. So where did we go wrong here? Well, the problem is that we've double counted an option. We have an overlapping value in our probabilities that we're counting in both, and we can't do that. For the probability of getting heads on the first flip, we counted heads heads and heads tails. And then for the probability of getting heads on the second flip, we counted heads heads again and tails heads. The fact that we're double counting heads heads is what's throwing us off. One way that we can illustrate this overlap is with a Venn diagram. So we could draw a Venn diagram like this one, and we could say that one circle represents getting heads on the first flip, and that the other circle represents getting heads on the second flip. Now, with Venn diagrams, I always like to start with the overlapping area between the circles, the area in the middle, which is all of the outcomes that meet both criteria. So for the number in the middle here, we're looking for all outcomes where we get heads on the first flip and we get heads on the second flip. Well, we know that that occurs here at heads heads, so there's one outcome where that occurs, so we could put a 1 in the middle. Then over here on the left, we're looking for all of the outcomes where we get a heads on the first flip, but not heads on the second flip. Well, that happens here. We got heads on the first flip, but not on the second flip. There's one outcome, so we put a 1 over there. Over here, we're saying how many outcomes occur where we get heads on the second flip, but not heads on the first flip. There's one of those, so we put a 1 here. And then outside both circles, how many outcomes are possible where we don't get heads on the first flip or on the second flip? In other words, we don't get heads either time. Well, that's this option here, tails, tails, so there's a 1 out here as well. In the Venn diagram, then, we're illustrating the overlapping value with whatever is in this overlapping area of the Venn diagram. So whatever's in the middle are the number of overlapping outcomes. What we want to do is subtract that out. So if we go back to this idea of the probability of getting heads on the first flip or heads on the second flip, which is really the probability of getting at least 1 heads, we could write it out this way instead. So we could say the probability of getting heads on the first flip, we know that there are 2 outcomes that meet that criteria. We saw those up here with the yellow check marks, or we could look in our heads on the first flip circle and see that there are 2 outcomes inside that circle. So there are 2 outcomes that meet that criteria. Or the probability that we get heads on the second flip, we know that there are 2 outcomes that meet that criteria. We saw those with the blue check marks here, or we can see that there are 2 outcomes inside the heads on the second flip circle. So again, we add in those outcomes. But then here's how we correct. We subtract out the overlapping value. So there's one outcome that is overlapping between those 2. This one that we double counted here with both check marks. So we have to subtract out that. There are 4 possible outcomes total. So we subtract out 1, the overlapping value, divided by the total number of possible outcomes. So we subtract out 1/4. When we do that, we get 2 plus 2 is 4, minus 1 is 3. We get 3/4 or 75%, meaning a 75% probability that we get at least 1 heads. And we know that that's correct because if we look here at our 4 possible outcomes, 3 of those will satisfy our criteria of getting at least 1 heads. We get at least 1 heads in this outcome, at least 1 heads in this outcome, and at least 1 heads in this outcome. But we do not get at least 1 heads when we get tails, tails. So 3 out of our 4 possible outcomes satisfy the at least 1 heads, so the probability is 75%. What we need to realize is that in order to get there, we had to subtract out this overlapping value. And that's really where we get to the addition rule. So the addition rule tells us that the probability of A or B happening, so event A happening or event B happening, is equal to the probability that event A happens plus the probability that event B happens minus the probability that A and B both happen. So this comes right from the formula we already built without knowing the actual formula, which was, we said here, this is the probability of event A happening, getting heads on the first flip. Add to that the probability of event B happening, that we get heads on the second flip, but then subtract out the overlapping value where we get heads on both flips. We're double counting it, so we want to make sure we subtract it out so that we don't get that double counting. If we generalize that into a formula, what we get is the addition rule. This is the addition rule here, also called the sum rule, and this is the formula that we use. Now, it's interesting to say that if the events are mutually exclusive, which means that there is no overlapping value between the events, if there's no overlapping value, then the probability that A and B both happen is 0. So for mutually exclusive events, which we also call, by the way, disjoint events, then P of A and B equals 0. And so if we plug that into our addition rule, this term here becomes 0, and we say the probability of A or B is simply the probability of A plus the probability of B, because we would just have minus 0 here at the end, and that would have no effect. And this should make sense to us because if we calculate, for example, rolling a 6-sided die and we want to know the probability of rolling a 2 or a 3, well, if this is a regular 6-sided die, all 6 faces are equally likely to appear, so the probability of rolling any value on that die is 1/6. So the probability that we roll a 2 or a 3 would be the probability of rolling a 2, so the probability of rolling a 2, plus the probability of rolling a 3. The probability of rolling a 2 is 1/6. The probability of rolling a 3 is also 1/6. So the probability then is 2/6 or 1/3. In an example like that one, the probability of rolling a 2 and a 3 is 0 because we're talking about rolling a dice only one time. And if I roll the die once, it's impossible for me to get a 2 and a 3 on that one roll. They can't happen at the same time. I can only get one result at a time. So the probability of getting a 2 and a 3 on one roll is going to be 0, which is why those are mutually exclusive or disjoint events. We don't have this probability of A and B term. It disappears as 0. And then we can simply add the probability of each of those events together without having to subtract out anything for overlapping events. But when we do have overlapping events, like we did in this first example, we have to pay attention to this probability of A and B term and make sure to subtract out those overlapping outcomes. Now let's go ahead and move this portion down because I want to look at another version of the addition rule. So this exact same addition rule can also be written as the probability of A and then this symbol B is equal to the probability of A plus the probability of B minus the probability of A, this symbol, and then B. So what are these? Well, this symbol that looks like a U is called union. And it basically means or, right? We said the probability of A or B. Well, that's the same thing as A union B. It means that either A happens or that B happens. This symbol is called intersection, and it basically means and, the probability that A and B happen, or the probability of A intersection B. You'll very often see the addition rule written this way with the union and intersection notation instead of the or and notation. They mean exactly the same thing. It's just two different ways of expressing the same rule. We can also calculate this kind of probability where we use the addition rule and we look at the probability that one event or the other happens when we have a two-way data table. So in this table, we have males and females across the top, and then their favorite sport or their preferred sport down the left-hand side. So as an example, there are 22 males who prefer football. There are 8 females who prefer basketball. You can see here there are 60 total males in the survey, 40 total females in the survey for 100 people total, and there are 41 people total who prefer some sport other than football or basketball. So their favorite sport is something other than football or basketball. So we've got a lot of data in this chart. And we can do lots of addition rule probability with a chart like this one. So for example, we could ask something maybe like, what is the probability that someone in this survey is male or prefers football? So their favorite sport is football. That's the probability we want to figure out. Well, we could break this down. So we could basically say that event A is the person being male. Event B is the person preferring football. Then if we're using our addition rule formula, we know that we're going to need to find the probability of A and the probability of B, P of A and P of B. So what are those? Well, the probability that event A occurs, the probability that the person is male, let's see. Well, if we sum up our entire male column, we have 60 males total in the survey, and there are 100 people in the survey overall. So if 60 of our 100 people are male, then the probability that somebody in the survey is male is going to be 60 over 100, or if I reduce this fraction to lowest terms, 3/5. So there's a 3 out of 5 chance that somebody in our survey is male. What's the probability that somebody in our survey prefers football? Football is their favorite sport. Well, I can again look at the total, and I can say there are 38 people who prefer football over any other sport, and 100 people total in our survey. So the probability that somebody's favorite sport is football is 38 over 100, or if I reduce that to lowest terms, 19 over 50. But remember, according to the addition rule here, I have to subtract out the intersection of A and B, the probability that A and B both occur at the same time. So if I say A intersection B equals male intersection football, well, where in my table does male and football occur at the same time? That's here in this top left cell where I have 22. These are the number of people that are both male and prefer football. So this is the intersection of male and football. So I want to say the probability that A and B both occur, so A intersection B, will be equal to 22 of the people in our survey divided by all of the people in our survey, 100. And if I reduce that to lowest terms, I get 11 over 50. Then I can use the addition rule and say the probability that the person is male, event A, or prefers football, event B, so the probability of A union B, is equal to the probability that the person is male, which we said was 3/5, plus the probability that the person prefers football, which was 19 over 50, minus the probability that both occur, they are male and prefer football, which is 11 over 50. Now, if I want to find a common denominator, I want to multiply this first fraction by 10 over 10 so that I get 50 in the denominator. So 3 times 10 is 30, 5 times 10 is 50. So now I have 30 over 50 plus 19 over 50 minus 11 over 50. So I did that so I would have a common denominator, and now I can combine all three fractions. So 30 plus 19 is 49. 49 minus 11 is 38. So my probability is 38 over 50, or if I reduce that to lowest terms, 19 over 25. If I convert that to a decimal, I get 0.76 or 76%. So there's a 76% chance that someone in my study is either male or prefers football. So 76 out of my 100 total participants are either going to be male or prefer football. They're going to meet one of those criteria. Now, we did a lot of math here in order to apply the addition rule. But the cool thing is that we can actually just see this visually in our table. So here's what I mean. The probability that the person is male is given here in this column. We know there are 60 people who are male in our survey. The probability that someone prefers football, we know is 38 out of 100. 38 of our participants prefer football. And we know that the overlap of male and football is given here as 22. So really all we need to do is grab those three numbers and say that the probability of male or football is equal to the probability that they are male plus the probability that they prefer football minus the overlapping portion where they are male and prefer football, and then we just divide that by the total number of participants, 100, which is really all we did here. And we can see that we get that same value. 60 plus 38 is 98. 98 minus 22 is 76. So we get 76 over 100, or 76%. Alternatively, although this is really doing the same thing, we could take the entire male column and the entire football row, but only include the male and football intersection once. So for example, if we only took here all of the males, and then we want to make sure we don't double count the 22, so we won't box that again, but we also need to include everyone who likes football, so we're missing this box here, we need to grab that as well. In that case, we're just saying that these are all of the people we want, we just want to make sure we don't double count 22. So if we add all of those up, 22 plus 13 plus 25 plus 16, we get 22 plus 13 is 35, 35 plus 25 is 60, 60 plus 16 is 76, so we get 76 people out of the total of 100 participants, or again, 76%. So I'm just showing you all of these different ways to reinforce the idea that all we're really looking at is all of the people who meet one criteria or the other, and making sure not to double count the people who meet both criteria. So far in this course, we've been talking about the probability of independent events. I want to take the opportunity in this video to look at the difference between independent and dependent events and how we calculate probability for each of those kinds of events. So let's start with a quick review of independent events, which are simply events that don't affect one another. So for example, flipping a coin. Every time I flip a coin, you can think about that as one trial or one experiment. Independent events are events where one trial does not affect the result of the next trial, or the result of one experiment is not affected by the result of the previous experiment. Flipping a coin is a great example of that because if I flip a coin one time, trial number 1 says that I can either get on that trial heads or tails. I have two options. Now let's say I want to flip the coin again. I'll have here trial number 2. So let's say in the first trial I got heads. I got heads, I pick up the coin, and I flip it again for trial number 2. Well, in that case, I can either get heads or I can get tails. If I got tails on the first flip, and then I pick up the coin and I flip it again, I can either get heads or tails. And my options, my outcomes, are always going to be the same no matter how many trials I run, even if I flip the coin 20 times. Every single time I flip the coin, I can either get heads or tails. Each flip is unaffected by any of the flips before it. So when I flip the coin for trial number 2, I flip the coin the second time, it doesn't matter at all whether I got heads the first time or tails the first time. I've still got a fair flip and an equal chance of getting heads or tails. In other words, trial number 2 is completely unaffected by the result of trial number 1. If I got heads on the first flip, it doesn't make it more likely that I'm going to get heads on the second flip, and it doesn't make it more likely that I'm going to get tails on the second flip. If I got tails on the first flip, I'm not more likely to get heads on the second flip or more likely to get tails on the second flip. I have an equal chance of getting heads or tails on the second flip, regardless of whether I got heads or tails on the first flip. So these are independent events because each trial doesn't have any effect whatsoever on any of the other trials. We see this illustrated mathematically when we use the multiplication rule for independent events. The multiplication rule lets us find the probability of getting a specific outcome on each of our trials or experiments. For example, if we wanted to say what's the probability that we get heads on the first flip and then heads on the second flip, the multiplication rule would allow us to do that because we're saying what's the probability that we get a specific outcome on trial number 1, and then what's the probability that we get a specific outcome on trial number 2, and what's the probability of those two things happening back to back. Well, remember, because the events are independent, they don't have any effect on each other. So the probability of event A happening and event B happening on two separate trials, so event A occurs on trial number 1, event B occurs on trial number 2, is simply the probability of event A multiplied by the probability of event B. In other words, if I flip a coin 2 times and I want to know what's the probability that I get tails and then tails. Well, event A is tails on the first flip. Event B is tails on the second flip. The probability of event A is what's the probability that we get tails on the first flip? Well, we know that that's 1/2 because I have a 50% chance of getting either heads or tails on a single flip. What's the probability of event B? What's the probability that I get tails on the second flip? Well, remember, these are independent events. We use the multiplication rule with independent events. So I don't have to think about the first flip at all. Trial number 2 basically is I'm just flipping a coin. We can forget that trial number 1 ever even happened. So I'm just flipping a coin. What's the probability that I get tails? Well, it's still 1/2. So then the probability of getting tails and tails is going to be equal to 1/2 multiplied by 1/2 or 1/4 or a 25% chance. And that should make sense to us because we looked at the probability of getting 2 tails when we flip a coin 2 times. Well, when we flip a coin 2 times, what are all of our possible outcomes? We can get heads and then heads. We can get heads and then tails. We can get tails and then heads, or we can get tails and then tails. These are the only 4 possible outcomes that we can get when we flip a coin 2 times. And we wanted to know what's the probability of getting tails and tails? Well, there's 4 possible outcomes and only 1 that meets the criteria we're interested in. So the probability is 1 out of 4 or 25%. That's all the multiplication rule is telling us. It's giving us the probability that multiple independent events happen on consecutive trials. The other thing I want to say about independent events is that events are independent not because there's a 50-50 chance of them occurring. So we use the example here of flipping a coin. And when you flip a coin, you have an equal chance of getting heads or tails, a 50% chance of getting heads, a 50% chance of getting tails. Flipping a coin is not an independent event simply because these probabilities are equal. Flipping a coin will be an independent event because I can flip a coin once and then flip a coin again, and those 2 flips don't have any effect on each other. Another example might be a basketball player making free throws. So a professional basketball player might have an 80% chance of making any given free throw. The reason we know that is because this basketball player has taken, 20,000 free throw shots in his professional career. And over the course of that time, we've seen that he makes about 80% of those. So we say that his free throw percentage is 80%. We know that he makes about 80% of his free throws. So if that's the case, what is the probability that he makes 2 free throws in a row? We're going to assume those are independent events. So making the first free throw is going to have no effect on whether or not he makes the second free throw, and vice versa. Each free throw is an independent event. So if we go back to our multiplication rule, since these events are independent, and we say the probability of A and B is going to be equal to the probability of A multiplied by the probability of B, we're saying that event A is he makes the first free throw. Event B is he makes the second free throw. And then we want to say the probability of event A is 80%. He's an 80% free throw shooter. So we can say that the probability of event A is 0.8. The probability of event B, what's the chance that he makes free throw number 2? Well, he's an 80% free throw shooter. So he's going to have an 80% chance on every single shot. So again, it's 0.8. We could also express these as 8 out of 10 or 80%. But either way, then we say the probability of a make and a make is equal to 0.8 times 0.8, which is going to be equal to 0.64 or 64%. So he has a 64% chance to make 2 free throws in a row. Now, sometimes that feels a little confusing when we think about a free throw shooter having an 80% free throw make percentage, why would the probability that he makes 2 in a row be less than 80%? Why would it be 64% and not always just 80%? Well, we can think about it this way, sort of by taking it to an extreme. What's the probability of him making 1,000,000 free throws in a row? Even though he's an 80% free throw shooter, making 1,000,000 free throws in a row is extremely unlikely. He's bound to miss one of those in there somewhere. I mean, he only makes 8 out of 10, so 2 out of every 10 shots he makes, he misses, historically. So if he's going to take 1,000,000 shots, he's going to miss some somewhere. So the more makes we want him to have in a row, the smaller percentage chance he has of doing it. In other words, he's less likely to make 1,000,000 shots in a row than he is to make 1,000 shots in a row. He's less likely to make 1,000 shots in a row than he is to make 10 shots in a row. The fewer number of shots we have, the more likely he is to make all of them. So even though he makes 80% of all of his free throws, asking him to make 2 in a row, he only has a 64% chance of doing that. And notice here that the probability of a success on each event was 80%, versus the probability here, flipping a coin, we called tails sort of a success, if you will, and the probability of that success was 50%. The probability of getting tails was 50%. The probability of making a free throw was 80%. So it's not the percentage that makes these independent events. It's the fact that free throw number 1 has no effect on free throw number 2 and vice versa, and the fact that coin flip number 1 has no effect on coin flip number 2 and vice versa. So those are independent events and how you apply the multiplication rule to find the probability that multiple independent events occur. Now we want to contrast this with dependent events. So these were all independent events. And now we want to look at dependent events. Dependent events are events that do affect each other. And the most classic example is drawing cards from a deck of playing cards. So if you have a standard deck of 52 playing cards, and you want to say something like, what's the probability that I pull a card from the deck and it's a king, and then I pull another card from the deck and it is also a king? In other words, pulling 2 kings from the deck in a row without replacing the first card. And that without replacing is the key to making these dependent events. So here's what we mean. If we have pull number 1, or draw number 1, and pull number 2 from the deck, and we are not replacing the cards, well, the probability of getting a king on pull number 1, there are 4 kings in a 52 card deck. So there are 52 possible outcomes, but only 4 that are, for me, a success. So the probability of pulling a king on pull number 1 is 4 out of 52. Now let's say I don't put that first card back. I keep it in my hand. I want to pull another card from the deck, and I want that card to also be a king. Well, the probability of getting a king on the second pull is not 4 out of 52, because 2 things. There are no longer 52 cards in the deck. There are only 51. And there are no longer 4 kings. There are only 3 kings. So the probability of pulling a king on the second draw isn't 4 out of 52. Now it's 3 out of 51. In other words, what I pull out of the deck on the first pull is going to affect what I can pull out of the deck on the second pull. It depends whether or not I pulled a king on the first pull, or I pulled a 7, or I pulled some other card. I'm altering my options for pull number 2. That's a great way to think about it. I'm altering my options for the second pull. My possibilities, my possible outcomes are not the same for pull number 2 as they were for pull number 1. These are dependent events, events that affect one another, where the outcome of the first trial, the first experiment, has an effect on the outcome of the second trial or the second experiment. Keep in mind, though, that if I'm pulling cards from a deck and I'm replacing the card each time, so for example, I pull one time, I get a card, then I put that card back into the deck, I shuffle the deck, put the deck on the table, and pull a second card. I look at that, okay, I put that back into the deck, shuffle the deck again, put the deck down on the table, pull a third card. Those then are independent events. I'm replacing the card each time, reshuffling the deck, so my odds are going to be the same every time because in each pull there, I have a full 52 card deck and it's been randomly shuffled, so the likelihood of me pulling any one card is going to be the same every time. It's when I don't replace the cards and I just keep pulling out of the deck one after the other that my odds for pulling any one card in particular are going to change between trials. So what probability formula do we use for dependent events? Well, it's the same as the multiplication rule in terms of we're looking for the probability of A and B. Here we had a formula for the probability that A and B both happen when we have independent events. Here we'll say the probability that A and B both happen, but for dependent events. Well, that probability is going to be the probability that A happens multiplied by this new notation we haven't seen before, which looks like this, and this means the probability that event B happens. This line means given, so the probability that event B happens given that event A has already happened. When we have independent events, the probability that A and B both happen is just the product of the probability that A happens and the probability that B happens. But when it's dependent events, we look at the probability that A and B both happen as the probability that A happens on the first pull. You can kind of think of this as an independent event by itself because nothing has happened before it. This is the first event. This is the first thing to happen. But then for the second event, we have to assume, because A and B are dependent, we have to assume that event A has already happened. So we can't just multiply by the probability of event B. We have to say the probability of event B assuming that A has already happened. So for instance, if we want those two kings in a row, then event A would be a king on pull number 1. Event B would be a king on pull number 2. The probability that A happens, well again, when we have pull number 1, we have a complete 52 card deck. There are 4 kings in the deck, so the probability that we pull a king is 4 out of 52. But the probability of event B, assuming that A has already happened, given that A has already happened, the probability of pulling a king on the second trial depends on the result of A. Assuming that we pulled a king, the probability of pulling a king the second time is 3, because there are only 3 kings left in the deck, divided by 51, because there are only 51 cards left in total. Therefore, we can say the probability of king and king back to back is 4 over 52, the probability of event A, multiplied by the probability of B given A, or 3 over 51. We can actually reduce these fractions to lowest terms. 4 over 52 is the same as 1 over 13, and 3 over 51 is the same as 1 over 17. So then 1 times 1 in the numerator gives us 1, 13 times 17 in the denominator gives us 221. So the probability of pulling 2 kings in a row is 1 in 221. In other words, there's less than a 1% chance of pulling a king 2 times in a row. In this video, I want to focus just on Bayes' theorem, which is a theorem that allows us to calculate the probability that an event happens given our knowledge that some other related event has already taken place. The formula for Bayes' theorem is this formula here. So the probability of event A, given that event B has already happened, that's the probability that we're looking for. And you can see here in the formula, we have the probability of event A, the probability of event B, and the probability of event B happening given that A has already happened. So the easiest way to illustrate this is with an example. So let's go ahead and work through one. We'll come back to this formula and each piece in it. So we'll start to understand it more as we go through the example. So let's pretend that we have 2 dice. We have a pair of dice, and one of the dice is fair, and the other dice is unfair. It's a weighted dice. In the fair die, when I roll it, I have an equal chance of landing on 1, 2, 3, 4, 5, or 6. But in the unfair die, the one that's weighted, it's weighted in such a way that I'm going to land on 6 about 50% of the time. So I'll get a 6 50% of the time. The other options, 1, 2, 3, 4, and 5, all have an equal chance of occurring, but the dice is weighted for us to land on 6 50% of the time. So here's the scenario. We'll call this the scenario. We choose one of the dice without knowing which one we're picking. So we choose one die. We don't know whether we've selected the fair die or the unfair die. They look exactly the same, they feel exactly the same, so we can't tell which one we're picking. We choose one, and then we roll that one die, and it lands on 6. So we roll it, and we get a 6. Then our question at this point is, what is the probability that we picked the biased die given that we've rolled a 6? So we've already rolled a 6, we just don't know if we rolled the biased die or the fair die. We want to figure out the probability that we picked the biased die. So if we come back here to Bayes' theorem, Bayes' theorem is allowing us to calculate the probability of A given that B already happened, which sounds a lot like our problem. We're looking for the probability that we rolled the biased die given that we already rolled a 6. So from that, we can start building out values for Bayes' theorem. So first of all, we're going to call event A choosing the biased die, and we're going to call event B rolling a 6, because the question we're trying to answer is, what is the probability we chose the biased die, A, given that we already rolled a 6, B. So B is rolling the 6, A is choosing the biased die, which means that the probability of A given B we could rewrite as the probability of biased given that we've already rolled a 6. We could write the probability of B given A, which is up here in our formula, as the probability of rolling a 6 given that we have the biased die. The probability of A, up here in our formula, is going to be the probability of picking the biased die, and the probability of B is going to be just the probability of rolling a 6 in general. So when you're solving a conditional probability problem with Bayes' theorem, it's really helpful to write out the scenario that you have, and then based on the question you're trying to answer, to identify event A and event B, and then to write out these 4 values here, because then we can calculate each of these values and just plug them into the Bayes' theorem formula to find the probability we're interested in. So for example, we already know a couple of these values. We know that the probability of rolling a 6, given that we picked the biased die, is 50%, because we were told in the question that the biased die, the unfair die, has a 50% chance of landing on 6. It's weighted that way, so when we roll that die, 50% of the time it's going to land on 6. So the probability here is 50%, or 1/2. We also know the probability of picking the biased die, because we have 2 dice, and we randomly pick one of them. We don't know which one it is, but we have 2 dice sitting in front of us, and we choose to pick one up. So there's a 50-50 chance that we could pick the fair die or the unfair die, which means that there's a 1 in 2 chance that we choose the biased die instead of the fair die. This first value, the probability that we picked the biased die, given that we've already rolled a 6, that's the value we're trying to solve for in Bayes' theorem. That's the value here on the left. That's what we're trying to find. So the only other value we need to know is the probability of getting a 6. Once we have that probability, we can just plug these 3 values into our Bayes' theorem formula, and we'll be able to find the probability that we picked the biased die, given that we've already rolled a 6. So the probability of rolling a 6 is going to be equal to the probability of choosing the biased die and then rolling a 6, plus the probability of choosing the fair die and then rolling a 6. Well, we know that the probability of choosing the biased die is 1/2 because we have an equal chance of choosing the biased versus unbiased die. And if we pick up the biased die, we know that our chance of rolling a 6 is 50% because the biased die is weighted to land on 6 50% of the time. So the probability of rolling a 6 in that case would be 1/2. What we realize here is that choosing the biased die and rolling a 6 are independent events. They're totally separate things. So we can use the multiplication rule and multiply these together to get the probability of both things happening. And then we add to that, and we can again use the multiplication rule. The probability of picking up the fair die is still 1/2, just like the probability of picking up the unfair die. And then if we pick up the fair die, the probability of rolling a 6 is, of course, 1/6, because it's perfectly fair, 6-sided dice. We have an equal chance of getting 1, 2, 3, 4, 5, or 6 on our roll. So the probability there is 1/6. Therefore, the probability of picking up the fair die and rolling a 6 on the fair die is 1/2 times 1/6. So when we do the math here, we get 1/4 plus 1/12. We can find a common denominator here by multiplying by 3/3. And the result then is 3/12 plus 1/12 is equal to 4/12, or if we reduce this fraction to lowest terms, 1/3. So the probability of rolling a 6 in general is 1/3. And now that I have all three values, I can plug in to my Bayes theorem formula. So I would say the probability that we picked the biased die, assuming that we already rolled a 6, will be equal to the probability that we rolled a 6 given that we already picked the biased die, which we found was 1/2, multiplied by the probability that we picked the biased die, which we said was 1/2, divided by the probability that we rolled a 6. So probability of event B, probability that we rolled a 6, which was 1/3. So if I do that math there, I get 1/4 divided by 1/3, which is equal to 1/4. Instead of dividing by 1/3, I can flip that fraction upside down to get the reciprocal and multiply instead of divide. So multiply by 3/1, which is 3/4. So the probability that I chose the biased die when I picked a die off the table, given that I have already rolled a 6 with that die that I chose, that probability is 3/4. Now there's actually another really interesting way that we can calculate it, and it's using a tree diagram. So if the math ever gets confusing, you can fall back to the tree diagram approach or double check yourself with the tree diagram approach. What we want to do with the tree diagram is build a branch of the tree for every decision that we make. So we kind of walk through our scenario like it's a story. And we say, what's the very first thing we do? Well, we have 2 dice in front of us on the table and we pick one. So that's our first choice. That's the first split in our tree. And we say we can either pick the biased die or pick the unbiased die. So fair or unfair, that's our first choice. We pick one of the dice. Now from here, we could roll each dice, and there are 6 possible outcomes that can occur. With the unbiased fair die, we're going to roll it, and we have an equal chance of getting a 1, 2, 3, 4, 5, or 6. So we put all those options down as equally likely. We can roll the fair die, and we might get a 1. We can roll the fair die, we might get a 2. Roll the fair die, we might get a 3, or a 4, or a 5, or a 6. So those are all of our options. For the biased die, the unfair die, remember, it's set up to land on 6 50% of the time. So we need to show branches for all 6 outcomes, 1, 2, 3, 4, 5, and 6, because the unfair die can still land on all of those faces. But we need to set up the branches such that it lands on 6 50% of the time. So here's what that would look like. We would draw out our branches, and you can see we have 1, 2, 3, 4, 5, and 6. But our branches always need to be equally likely. Since we'll land on 6 50% of the time, we need the number 6 to take up 50% of all of the branches from our biased die. Well, we have to show branches for all of the other options, 1, 2, 3, 4, and 5, because we could land on all of those numbers when we roll the biased die. So just to show those branches, it takes us 1, 2, 3, 4, 5 branches, of course. So it takes us 5 branches to show those options, which means that we're also going to need 5 branches in order to show the options for 6, because 6 has to cover 50% of all of these branches coming from the biased die. So I do 5 branches for the 6s and 5 branches for all of the other options. Now all of these options are equally likely, and I could think about it this way. Since there are 10 total branches, and the branches always have to be equally likely, that means there's a 10% chance of getting this branch, rolling the 1 from the biased die. There's a 10% chance of getting this branch, a 10% chance of getting this branch, all the way across, and we can see that that makes sense because for the 6s, I'd have a 10% chance here, 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 and here, and if I add those all up, 10 plus 10 plus 10 plus 10 plus 10 is 50% of getting 6. So I might as well go ahead and put 10% here and 10% here as well. Now that we've set up both the unbiased branches and the biased branches, we need to make sure that we have an equal number of branches at each level in our tree diagram. Over here, on the biased side, we have 10 branches. On the unbiased side, we have 6 branches. So if we wanted them to have an equal number of branches, we could just multiply 10 by 6 and put 60 branches on both sides. Really, all we need to do is find the least common multiple, and for 10 and 6, that's actually 30, but we'll just go ahead and work with 60 in our example, because all we really need to do is make sure we scale up both sides to have an equal number of branches. So if we want both sides to have 60 branches so that they have an equal number, since we have 10 branches over here, that means we would need to make 6 versions of each branch, because we have 10 versions. So if we just duplicate each branch so that there's 6 of each option, then we would have 6 times 10, or 60 branches over here on this side. That means we'll have 6 branches for 1, 6 branches for 2, 6 branches for 3, 6 branches for 4, 6 branches for 5, and then you would have 6 branches for each of these 6s. So since we have 1, 2, 3, 4, 5 6s, and we're multiplying each of these 5 by 6, we'll have 30 total options for the 6s. And here's what that looks like. We have 6 1s, 6 2s, 6 3s, 4s, and 5s, and then 1, 2, 3, 4, 5 times 6, so 30 6s, for 60 branches total on the left-hand side. We need 60 branches total on the right-hand side, and we only have 6 branches right now. So in order to turn 6 into 60, we have to multiply by 10. That means we'll have 10 branches of 1s, 10 branches of 2s, 10 branches of 3s, 4s, 5s, and 6s. And that looks like this: 10 1s, 10 2s, 10 3s, 10 4s, 10 5s, and 10 6s. Now that we have the whole tree set up, we just trim the branches for all of the outcomes that didn't occur. We know that we rolled a 6, which means that we never rolled a 1, 2, 3, 4, or 5, so we can trim all of those branches. So all of these will go away. We'll get rid of the 1s, 2s, 3s, 4s, and 5s. And then same thing over here, we'll get rid of the 1s, the 2s, the 3s, the 4s, and the 5s. And you might be thinking, wow, we did a lot of work to draw those out when we only needed the 6s, but we needed to make sure before we trimmed the trees that our tree was balanced, that we had the 60 branches on the biased side and the 60 branches on the unbiased side. So we had to get it all set up first to make sure that we had the correct number of 6s before we went getting rid of the information that we didn't need. So now the only thing that we care about here are these branches for the biased side, so all of this here, and these branches for the unbiased side. That's all we care about. We can ignore everything else. All we have to do now to find the probability that we rolled the biased die is just compare the branches that we have on the left to the branches that we have on the right. So we don't have to go through and find all these values for Bayes' theorem. We just say we want to know the probability that we rolled the biased die. We've already sort of taken care of the given the fact that we rolled a 6 by ruling out all of the other branches by crossing those out. So we're saying the probability that we rolled the biased die, given that we've already rolled a 6, is going to be equal to, we look at the number of branches that satisfy our criteria, in other words, that come from the biased die, because we want to know the probability of rolling the biased die. There are 30 branches for 6 on this side. So you can think of 30 outcomes that meet our criteria. And then we divide that by the total number of outcomes. We've got 30 branches for 6 on the left, and we've got 10 branches for 6 on the right. So we add the total number of all possible outcomes together, 30 plus 10, there are 40 possible outcomes. So we get 30 over 40, or 3 over 4, which again is what we said up here, the probability that we rolled the biased die, given that we've already rolled a 6, was 3/4. We found that using Bayes' theorem, but we also found it here using the tree diagram method. In this video, I want to start talking about probability for discrete random variables. But in order to do that, we have to define what a discrete random variable actually is. And the best way to do that is by contrasting it with a continuous random variable. So think about a discrete random variable as a variable that can take on a discrete set of values, or a discrete value set. We usually use a capital X to denote a discrete random variable. So let's say that we want our discrete random variable capital X to model the number of heads we get when we flip a coin 2 times. Well, when we flip a coin twice, we only have 4 possible outcomes. We have heads, 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 tails, tails, heads, or tails, tails. These are the only things that can happen. So X models the number of heads that we get when we flip a coin twice. Well, we can see here that if we get this first outcome, then we get 2 heads. If we get this second outcome, we get 1 heads. If we get the third outcome, we get 1 heads. And if we get this fourth outcome, we get 0 heads. So if X is a discrete random variable that models the number of heads we get when we flip a coin 2 times, then X can only take on the discrete set of values 0, 1, and 2. There are no other values that X can have. X can't be 1.5, it can't be 7, it can't be 0.5, it can't be any values other than 0 or 1 or 2. So we would call X a discrete random variable because it can only take on these discrete values, or these particular points. We would contrast that with a continuous random variable that can take on all values along a continuum. An example might be if I want to model the heights of all of the people in the world. So let's say I'm doing this in inches. Someone that's 5 feet tall is going to be 60 inches tall. So they're going to be 60 inches tall. There's going to be a lot of people who are 61 inches tall, some people who are 62 inches tall. There's going to be some people who are 59 inches tall. But there are also going to be people who are 59.5 inches tall. There's going to be people who are 60.5 inches tall. And there's going to be people who are 61.5 inches tall. Furthermore, there are going to be people who are 60.25 inches tall. And if I start measuring even more finely, I could say people who are 60.2 inches tall, or I could say people who are 60.3 inches tall. And I could get more particular and say that there are people who are 60.255 inches tall. Now, at a certain point, our ability to measure the difference between the height of 2 different people is just going to reach its limit. We may only be able to calculate someone's height to a certain number of decimal places, and we can't keep getting more and more and more precise. So you might be tempted to think that this is also a discrete random variable, because maybe we can only measure someone's height precisely to 3 decimal points. And in that case, you could say that, oh, it's a discrete random variable where the heights can only be 60.255, and then 60.256, and then 60.257, and we can't have anything in between these. But barring our inability to measure smaller and smaller differences, that's not really the point we're trying to make. The point that we're trying to make is that people's heights generally fall along a continuum. And we have people that can take on all of these values for their height. It's not like we're limited to people are exactly 59 inches tall, or exactly 60 inches tall, or exactly 61 inches tall, with no possible way to take on values in between. Everybody's height is going to be slightly different. And so we would think about something like this as a continuous random variable versus something like this, which is very clearly a discrete random variable because the value can only possibly take on exactly 0, exactly 1, and exactly 2, nothing else. Now, if I want to create a probability distribution for a discrete random variable, all I need to do is identify the values that the discrete random variable can take on. So like in this case, it can take on 0, 1, and 2. And then I need to find the probability that it will actually take on each of those values. So what is the probability that the value of the discrete random variable x is 0? What's the probability that it's 1? What's the probability that it's 2? Well, in this distribution here, the probability that x is 0 is the probability of getting 2 tails when we flip a coin twice. Well, we know that there are 4 possible outcomes, and one of them is an outcome where we get 0 heads. So 1 out of the 4 outcomes gives us a value of 0 heads, which means that the probability of getting 0 heads is 0.25 or 25%. If I do that same calculation for 1 and 2, I get this probability distribution table for the discrete random variable x. You'll see the capital X here. I can see the values that it takes on, 0, 1, and 2, and then the probability of getting each value. This tells me that there's a 25% chance of getting 0 heads, that there's a 50% chance of getting 1 head, and that there's a 25% chance of getting 2 heads. Keep in mind also that since all probability distributions sum to 1 or 100%, if we know the probability that x takes on one of these values for every value but 1, so let's say we know that this first value is 0.25, that the second value is 0.5, but then let's say that we don't know this value at all. We don't know what this value is. Well, in order to calculate it, so we say 1.00 minus 0.25 minus 0.50, and we get 1 minus 0.25 is 0.75, minus 0.5 is 0.25. So this is equal to 0.25, and then we could go ahead and put in here 0.25. We can also show the data from this table for the discrete random variable in a probability distribution. And that would look something like this. So across the bottom, we can see the values that x can take on. We know x can either be 0 or 1 or 2. So we have 0, 1, and 2 across the bottom. And then we just plot up the vertical axis the percentage chance that each of these occur, or the probability that each of these occur. So we have a 25% chance that x will take on the value of 0, so we graph this 0 bar here up to 0.25. There's a 50% chance that x takes on the value of 1, so for 1 here, we plot this all the way up to 50%, or 0.5, and there's a 25% chance that the discrete random variable x takes on a value of 2, meaning that we get 2 heads when we flip a coin 2 times. There's a 25% chance of that, so we graph this bar up to 25%, or 0.25. And no matter how many values our variable can take on, we can still just line those up side by side in our probability distribution and graph the probability for each one. Now, the last thing I want to talk about is mean, variance, and standard deviation for a discrete random variable. For the mean, which we also call the expected value, since the function is not continuous, what we have to do is we have to weight each of our probabilities by the value that the variable takes on. So in other words, we say mu sub capital X is the discrete random variable. We could also express that as E of capital X, or the expected value, is going to be equal to, and all we do here is we multiply these two values together. So we say 0 times 0.25 we say 1 times 0.5, and we say 2 times 0.25. So the value that the variable can take on, 0, multiplied by the probability that that happens, so 0.25, plus the value that the variable can take on, 1, multiplied by the probability that that happens, 0.50, plus the value that the variable can take on, 2, multiplied by the probability that that happens, 0.25. And we could continue on even if we had more values, more possible values for x. In this case here, we just get 0 for the first term, we get 0.5 for the second term, and 2 times 0.25 is another 0.5. So the result then there is 1. What this tells us, since x models the number of heads we get when we flip a coin 2 times, is that we can expect to get 1 heads every time we flip a coin twice. So that's our expected value. We expect that most of the time we'll get 1 heads when we flip a coin 2 times. And then the variance, so the variance for a discrete random variable, again, we have to weight it just like we did for the mean or the expected value. So the formula we use, again, for variance, it's always sigma squared, but we put the capital X there to indicate the discrete random variable. And then we're just going to take the sum from I equals 1 to n, however many values we have, of x sub I minus the mean, mu sub x, and then we're going to square that, and then we're going to multiply by the probability of that particular value that x takes on. So here's what that looks like. All we do is we take the first value that x can take on, which is 0, and we subtract the mean. Well, we already found that the mean, or the expected value, was 1. So we get 0 minus 1 squared, and then the probability that x takes on the value of 0 is 0.25. So we multiply that by 0.25, and that's all that fancy formula means. We do that for every value that the variable can take on. So then we're going to add to that the next value. X can take on the value of 1. So we say 1 minus the mean. We square that. And then the probability that x will be 1 is 0.5. So we say 0.5. And then add to that the last value. X can take on the value of 2. So we say 2 minus the mean squared, multiplied by the probability of 0.25, so 0.25. If we simplify that, we say 0 minus 1 is negative 1. Negative 1 squared is a positive 1. 1 times 0.25 is 0.25. 1 minus 1 is 0. 0 squared is 0. 0 times 0.5 is 0, so we get plus 0. And then 2 minus 1 is 1. 1 squared is 1. 1 times 0.25 is 0.25. So 0.25 plus 0.25 is equal to 0.5. And that is the variance of this discrete random variable x. And then the last thing is just standard deviation. And standard deviation is always the square root of the variance. So the standard deviation we denote with just sigma. We'll put the x there to indicate the discrete random variable. So sigma sub x is simply going to be equal to the square root of 0.5. And when we calculate that, it is approximately 0.71. So just remember that for a discrete random variable, when we find the mean and the variance, we have to do this weighted method where we multiply the value that the variable can take on by the probability that the variable takes on that value. And then in order to find standard deviation, like always, we just take the square root of the variance. Remember before that we had talked about shifting and scaling a data set. And specifically, we had talked about shifting as adding or subtracting some constant value from all of the points in our data set, and the effect that that would have on our measures of central tendency and measures of spread. So just to refresh our memory a little bit, what we said is that we would have some data set, and we could add or subtract, in other words, shift that original data set by some value k. And this is all review. And basically what we concluded was that the mean, median, and mode would shift by the same amount that we added or subtracted from the dataset, but the range and the interquartile range would stay the same. In other words, let's say that we were going to sketch the distribution of the variable x. That might look something like this. So this is a normal looking distribution for the variable x, and what we would say is that the mean of x is right here at the center. If we then shift this entire data set by k units, and let's say that in this case k is going to be positive, but it could be negative as well. If k is positive, we're going to shift this entire data set over to the right in the positive direction. If k were negative, we would be shifting the whole data set to the left. But k is positive, so after we add k, the distribution might look like this. So this distance we can see from one mean to the other. This distance right here is k. So we could go ahead and say that we are shifting the data set by a distance of k. And notice how that just shifts everything up. So now the mean of the new data set would be here, mu sub y. And you can see that to get from the mean of the original data set to the mean of the new data set, we just add k, which is why we get here x plus k equals y. The median and the mode will do the same thing. They'll just shift up by k units. But the range and the interquartile range are going to stay the same because the distribution isn't stretched or shrunk at all. It has the same proportion. So the range, the distance from one end of the distribution to the other, and the interquartile range, the spread around the median, is the same in both distributions, both the distribution for x and y, which is why the mean, median, and mode shift by k units, but the range and interquartile range stay the same. Now that we're further along in the course, we also want to add to this list standard deviation. And as we can probably tell from the diagram, the standard deviation of x is going to be equal to the standard deviation of the new data set y. And we can see that here, this is a standard deviation for the variable x, so standard deviation for x, and this is a standard deviation for y, so standard deviation for the variable y. And you can see that they are the same width. We've just shifted the whole distribution up to the right, but the width of the standard deviation doesn't change. So when we shift a data set by some positive or negative constant, k, the standard deviation remains the same for both the original data set and the shifted data set. On the other hand, when we scale a data set, so instead of shifting, this is scaling, which is what we do when we multiply or divide by a constant k instead of adding or subtracting. What we saw before was that the mean, median, mode, range, and IQR will all be scaled by that constant k. So in other words, if we take every data point in the original data set x and we multiply it by 2, so we say k is 2, we multiply it by 2, the mean, median, mode, range, and IQR are all going to be multiplied by 2 as well in order to get the new scaled data set. So here's what that looks like. Again, if we just have the distribution of the variable x, and again it looks fairly normal, we could say that we have the mean of the variable x, and we could see here the standard deviation of the variable x. But when we scale by k, the distribution for y might look something like this. So remember, if k is 2, then that means all of these values are going to double. So we could see as an example here, the mean is doubled from the value it is here all the way up to this value here. This is the mean of y. The median and the mode both double, and then the range has to double as well, which means the distribution is going to get stretched out lengthwise so that it's double the length. Remember though that a probability distribution like this has to encompass the same amount of area. So if we're going to stretch this out horizontally, that means we have to also shrink it down vertically so that we're not doubling the amount of area that's under the distribution, we're keeping it the same. So if we're doubling the width, we have to cut the height in half. And we want to also go ahead and add standard deviation to this list, just like we did for shifting. In this case, when we scale the data by k, that means we have to multiply the standard deviation with respect to x by k as well in order to get the new value for the standard deviation for y. And of course, we could show the standard deviation in our visualization here, that this is the standard deviation with respect to y. So the things we want to take away from this video are that when we're shifting the data, the standard deviation is going to stay the same, just like the range and the interquartile range stay the same. When we're scaling the data, the standard deviation is going to scale as well, just like the mean, median, mode, range, and interquartile range all scale as well. And then in addition to that, we want to understand a visual picture here that when we shift a data set, we're shifting by this distance of k, and we can see our standard deviation staying the same width. But when we scale the data set, if we are stretching out the data set like this, because we stretch it out and we need the area under the curve to stay the same, we have to shrink it down vertically so that the area under the new distribution remains the same as the area under the original distribution. And when we stretch out the data set like this, we see the standard deviation gets stretched out as well. In this video, I want to talk about combinations of random variables, and we're going to start by talking about linear combinations of random variables. And then we're going to talk about the specific instance where the random variables we're combining are all normally distributed, because we're going to be able to answer some special kinds of probability questions if all the random variables in the combination are normally distributed. So let's just jump right into it. When we talk about linear combinations of random variables, we're talking about something like this. So let's say that I know on average that I walk 1.1 hours per day. So I could say the mean of my walking time is 1.1. And let's say I also know, because maybe I've collected data for an entire year, and so I have a pretty good idea of both the mean and then also the standard deviation of my walking time is 0.2 hours. Let's say I also know that I spend a certain amount of time biking each day, and the mean of my biking time is 0.6 hours. The standard deviation of my biking time is 0.1 hours. So the point here is that I have two different random variables. A random variable W that models how much time I spend walking each day, and a random variable B that models how much time I spend biking each day. But now I'm interested in my total activity time. I want to know if I add these two together to get total activity time, the time I spend walking and biking combined, how do I use the data that I already have to find totals for activity? Well, for the mean of my activity time, and we'll use the variable A to model total activity time. The mean is really easy. When I want to find the mean of the combination, so the mean of my total activity time, I just add the means together. In other words, when we want to find the mean of the sum, we just find the sum of the means. The standard deviation of the variable A, or my activity time, is not quite as simple. I can't just say the standard deviation of total activity time A is the sum of these two standard deviations. It doesn't work that way. There won't be a true equation. What I have to do instead is first look at the variance. So the variance, remember, is sigma squared. So we'll say the variance of total activity time is going to be equal to, I square the standard deviation for both walking and biking to get the variance for walking and biking, and then I can add the variances together. So I say the variance, sigma squared, of walking plus the variance sigma squared of biking. When I add those two together, it is true that that is equal to the variance of total activity. And then from there, to find standard deviation, I simply take the square root of the variance for activity and I get the standard deviation of activity. So this was mean here, and then this was variance and standard deviation here. Now similarly, if I want to find the difference of my random variables, for example, I want to subtract biking from walking to find the difference, the same thing here with the mean. Instead of finding the sum, I can find the difference and just subtract. If I want to find the difference in the standard deviation, I still find variance, but the variance is still going to be the sum of the variances, not the difference of the variances, which I know might seem counterintuitive, but it's true. We're going to use the sum both times, and then we still just take the square root of variance to get standard deviation. In other words, if we were to make a table here to describe the formulas that we would use for the sum or difference, we would say that we would have the sum or the difference of two random variables, in our case W and B, but we would say that the combination would be given by, and we'll use our variables here where the total combined is activity A, and then the difference of the combination is D. So for the sum, total activity will be equal to walking plus biking, but the difference between walking and biking will be walking minus biking. Then for the mean, I can simply say that the mean of total activity is equal to the mean of walking plus the mean of biking. And I can say that the mean of the difference is equal to the mean of walking minus the mean of biking. But for the variance of the sum versus the difference, the variance sigma squared of my total activity is going to be the sum of the variances here for the sum. So we'll say sigma squared for walking plus sigma squared for biking. But then here's where people get thrown off. The variance for the difference is the same thing. So the variance for the difference is still the sum. So the variance for walking still plus the variance for biking. So that is the tricky part to remember right there, that this is still a sum and not a difference. And then for the standard deviation, we still just take the square root of the variance in both cases, and we end up with sigma of A or sigma of D. So these are the formulas that you use to find the mean, variance, and standard deviation of either the sum or the difference of a combination of random variables. Now here's where combinations get really interesting. When both of the original variables, so in this case the original variables W and B for walking and biking, when both of those are normally distributed, that means that the combination, either the sum or the difference, will also be normally distributed. As long as the original variables are all normally distributed, then the combination will be normally distributed as well, which means that we can do problems like this one. So let's say that we have a popcorn company, and this popcorn company fills tins, metal tins, with varieties of their popcorn flavors. So they have one tin that is filled with 3 flavors. We've got a cheddar popcorn, so maybe a cheddar popcorn in a third of the tin. We have a caramel popcorn in 1/3 of the tin, and then we also have a chocolate popcorn in 1/3 of the tin. So let's pretend that as they're filling these tins, they try to put 1 pound exactly of each flavor of popcorn in the tin. And let's say the amount of each flavor that they put in is normally distributed with a mean of 1 pound and a standard deviation of 0.1 pounds. So let's go ahead and call the cheddar popcorn, let's give that a variable name of D. The caramel popcorn will be M, and the chocolate popcorn will be C. What we're saying then is that the mean of D is 1 pound, and the standard deviation of D is 0.1 pounds. And the same goes for the others. The mean of the caramel popcorn, M, is 1 pound. The standard deviation of the caramel popcorn is 0.1 pounds. And then the mean of the chocolate-covered popcorn is 1 pound. The standard deviation of the chocolate-covered popcorn is 0.1 pounds. And we've been told that all three of these variables are normally distributed. If we define a new variable as W, which is the weight of a full tin, a tin that's already been packed with all three flavors, then we can ask, what is the probability that a full tin contains less than 3.25 pounds of popcorn? And we can see how that's an interesting probability question because we know that the mean of each flavor is 1 pound. So if when they're packing the tin, they hit it right on the money for each flavor, then they'll have 1 pound of cheddar, 1 pound of caramel, and 1 pound of chocolate, and the tin will be exactly 3 pounds. But sometimes they're going to overpack one flavor a little bit and underpack another flavor a little bit, maybe overpack the other flavor. There's some standard deviation there for each flavor. Sometimes they might overpack the tin enough that it's going to weigh more than 3.25 pounds. In other words, they put more than 0.25 extra pounds in it, or more than a quarter pound extra of popcorn. So we want to know the probability that the full tin is less than 3.25 pounds. Well, as we know here from the formulas that we built for these combinations, if we want to find the mean of the total weight, we simply add the means together for the variables that make up the combination. So we can say that since W is equal to D plus M plus C, that the mean of W is equal to the mean of D plus the mean of M plus the mean of C. And then we can substitute those values and get 1 plus 1 plus 1, or 3. So the mean weight of a full tin is going to be 3 pounds. Now we need to find standard deviation. But remember, we can't just add the standard deviations together, even though our linear combination is just adding the three variables together. Instead, we need to first find the variance of each of these variables individually. So to find the variance of each variable, we square the standard deviation. So we say the variance of cheddar here is going to be 0.1 squared, which is 0.01. The variance of caramel, we square again the standard deviation, and we get 0.01. And then the variance of chocolate, we square the standard deviation, and we get 0.01. Now, from this, we can find the variance of the total weight. So the variance, sigma squared, of the total weight W is equal to, and here's where we add all three variances together. So it's equal to the sum of the variance of the cheddar popcorn and the variance of the caramel popcorn and the variance of the chocolate popcorn. And then we can make substitutions and say 0.01 plus 0.01 plus 0.01 is equal to 0.03. So this is the variance for the total weight. Then to find standard deviation, we just take the square root of both sides. So we say the square root of the variance is equal to the square root of 0.03. And then that gives us a standard deviation of approximately 0.1732. And now that we have a mean and a standard deviation for the combination variable W, we're actually able to answer probability questions, because remember, we said that each of the original three variables was normally distributed, which means we know that the combination, the total weight, is also normally distributed. So now we have a normal distribution for W, maybe it looks something like this, and we have a mean here of 3 and a standard deviation of 0.1732. So maybe that comes out to here and here. We would have a standard deviation of 0.1732. So here that would be up at 3.1732. But we've been asked in this question, what's the probability that the tin contains less than 3.25 pounds? So maybe that's somewhere right here, 3.25. We know that it's outside of the first standard deviation because the first standard deviation gets us all the way up to 3.1732. So what we want to do is we want to look at the distance between 3.25, the value we're interested in, and the mean. So we say 3.25 minus the mean of 3 is equal to 0.25. Then we want to express this value that we found in terms of standard deviations. So the way that we do that is we take the 0.25 and we divide that by the standard deviation 0.1732 approximately. The result of that is 1.44. So what that tells us is that 0.25 is about 1.44 standard deviations, or a little less than 1.5 standard deviations away from the mean or above the mean. So what we want to do then is look up 1.44 in a z-table, and when we do that, the value that we find in the z-table is 0.9251. We want to know the probability that the weight is less than 3.25. So we want to know the probability that the weight W falls anywhere in here all the way up to 3.25. Well, this 0.9251 represents all of the area below the 3.25, which means that there is about a 92.5, or maybe we could call it approximately 93% chance that the weight of the popcorn in a full tin is less than 3.25 pounds. We need to understand permutations and combinations in order to be able to answer lots of different kinds of probability questions. So I want to go over both permutations and combinations in this video. They're similar concepts, they each have a formula that we're going to apply, and there's just one specific important difference between the two. So let's go ahead and start with permutations. Now, we'll unpack this in a second, but the formula that we're going to use for permutations is n, p, k. So we have a little n and a little k and a big P is equal to n factorial divided by quantity n minus k factorial. So here's what this really means. I have n choices, and I want to arrange k of them, which sounds kind of strange, but you'll get the idea if we look at a couple examples. So let's say, for instance, that I have 4 scoops of ice cream. So in this case, n will be equal to 4. I only want to eat 3 of the scoops, so that means k is going to be equal to 3. I have 4 options, I'm choosing 3 of them. And in this case, I care about the order in which I eat the scoops. Let's say my 4 scoops of ice cream are chocolate, strawberry, vanilla, and mint. I only want to eat 3 of the scoops, and I care about the order in which I eat the scoops. So here's what that means. Let's say, for instance, that the 3 scoops I choose to eat are chocolate, strawberry, and vanilla. I'm not going to eat the mint. I could eat those 3 flavors as chocolate, strawberry, vanilla, or I could eat them as chocolate, vanilla, strawberry, or I could eat them as strawberry, chocolate, vanilla, or keep the strawberry first, and then flip the vanilla and the chocolate, so vanilla and then chocolate, or I could eat the vanilla first. And there are going to be two cases where that's true. So vanilla first, then strawberry, then chocolate, or then chocolate, then strawberry. So there are 1, 2, 3, 4, 5, 6 ways alone just to eat chocolate, strawberry, and vanilla, those 3 scoops. But I could choose 3 different scoops. I could choose, for instance, chocolate, strawberry, and mint, or chocolate, vanilla, and mint, or strawberry, vanilla, and mint. You get the idea. And then with all of those different combinations, I could go through and arrange them in all different orders, just like I did here for chocolate, strawberry, and vanilla. So when I find this permutation, I have 4 scoops of ice cream, I want to eat 3 of them. How many permutations is that? That big number is what I'm looking for, the number where I pick 3 different scoops, and then I arrange them in a specific order, and I count up all of those possibilities. So we're actually really glad that we have a formula in this case, because laying out all those possibilities, especially as we add more data points, it would take us forever to figure out all of these different arrangements. But this formula here for the number of permutations that exist, of course, makes it a whole lot easier. So the formula says that when you have 4 items or 4 spots or 4 options, and you're looking for an arrangement of 3 of them, you would calculate that permutation as 4, 3, and that's going to be 4 factorial divided by 4 minus 3 factorial that way. Now the math symbol factorial, the exclamation point, just means take this value in front of it, so in this case 4, and multiply this by all of the integers less than 4 all the way down to 4. In other words, in plain English, 4 factorial means 4 times 3 times 2 times 1. 6 factorial would mean 6 times 5 times 4 times 3 times 2 times 1. 3 factorial would mean 3 times 2 times 1. So you get the idea. But if we want to simplify this, we just expand the factorials. So 4 factorial will be 4 times 3 times 2 times 1. And then in the denominator, we do our parentheses first. So 4 minus 3 is 1. So we get 1 factorial. Well, 1 factorial is still just 1. Those are the only ones that are tricky. 1 factorial is still 1. 0 factorial is also 1, actually. So here we have 4 times 3 times 2 times 1 divided by 1. Well, dividing by 1 doesn't have any effect on the value, so we don't have to worry about that. 4 times 3 is 12. 12 times 2 is 24. 24 times 1 is still 24. So we get 24. What that tells us is that there are 24 different ways for us to eat 3 scoops of ice cream in a specific order if we have 4 scoops to choose from. And that is the idea behind permutations. Basically, the order matters. So I count chocolate, strawberry, vanilla as 1, and I count chocolate, vanilla, strawberry as another. So with permutations, the order makes a difference. If I change the order, I count those as 2 different permutations. And that's the difference between a permutation and a combination. So in a combination, the order doesn't matter. So all of these arrangements here that we drew out between chocolate, strawberry, and vanilla, they would all count as 1. Because in a combination, all we care about is which 3 items we've selected. Since all of these are just made up by chocolate, strawberry, and vanilla, no matter how we arrange them, they're all just chocolate, strawberry, vanilla, these would all just count as 1 combination. So your value for combinations will always be less than your value for permutations using the same scenario, because with a permutation, we care about the order in which we arrange our items, and with a combination, we don't. So the formula for the combination looks similar. Again, we have n, and then this time c for combination, and then our little k is equal to n factorial divided by k factorial times quantity n minus k factorial. So you'll notice it's exactly the same as the permutation formula, except for this single k factorial value in the denominator. Other than that, the formulas are identical. So let's take the same example with the ice cream. We still have the same 4 ice cream flavors. If we want to find all of the combinations that we can make with these 4 ice cream flavors, again, we're only looking at the 3 scoops that I can pick. So chocolate, strawberry, vanilla would be one combination. Chocolate, strawberry, mint would be another combination. Strawberry, vanilla, mint would be another combination. And all of those just count as one. We don't then go pull them apart down here and figure out the order like we did with the combination. So here's what that looks like when we plug into the formula. This time we say 4 and then our big C for combination, 3 is equal to 4 factorial divided by, since k is 3, 3 factorial times 4 minus 3 factorial. And then just like with permutations, the easiest way to solve this is to expand each of the factorials. So the 4 factorial, again, will be 4 times 3 times 2 times 1. And then in the denominator, the 3 factorial will be 3 times 2 times 1. 4 minus 3 is 1. So here we'll get 1 factorial, but we know that 1 factorial is just equal to 1. So we multiply by 1 here to account for the quantity 4 minus 3 factorial. Then what we see here is that everything in the numerator is multiplied together, and everything in the denominator is multiplied together. So we can simply cancel common factors from the numerator and denominator. So our 3's will cancel, our 2's will cancel, our 1's will cancel, and then we're simply just left with 4 divided by 1, but 4 divided by 1 is just 4. So there are only 4 combinations that I can make when I have 4 scoops of ice cream. Remember how we said before that our value for combinations would always be less than our value for permutations, because again, with combinations, we don't care about the order. Even if we arrange things in a different order, it still just counts as one combination, because we only care about the different items that we're picking and pulling together. But with a permutation, we care both about the items that we pull together and the order in which we arrange them. Remember that the prefix by means two. So when we say binomial or binomial random variables, we're talking about a specific kind of variable that can only take on 2 values. So for example, flipping a coin would be a great example, because when you flip a coin, you can only get one of 2 values, heads or tails. Another example would be if I have 2 marbles in a bag, a red one and a green one, and I'm doing trials where I reach into the bag and pull out 1 marble, that could be a binomial random variable, because I'm either going to get the red marble or the green marble. There are exactly 2 possible outcomes, not fewer and not more. So when we have exactly 2 possible outcomes, it's possible that we're dealing with a binomial random variable. But exactly 2 possible outcomes isn't the only criteria for having a binomial random variable. We also have to have independent trials. In other words, when I'm flipping the coin over and over again, I'm running a bunch of trials. When I'm pulling a marble out of a bag over and over, I'm running a bunch of trials. Each of those trials must be independent in order for us to call it a binomial random variable. The next thing is that each trial has to be able to be classified as a success or a failure. And all we do there is define which kind of outcome we're looking for. So for example, if I'm flipping a coin over and over again and I want heads, or I want to look at how many times I get heads, I can call getting heads a success and getting tails a failure. Or if I'm drawing a marble out of a bag and I have a green or a red marble, then I can call getting the green marble a success and getting the red marble a failure. But you have to be able to classify each outcome as a success or a failure. There also have to be a fixed number of trials. In other words, you have to be able to say, I flip a coin 10 times, or I draw a marble out of the bag 5 times. you have a fixed number of trials that you're running, I can't say something like, how many trials does it take me to pull a green marble out of the bag? We're not defining a specific number of trials in that case. So we have to have a fixed number of trials that we've determined up front. We are running this many trials exactly. And then the last one, the fourth and final, is that the probability of success on each trial is constant. In other words, if I'm flipping a coin and I define getting heads as a success, is the probability of getting heads on the first trial the same as the probability of getting heads on the second trial, and the same as the probability of getting heads on the third trial, and on and on and on? That probability has to stay constant. Or if I'm pulling marbles out of a bag, I have one red marble, one green marble, and I say getting the green marble is a success, well, I can pull out a marble, and the probability of getting green is the same if I then put that marble back in the bag, shake it around, pull the marble out again. The probability is still the same if I then again put the marble back in the bag, shake it around, and pull it out again. So that probability of getting a green marble is staying constant. That's required for a binomial random variable. If we're thinking about a scenario and we run through these four criteria, and our scenario doesn't meet any one or more of these criteria, then we can't call our variable a binomial random variable. We might be able to do something else with it, but we can't call it a binomial random variable. We have to meet each and every one of these if we want to classify our variable as a binomial random variable. So let's do an example, and let's say for a second that we have 2 green marbles and 1 red marble in like a paper bag so we can't see inside of it. And we're going to do 5 trials where we pull out one of the marbles, look at the color, and then put the marble back. Of course, we're going to record the color that we get in each of the 5 trials, and the question we want to answer is, what is the probability of getting the red marble exactly 3 times? First of all, let's say right away that the probability of getting red 3 times actually means that we're going to get green 2 times, and we're going to get red 3 times. Because if we're running 5 trials and we're getting red 3 times, well, the only other option out of the bag is green, which means we must have gotten green the other 2 times. So before we go forward with this problem, let's confirm first of all that this is a binomial random variable. So the first criteria is independent trials. Well, what we're doing is we're pulling a marble out of the bag, writing down what color we got, and then putting the marble back in, shaking up the bag, and pulling another one out again. Every time we do that, the marble that we pulled out the first time isn't going to affect the marble that we pull out the second time. It's not going to affect the marble we pull out the third time, because we're putting the marble back and shaking up the bag. So the outcome of each trial will not affect the outcome of any of the other trials. So we can say that we do in fact have independent trials. What about success or failure? We need to be able to classify the outcome of each trial as a success or a failure. Well, since we're interested in the probability of getting red 3 times, let's go ahead and call getting red a success, and we'll call getting green a failure. And keep in mind that for these problems, success and failure doesn't mean good and bad. It just means that we're going to define red as what we were looking for and green as what we weren't looking for. In this case, we can define each trial as a success or a failure because we just call red the success and green the failure, so we meet that criteria as well. Do we have a fixed number of trials? Well, yes, we already said up front before we even started that we're going to run 5 trials exactly. So we've got a fixed number. And then the probability of success has to stay constant. Well, the probability of a success is the probability that we get red. And the probability that we get red, so the probability of getting red, is going to be equal to 1/3, because there are 3 possible outcomes in the bag and 1 outcome that meets our criteria. So 1 out of the 3 outcomes is a success. So the probability of a success, or the probability of getting red, is 1/3. And if I put the marble I pulled back into the bag every time and shake it up, the probability of getting red on any one pull is always going to be 1/3. I'm always going to have the 2 green marbles and the 1 red marble in the bag when I pull one out. So the probability of getting red will always be 1/3, and that probability is going to stay constant across all of my trials. Therefore, I can define this as a binomial random variable, and I can try to answer the question here that we said, what is the probability of getting red on exactly 3 pulls? Well, for a binomial random variable, there's a formula that we use for that. It's the probability of k successes in n attempts is going to be equal to, this is called n choose k, it's the binomial coefficient, and we'll go back to that in a second, times p to the k times 1 minus p to the n minus k. P is the probability of success, and k is the exact number of times that we want a success. This binomial coefficient, that's what this notation here is called, the n choose k is the binomial coefficient. That is just the combination. So this is the combination n choose k. We learned about this in permutations and combinations, but n choose k, that combination, is equal to n factorial divided by k factorial times n minus k factorial. So that's the first thing we want to find. We want to find this combination, because then we'll be able to plug that into our formula for the binomial coefficient. Then we'll find the rest of this here. So let's start with n choose k. Well, for us, that's just choosing the number of successes we want out of the number of trials that we're going to run. So in our problem, that's really 5 choose 3, because we're running 5 trials and we want 3 successes. So we're going to say 5 choose 3 is equal to 5 factorial when we plug 5 in for n, divided by 3 factorial when we plug 3 in for k, times 5 minus 3 factorial. When we expand out those factorials, remember that 5 factorial is 5 times 4 times 3 times 2 times 1. And then in the denominator, 3 factorial is 3 times 2 times 1. 5 minus 3, we have to do what's inside the parentheses first. 5 minus 3 is 2, so we get 2 factorial. Well, 2 factorial is 2 times 1. Now we can cancel common factors from the numerator and denominator. Well, 3, 2, and 1 cancel with 3, 2, and 1. Everything's multiplied together in both the numerator and denominator, which is why I can just cancel factors like that. So what we're left with is 5 times 4 in the numerator, 20, divided by 2 times 1 in the denominator, or 2, and 20 over 2 is 10. So my binomial coefficient will be 10. Now I just need to plug everything else into the formula. So I'm saying the probability of k successes in n attempts. Well, we want 3 successes in 5 attempts, so we could maybe just write that as 3 in 5. This isn't technical, I'm just abbreviating here. We could also have written this more technically as the probability of r equals 3, because we want exactly 3 red pulls out of 5 trials, so that's the probability of getting the red marble 3 times. Is going to be equal to, we already calculated that the binomial coefficient was 10, so we'll plug that in. And then remember, p is the probability of success. Well, the probability of success we already calculated as 1/3. The probability of getting the red marble is 1/3, so we'll multiply this by 1/3, and then we're raising that to the k, which is the number of successes that we want to get. Since we want 3 successes, we want to raise this to the 3rd power. Then 1 minus the probability of success. Well, if the probability of success is 1/3, then 1 minus 1/3 is 2/3. So we're going to get here 2/3, and then we're raising that to the n minus k. Well, n was 5, k was 3, because we're running 5 trials and we want 3 successes. So 5 minus 3 is 2, so we're going to put 5 minus 3, or 2, in here. So we get 2/3 to the 2. Now the important thing to realize about this formula, because this one looks a little complicated, But we just need to remember the combination formula here to calculate the binomial coefficient. But everything else, this here, 1/3, this is the probability of success, the probability of getting a red marble, raised to the number of times we want to have that success. We want to have that success 3 times. This is the probability of failure, the probability in our case of getting a green marble, raised to the number of times that we want to have that failure. So we're just saying probability of success raised to the number of times we want a success, multiplied by the probability of failure raised to the number of times we want the failure. That's what this formula means. So just think about success to the power of success times failure to the power of failure. That's all we really need to remember, plus this binomial coefficient out in front. But if we can remember that, then that is our formula for the probability of k successes in n attempts. So now we just need to do the math here. So what we get is 10, and then 1/3 to the 3 is 1/3 times 1/3 times 1/3, which is 1/27. And then 2/3 squared is 2/3 times 2/3, which is 4/9. So when we multiply across our numerators, we get 10 times 1 times 4 is 40. And across the denominators, 27 times 9 is 243. And if we want, we can calculate that as a decimal and say this is approximately equal to 16.5%, which means that there's about a 16.5% chance of pulling the red marble exactly 3 times if we run 5 trials. Keep in mind that I can go through the same process and use this same formula for any number of successes that I want to. So I could, for example, do the same calculation to find the probability that we get the red marble exactly 1 time, or exactly 2 times, or exactly 3 times like we did, or exactly 4 times, or exactly 5 times, or exactly 0 times. Or if I wanted to say instead, what's the probability that I pull a green marble exactly twice, I could define a green marble as success and a red marble as failure. And then I could go through and do these calculations again, and I could figure that out. So this is just the method you'll use for finding the probability of an exact number of successes in a specific number of trials. Continuing on with our same marble example, I want to show you briefly how to plot a probability distribution for a binomial random variable. So we have that same marble problem where we have 2 green marbles and we have 1 red marble, and we're running the same number of trials. We're running 5 trials, and we want to look at the probability distribution for pulling a red marble like we talked about 0 times, 1 time, 2 times, etc. So we're going to say probability of pulling red 0 times in 5 pulls. So we'll say 0 in 5. And we want to calculate all these probabilities. So we're going to say the probability of getting red once in 5 trials, the probability of getting red twice in 5 trials, and on to 5. And I'm doing it like this because I want to show you the pattern here. So we're going to use that same formula where we had at first the binomial coefficient. So the binomial coefficient for this will be 5 choose 0. We're running 5 trials, but we're choosing success 0 times. The binomial coefficient here will be 5 choose 1. Here it'll be 5 choose 2, so we'll fill this in the rest of the way. Then remember we wanted to say we multiply that by the probability of success raised to the number of times we want that success. Well, we said success was pulling the red marble. The probability of pulling the red marble was 1/3, so 1/3, and we want to raise that to the number of times that we're pulling the red marble. Well, here we're saying we're going to pull the red marble 0 times, so we would raise that to the 0 power. Here we want to pull the red marble once. Here we want to pull the red marble twice, and on down to pulling the red marble 5 times. And then we say the probability of failure raised to the number of times that we have the failure. So here, the probability of failure is the probability of pulling the green marble, which we know is 2/3. And here we're going to fail 5 times. Here we have a 2/3 probability, and we're going to fail 4 times. Notice how the probabilities 1/3 and 2/3 always add to 1, because the probability distribution always has to sum to 1, and the exponents, the number of successes and the number of failures, always has to sum to 5 because we're always running 5 trials. So here, probability of failure, we're going to have 3 failures. 2 plus 3 is 5. 1 plus 4 is 5. 0 plus 5 is 5. So it's always going to sum to 5. Now from here, it's just a bunch of arithmetic, but if we do these calculations, we see that the probability of pulling red 0 times in 5 trials is approximately 14%. The probability of pulling 1 red marble in 5 trials is about 33%. The probability of pulling 2 red marbles in 5 trials is also approximately 33%, and we're rounding to the nearest percent here, or to the nearest hundredth. The probability of pulling exactly 3 red marbles in 5 trials, we already calculated, was about 16%. The probability of 4 red marbles is about 4%. And the probability of pulling 5 marbles is less than 1%. If we round it to the nearest percent, it's 0%, even though it does have some probability greater than 0. It rounds to 0 if we round to the nearest percent. So now that we've done all this work, what we see is a little bit of a probability distribution. It shows us the likelihood of pulling the red marble a certain number of times, all the way from 0 times to 5 times. These are all of the possible outcomes because we're running exactly 5 trials, no more, no less. So the only values that this binomial random variable can take on are 0, 1, 2, 3, 4, and 5, since the binomial random variable models the number of times we pull a red marble. So these are our only options. These are the percent chances associated with each option. Then we can go ahead and graph this as a probability distribution. And here's what that looks like. So this is the probability that our binomial random variable, where our binomial random variable represents the number of times we pull a red marble, this shows the probability that we pull a red marble 0 times. The vertical axis here is in percentages. So this is actually 10%, this is 20%, 30% chance, and 40% chance. So the probability that we pull 0 red marbles in 5 trials is here at about 14%. We got 33% for both pulling a red marble 1 time and 2 times, so we show that up here at 33. And then we have our 16%, our 4%, and our rounded to 0%. So now we get a visual picture of the likelihood of all of these possible outcomes for the binomial random variable. And what this tells us is that if we run 5 trials, we're most likely to pull a red marble once or twice. We're less likely to pull a red marble 0 times or 3 times, and it's really unlikely that we'll pull the red marble 4 times or 5 times. In fact, I could even add these percentages together. 33 plus 33 is 66, and I could say there's a 66% chance that we're either going to pull the red marble once or twice if we run 5 trials, because together those outcomes account for 66%. So I've got about a 2/3 chance that one of these 2 things is going to happen, and then a much smaller chance that any of the other outcomes occur. So this is what the probability distribution looks like for a binomial random variable, and these are the calculations that we go through in order to create that distribution. I just want to use this video to talk about 2 more things for binomial random variables. The first of which is whenever we're talking about at least probability or at most probability, which we'll get into, and then the mean, variance, and standard deviation of a binomial random variable. So let's start with at least and at most probability. So what do we mean by that? Well, in the last section, we talked about pulling marbles out of a bag where the bag has 2 green marbles and 1 red marble. We talked about the binomial random variable as the probability of pulling the red marble a certain number of times. And we looked at the probability of pulling the red marble exactly 0 times, exactly 1 time, exactly 2 times, exactly 3 times, exactly 4 times, and exactly 5 times when we're doing 5 trials. And then we plotted those outcomes in a distribution to show the probability of all of those outcomes for the binomial random variable. But sometimes we're not asked to find the probability of getting the red marble exactly 4 times or exactly 1 time. Sometimes we're asked about the probability of getting the red marble at least 3 times, meaning the probability of getting it 3 times or 4 times or 5 times in 5 trials. Or we might be asked the probability that we'll pull the red marble at most twice, which would mean pulling the red marble 0 times or 1 time or 2 times. The good news is that calculating this probability isn't too complicated in comparison to calculating the probability of getting the red marble an exact number of times. For example, the probability of getting red at least 3 times, which we could write as at least 3 reds in 5 pulls, or we could say red greater than or equal to 3, because we're getting the red marble 3 times or 4 times or 5 times. At least 3 times, the probability of getting red at least 3 times means the probability that red is greater than or equal to 3. We also could have written this, of course, as 3 less than or equal to red. The probability of that is just going to be equal to the probability that we get red exactly 3 times, plus the probability that we get red exactly 4 times, plus the probability that we get red exactly 5 times. So that's all we're doing, and we already calculated the probability of getting red 3 times, 4 times, and 5 times. So the probability of getting red at least 3 times, which means 3 or 4 or 5 times, is just each of those added together. And remember that, let's say we hadn't calculated these yet, each one is just the product of the binomial coefficient, the probability of success raised to the number of times you want that success, times the probability of failure raised to the number of times you want that failure. In other words, here we're running 5 trials and we're choosing 3 successes. So this is going to be the binomial coefficient, 5 choose 3. The probability of success, the probability of getting red, is 1/3. So we say 1/3. And we want 3 successes. So we raise that to the 3rd power. The probability of failure, which is the probability of getting anything other than red, in this case green, is 2/3. So we get 2/3. And we want failure twice. So we raise that to the power of 2. The probability of getting red 4 times is the binomial coefficient 5 choose 4. The probability of success is 1/3, and we want 4 successes. And the probability of failure is 2/3, and we want 1 failure. And then the probability that we get exactly 5 reds or 5 successes is 5 choose 5 times the probability of success, 1/3, raised to the number of times we want success, which is 5 times, multiplied by the probability of failure, raised to the number of times we want the failure, which is 0 times. And we've already calculated these, so let's just say that this is approximately about 0.1646 plus about 0.0412 plus about 0.0041. And so if we add all these together, we get 0.2099, or about 21%, meaning there's a 21% chance that we'll pull red at least 3 times when we run 5 trials. So that's how you would calculate at least probability. And remember, we could write that as the probability that we pull red more than 3 times, so R greater than or equal to 3, or we could write it as 3 less than or equal to R. Those inequalities mean the same thing. Keep in mind also that a probability distribution will always sum to 1 or 100%. So if you were then asked, what is the probability that you get a red marble at most 2 times, which you could write as the probability that you get red less than or equal to 2 times, or 2 greater than or equal to R, that is the probability that you get red 0 times, or 1 time, or 2 times, because you're saying at most 2 times. Well, remember, for this problem, the only values that we can get for the number of times we pull the red marble are 0, 1, 2, 3, 4, and 5. Well, we just found the probability of getting the red marble 3 times or 4 times or 5 times. So everything else is 0 time or 1 time or 2 times. So the probability that we get red less than or equal to 2 times, 0 time or 1 time or 2 times, we don't have to go through all of this tedious calculation. All we have to do is say that this is going to be equal to 100% minus the 21% value that we already calculated, because this probability will be everything other than the 21%. So this will then be approximately 100% minus 21% is 79%. So whenever we have questions like this, at least or at most, we can always flip around the question to look at the other side. So being asked, what is the probability that we get red at least 3 times, is exactly the same as asking, what is the probability that we don't get red 0 times or 1 time or 2 times? Which means to calculate this value, we can either calculate it directly, like we did, and find the probability that we get red on at least 3 pulls, 3 times or 4 times or 5 times, or we could say that the probability that we get red at least 3 times is going to be equal to 1 minus the probability that we get red less than or equal to 2 times. In other words, we could have calculated this value at 79% and then just subtracted that from 1. So we would have gotten 100% minus 79% is equal to 21%. We would have come up with that same 21% value as we did going through the calculations. And sometimes it's going to be a lot easier to calculate the probability one way or the other, especially if you have something with a large number of trials. So if instead we were pulling a marble 10 times instead of 5, so we're doing 10 trials, we're pulling the marble out 10 times, and we're asked, what is the probability that we get at least 1 red marble? So the probability that we get red 1 or more times, so at least once. If we go through and do the calculation directly, that's going to be the probability that we get red 1 time plus the probability that we get red 2 times plus the probability that we get red 3 times, and on and on and on, all the way up to 10 times. 4 times, 5 times, 6, 7, 8, 9, and 10. And with the binomial coefficients and all of this multiplication and addition here, that's a lot of work to do the calculation. Or we could just flip it around, realizing that instead of doing all that work, we could just say that this is the same as 1 minus the probability of getting red on exactly 0 pulls. Or we could just write this as 1 minus the probability of getting red on less than 1 pull, because here we want the probability of getting red on more than 1 pull, so getting at least 1 red marble. The only option that doesn't satisfy this is getting red exactly 0 times. So instead of doing 10 calculations here for the probability that I get exactly 1 red versus 2 reds versus 3 reds, 4 reds, 5 reds, 6 reds, 7, all the way up to 10, I only have to do one of them. And here I just say 1 minus the probability that I get exactly 0 reds is the binomial coefficient 10 choose 0. I'm doing 10 trials. I'm getting 0 successes, times the probability of red getting 0 successes, times the probability of failure, I'm getting 10 failures. And that's the only calculation I have to do. So the takeaway is, especially when you have a large number of trials, think about what you're actually being asked and figure out if it's going to be easier to calculate what they asked you to find directly, or to find the complementary probability, the other part of the probability distribution, calculate that instead, and then subtract that from 1 or 100%. And then the last thing about binomial random variables, I just want to talk about mean, variance, and standard deviation for binomial random variables. So for the mean, we always call the mean of the binomial random variable mu of x we usually use capital X for a binomial random variable. Or we can call the mean the expected value. That's just another name for the mean. So we would say the expected value of the binomial random variable, capital X. But these are just notation. All we're doing here is calculating the mean. Don't get thrown off by the fact that this maybe looks a little different. We're just finding the mean like we would normally find mu. Well, for a binomial random variable, the mean is given by the number of trials we run, n, multiplied by the probability of success, p. So if I wanted to calculate the mean for this experiment we're doing here, where we run 5 trials, pulling the marble out of the bag each time, the number of trials that we run is 5, and the probability of success, the probability of pulling the red marble, is 1/3, so the mean will be 5/3. The variance of a binomial random variable, we always indicate with sigma squared, and then we can put the capital X here to indicate it's a binomial random variable. That's always equal to the number of trials we run multiplied by the probability of success multiplied by 1 minus p, which is really the probability of failure. So the number of trials times the probability of success times the probability of failure. In our case with the marbles, we're running 5 trials. The probability of success is 1/3, and the probability of failure is 2/3. So the variance for our marble problem is, let's see if we multiply across the numerators, 5 times 1 is 5, 5 times 2 is 10, so I get 10 in the numerator, and in the denominator, 3 times 3 is 9, so the variance is 10/9. And then the standard deviation of a binomial random variable will always be equal to the square root of the variance. So I can say the square root of the variance is going to be equal to the square root of 10/9. And of course, the square root of the variance, if I have sigma squared and I take the square root, I get the standard deviation, sigma. So sigma of the binomial random variable will be equal to, and remember when you take the square root of a fraction, you can take the square root of the numerator and denominator separately. So I get square root 10 over square root 9. Square root 10 can't be simplified, so we leave that. The square root of 9 is 3. And if I wanted to put all of these in decimal form, as we normally do, I could do that, and I could say that the mean is about 1.67, that the variance is approximately 1.11, and then that the standard deviation is approximately 1.05. A Bernoulli random variable is a special kind of binomial random variable. So you think of Bernoulli random variables as a subcategory within, more generally, binomial random variables. The difference is that a Bernoulli random variable can only have one trial, whereas a binomial random variable can have an infinite number of trials. And with the Bernoulli random variable, we always define success as a 1, and we always define failure as a 0. Calling a success 1 and a failure 0 lets us give weight to success and failure such that we can mathematically find mean and variance and standard deviation. So let's say I want to know how many students in my math class have brown hair. There are 20 students in my class, and I look at each one of them and I see that 12 of them have brown hair, which means that out of all the students in my class, 12 over 20 have brown hair. If I reduce this fraction to lowest terms, I get 3/5, which is equal to 60%. So I'm going to say that 60% of the students in my class have brown hair, and I'm going to define success for this Bernoulli random variable as having brown hair, and I'm going to define failure as not having brown hair. Then we could sketch a Bernoulli distribution for this data. So again, success is brown hair, that's a 1, so we could call this brown hair. And then failure is not brown hair. So we could call this not brown, again, because 1 is a success and 0 is a failure. And we said that 60% of the students in our class had brown hair. So we plot this up to 0.6 or 60%, which means that 40% of the students in our class don't have brown hair because we have to account for 100% of the students, and 100% minus 60% is 40%. So that means 40% or 0.4 don't have brown hair. So this is what the Bernoulli distribution for this data would look like. Now, if we want to find the mean of this Bernoulli random variable, we use the same formula every time. So the mean, again, will be mu, which is going to be equal to, and here's where we have to weight the data by 1 a success or 0 a failure. So we go ahead and take the percentage of failures, or let's just say the failure percentage, and we multiply that by the weight of failure, which is 0. And then we add to that the percentage of success, or we'll just call it the success percentage, and we weight that by the value we've assigned to success, which is 1. Of course, 0 multiplying by 0 is going to eliminate this term completely. Multiplying by 1 has no effect on this term, so really, mu, the mean, comes out to just the success percentage, or the percentage of success. Well, we already know that the percentage of success is 60%. We saw that there were 12 students in our class with brown hair out of 20 total students, and 12 divided by 20 is 60%. So whatever percentage you find for success in your data, that's going to be the mean of your Bernoulli random variable. So in our case, we can say mu is equal to 60%. And you don't even ever need the formula. You can just grab it from this percentage here. Oftentimes, you'll actually see this mean formula expressed as mu equals p, because we define p as the percentage of success. So if p is the percentage of success, then the mean of a Bernoulli random variable is just going to be mu equals p. Now for the variance of a Bernoulli random variable, we always call the variance sigma squared, and then we set that equal to the probability of failure, or the percentage of failure, just like we did here. But remember, if the percentage of success is p, then the percentage of failure, so let's say the percentage of success is p, then the percentage of failure is just 1 minus p, because probability always has to sum to 1, or 100%. So just like we calculated here, if success was 60%, then failure had to be 1 minus 60%, or 40%, which is how we came up with the 40% of not brown hair as a failure. So for the variance, we say that the variance is equal to the probability of failure, 1 minus p, just like we did here. And then we always take the weight of failure, 0, so we say 0 minus p. This gives us the distance from the mean of this data point 0, and then we square that. And this is all typical variance formula. And then we add to that, this time the probability of success, so the percentage of success like we did up here, that's p. And this time we multiply by the distance of success from the mean. Well, that's going to be 1 minus the mean percentage is p, so we get 1 minus p, and then we square that to get the squared distance. Now the cool thing is that this is always going to be the case, and it's always going to simplify the same way. So 0 minus p is negative p. Negative p quantity squared is p squared. So we end up with p squared times 1 minus p. And then we get here plus p times, if we multiply out 1 minus p times 1 minus p, keep in mind that that looks like this, 1 minus p. And we have to FOIL this out. Multiplying 1 by 1 is 1. 1 times negative p is negative p. Negative p times 1 is another negative p. And negative p times negative p is a positive p squared. Here we'll distribute the p squared across the 1 minus p. P squared times 1 is p squared. P squared times a negative p is a negative p cubed. And then we'll distribute the p here. So p times 1 is p. P times a negative p is minus p squared. We get minus p squared and plus p cubed. we'll get minus p cubed and plus p cubed to cancel. We'll get plus p squared and minus p squared to cancel, leaving us with only p minus p squared, which is the same thing if I factor out a p, as p times 1 minus p. Now that's a lot of algebra to follow, but all I wanted to do was show you how we get to the variance formula. The variance formula will always just be this formula here, so we'll write that out as variance will always be sigma squared is equal to p times 1 minus p. So this is really all you have to remember here. So for us, in order to find sigma squared, we just take the variance, sigma squared, is equal to p, the probability of success, 60%, so 0.6, times 1 minus p, which is just the probability of failure, or 40%. So it's really always just success times failure. In our case, 60% times 40%. That's going to give us 0.24. So the variance of our Bernoulli random variable is 0.24. And then just as before, standard deviation is always just the square root of the variance. So standard deviation will be given by the square root of the variance. So in our case here, we would just take the square root of 0.24, and we'd get approximately, if we round to the nearest hundredth, 0.49. So just remember that for a Bernoulli random variable, we have to have just one single trial, like we did here, where we just found the number of students in our class with brown hair. That was one survey, one trial, and we're going to get a certain probability of success. From there, we can just take 100% minus that value and get the probability of failure. And with a Bernoulli random variable, we always weight the success as a 1 and weight the failure as a 0, which is what will allow us to find mean, variance, and standard deviation. The mean is always just going to be the percentage of success, which is a little counterintuitive because every single person in our class takes on a discrete value. They either take on 0, not brown hair, or 1, brown hair, success or failure. It's a little weird to say that the mean is 60% because we can think about this value as 0, this value as 1. 60% is going to fall somewhere in the middle, a little closer to success than failure, but still somewhere in the middle. Nobody has 60% brown hair. One person can't take on this value. Everybody has either brown hair or not brown hair. It's one or the other, success or failure, 0 or 1. So this 60% like somewhat brown hair kind of value feels a little strange, but that comes from weighting these as success or failure. It's what allows us to find a mean when we have this kind of discrete variable where everybody takes either the value 0 or 1. So we find the mean as just the percentage of success. The variance is always going to just be the percentage of success multiplied by the percentage of failure. So these two values here you multiply should always sum to 1. 0.6 and 0.4, they add up to 1. And that should always be the case when you're just multiplying probability of success times probability of failure. And then standard deviation is simply the square root of whatever you found for the variance. Remember that with a binomial random variable, we were always looking at the number of successes in a fixed number of trials. Geometric random variables are still going to require us to impose most of the conditions that we impose on a binomial random variable, except for the one about the fact that we have to have a fixed number of trials. So in order to call something a geometric random variable, each trial must be independent, so we still have to have independent trials. We have to be able to classify the outcome of each trial as a success or failure. And the probability of success has to remain constant across trials. For a binomial random variable, we had to meet a fourth criterion, which was that we had to have a fixed number of trials. So we had to decide in advance we're running exactly 5 trials or exactly 10 trials or whatever the number would be. But with a geometric random variable, we can model something like how many trials do we have to run until we get a success. And so if we think about, for example, how many times do we have to flip a coin until we get heads? Well, we might only have to flip the coin one time. We might get heads on the first flip. Or we might have to flip the coin 10 times or 100 times. And those outcomes are unlikely because we're probably going to get a heads pretty soon. But the point is that we have no idea when the first heads will occur. So we aren't running a fixed number of trials. We're running trials over and over and over again as long as it takes until we get that first success. A scenario like that is modeled by a geometric random variable. That is when we use a geometric random variable. The formula that we're going to come back to for a geometric random variable, our first probability formula, is always going to be the probability of success on the nth trial. So what this means is that we get the first success, S, to occur on the nth trial. Well, the probability of that happening is going to be equal to P, the probability of success, times 1 minus P. Remember that 1 minus P is the probability of failure, to the n minus 1 power. Remember that we're running n trials. So basically what we're saying here, because we're raising this to the n minus 1 power, is that we're multiplying by the probability of failure over and over and over again, so all the way up until the trial that results in the last failure. And then when we get our success, we multiply by the probability of success. So in other words, if we wanted to see the probability that we get our first success on the 5th trial, that would look like this. Probability of success on the 5th trial is equal to the probability of success. So let's just go ahead and write success. We mean the probability of success. But success raised to the first power times 1 minus P, the probability of failure, raised to the n minus 1 power. Well, n is 5, so n minus 1 is 4. I'm abbreviating this way and not being technical because I want to prove the point that when we're looking at the probability of getting success on exactly the 5th trial, what that means is that we failed 4 times and then succeeded on the 5th time. And that's why we multiply the probability of failure by itself 4 times, because we had 4 failures, and then multiply by the probability of success because we had that 1 success on the 5th trial. So if we wanted the probability that we'll succeed on the 11th trial, then we would raise failure to the power of 10 and then success to the power of 1, because we would have 10 failures and then our first success. Now that we understand that formula, let's look at an example. So in the example we're going to walk through, we're going to say that we're playing a game where the probability of winning a prize anytime we play the game is 0.7 or 70%, which means the probability of success is 0.7. So we say that P equals 0.7. That means, of course, that 1 minus P, the probability of failure, is 1 minus 0.7 or 0.3. So if we want to ask then, what is the probability that we don't win the prize until the 4th game? What that means is that we played 3 games where we failed and then succeeded on the 4th game. So we would calculate that probability as our first success is on the 4th game, and that's going to be equal to the probability of success, 0.7, which is always raised to the first power, multiplied by the probability of failure, 0.3, raised to the 3rd power, because we have 3 failures and 1 success to get through the 4th trial. The result there is approximately 0.0189, or about 2%. So there's approximately a 2% chance that we won't win a prize until the 4th game. In other words, that we'll fail on the first 3 games, not win the prize, and then finally win the prize on the 4th game. Now that probability calculation is fairly straightforward, but there are other probability calculations that we'll need to do for geometric random variables. So for example, we'll call this less than probability. Instead of being asked, what's the probability that you have your first success on the 4th trial, we could instead be asked, what is the probability that it takes less than 4 trials to have the first success? Well, the probability that it takes less than 4 trials means that you're either going to have the first success on the 1st trial, the first success on the 2nd trial, or the first success on the 3rd trial. One of those 3 has to be true. So we could say the probability that the first success happens before the fourth trial, or success less than 4, is going to be equal to the probability that we have the success on the first trial, or, and that means we add, the probability that we have success on the second trial, or the probability that we have success on the third trial. Keep in mind that we could also write this as probability of success less than or equal to 3, because success less than 4 means 1, 2, or 3. Less than or equal to 3 also means 1, 2, or 3. So both of these values here mean the same thing. And either way, each of these values on the right-hand side, we just go back to the formula we used before. We know success on the first trial, we know the probability of success is 0.7, so we'll just get 0.7 to the first power, but we had 0 failures because we got our success on the first trial, so we'll raise the probability of failure to the 0 power. Then here, for the probability that we get our first success on the second trial, we say 0.7 always to the first power, and then that means we failed once, so 0.3 to the first power. And then here, when we get the success on the third trial, it means that we failed twice, so we say 0.3 to the power of 2. And if we do this calculation, we get 0.7 plus 0.21 plus 0.063, and this will be equal to 0.973, or 97.3%, which means that the probability that we get our first success before we get to the fourth trial, so on the first trial or the second trial or the third trial, is 97.3%. We've got a 97.3% chance, meaning it's very, very likely that we'll get our first success on the first, second, or third trial before we get to the fourth trial. Now, really closely related to less than probability, we'll call at most probability. So let's go ahead and say at most probability. So sometimes we'll be asked a question, what's the probability that it takes you at most 4 games to get the first success? Well, at most 4 games means that you could get your first success on the first trial, or the second trial, or the third trial, but also the fourth trial, because it takes you at most 4 trials, meaning it takes you no more than 4 trials. So for example, at most 4 trials would be the probability that the first success occurs before or on the fourth trial. And keep in mind that that is the same thing as the probability that the first success occurs before the 5th trial, because everything before the 5th trial is 4, 3, 2, and 1. Everything less than or equal to the 4th trial is 4, 3, 2, and 1. So these are equivalent values, and they would both represent the probability that your first success occurs at most on the 4th trial. In other words, it takes us at most 4 games to win for the first time. And of course, we would go through and calculate these the same way we did here. We would just have to add to this string here the probability that s equals 1, s equals 2, s equals 3. We would add to that the probability that s equals 4, and we would add the equivalent value here. Now, to take the opposite perspective, let's talk about more than questions. For example, what's the probability that it takes us more than 2 games to win for the first time? Well, more than 2 is going to be s greater than 2. And keep in mind, just like before, that this is the same as the probability that success is greater than or equal to 3. Because greater than 2 is going to include the values 3, 4, 5, 6, 7, etc., all the way on to infinity. The value success greater than or equal to 3, because we have that equal to, is going to also include the values 3, 4, 5, 6, 7, all the way on into infinity. So these two are equivalent values, just like these were, and just like these were. This more than probability is a little more complicated, because how do we calculate the probability that we get our first success after the second trial? In other words, on the third trial or later. Because we can't calculate an infinite number of probabilities here, where we look at the probability that we get success on the third trial, the fourth trial, the fifth trial, the sixth trial, the seventh trial, the eighth trial, the ninth trial, on forever. We can't calculate that infinite value. So what we do is we take advantage of the fact that we know every probability distribution is going to sum to 1. So the total probability for any geometric random variable is going to have a sum of 1 or 100%. So what we do instead is we flip this around and we say that in order for us to succeed for the first time on the third trial or later, we know that that just means that we don't succeed on the first trial or the second trial. So we subtract those values from the full probability of 1. So we could say that this is equal to 1 minus the probability that we succeed on the first trial plus the probability that we succeed on the second trial. Because we know that we are not succeeding on either of these trials, but we could succeed on any trial thereafter, the third or the fourth or the fifth or any trial thereafter. So what we get here then is 1 minus, and remember we already calculated the probability that we succeed on the first trial. We found that up here as 0.7 to the first times 0.3 to the 0. That ended up being 0.7, so we get 0.7 there. And the probability that we succeed on the second trial, we know is 0.7 to the first times 0.3 to the first, because we failed once and then succeeded, and that was 0.21, so plus 0.21. If we solve this here, 0.7 plus 0.21 is 0.91. 1 minus 0.91 is 0.09, or 9%. In other words, there's a 9% chance that it takes us more than 2 games to win the first prize. Now, just like we had at most to go along with less than, we have at least to go along with more than. So if instead of being asked what's the probability that we get our success after the second game, that it takes more than 2 games to get the first success, if we're instead asked what's the probability that it takes us at least 2 games to get the first success, then that at least tells us that we have to include the second game. Because at least 2 games to get the first success means that it could take us 2 games to get the first success, but it could also take us 3 or 4 or 5 or 6 and on forever like that. But again, because we can't calculate that infinite sum, we take advantage of this 1 or 100% minus the probability that's not included. So if we said the probability it takes at least 2 games to get the first success, we would say the probability that success occurs after or on greater than or equal to the second game. Keep in mind that that's the same thing as saying the probability that success occurs after the first game, because everything after the first game is the second, third, fourth, fifth, etc. Everything greater than or equal to the second game is the second, third, fourth, fifth, etc. So these are equivalent values because they both include the second game and everything after that. So of course here we're saying because this can be equal to the second game, we're including this probability here, the probability that success occurs on the second game. So the only probability that is not included is the probability that we get the first success on the first game. So this will again be equal to 1 minus, and then just the probability of success on the first game. We know that probability is 0.7, so 1 minus 0.7 is equal to 0.3, or 30%. There's a 30% chance that it takes us at least 2 games to get the first success. The last thing I want to talk about with geometric random variables is how you calculate the mean, variance, and standard deviation for geometric random variables. The formula for the mean is going to be mu sub x, where capital X represents our geometric random variable. We sometimes also call this the expected value of the geometric random variable, capital X. And the formula for the mean for a geometric random variable will be 1 divided by p, where p is the probability of success. So if we continue on with the example we've been going through in this video, where we were playing that game and our probability of success was 70%, or 0.7, we could calculate the mean for that game, that geometric random variable, and we would say 1 divided by 0.7, and we get an approximate value of 1.43. What this tells us is that our first success is most likely to occur somewhere between the first and the second game. Now, this is a discrete variable. We can't have our first success in between the first and second game. It either has to happen on the first game or on the second game. So this is a little bit misleading, but what it's telling us is that this would be the expected value. So over time, if we play this game over and over and over again, we should expect most of our first successes to come either on the first game or the second game, somewhere in there. So that gives us an idea of the mean for our geometric random variable. And then the formula that we use for variance is, again, as always, sigma squared, and we just give this capital X to indicate a geometric random variable. That's going to be equal to 1 minus the probability of success divided by p squared. So again, we just plug in our probability of success, 0.7. So here we could say 1 minus 0.7 divided by 0.7 squared. The result there will be 0.3 divided by 0.49, and we get approximately 0.61. Then the standard deviation, of course, is just the square root of our variance. So we take the square root of sigma squared sub x, and that, of course, will be the square root of about 0.61. When we take the square root of sigma squared, we get just sigma, which is what we use for the standard deviation. And what we get is approximately 0.78. So we could say, for this example we've been working through, that the geometric random variable that defines how long it takes us to win the first prize, when we have a 70% chance of winning on any given trial or in any given game, that the mean is about 1.43 and that the standard deviation is about 0.78. We're going to be talking a little bit about sampling and studies and study design, so I just want to take a little time to talk about some of the different types of studies that you can conduct to collect data that you can then use statistics to analyze. So first of all, let's talk about sampling for a second. We already know that we can have some population with n subjects in it, and we use capital N to indicate the number of subjects in a population. But we can't always survey everyone in the population. So what we do is we take a smaller sample of the population n, and so we get this smaller sample, and the sample will have lowercase n subjects in it. So this is going to be our sample. And the goal is always that when we choose a sample out of the population, that we select people randomly. So this should always be random selection. What we're usually trying to do here is find out information about a population proportion, p, or maybe some other parameter for the population like the mean, mu. So we're looking to learn about parameters of the population, and when they're values related to the population, we call them parameters. But since we don't know them, we take a sample and then we measure statistics for the sample. So they're called parameters for the population, they're called statistics for the sample. So for the sample, we might look at the sample proportion, p hat, or we might look at the sample mean, x bar. And then, and this is the whole point of statistics, once we have information about these values for the sample, we want to try to use what we know about those to make some inference about the corresponding values for the population. So that's the goal of taking samples. That's the reason that we take samples. That's the reason that we follow this process. And we're going to follow this process. We're going to take samples of the larger population, calculate sample statistics, and then use what we know about those to make inferences about the population in different kinds of studies. And the two kinds of studies that we're going to look at here are observational studies and experiments. Now, as their names kind of imply, an observational study is where you're just observing something that's already happening. You're not affecting your population or your sample in any way. You're just making observations. Compare that to an experimental study where you're actually influencing what's going on with the people in the population or the sample. When you do something to change a population, it's called a treatment. So in an experimental study, you're applying some kind of treatment, but in an observational study, you're not applying any treatment at all. You're simply observing. An example of an observational study might be trying to find out how many students in your class prefer peanut butter over jelly. In fact, you might be interested in peanut butter versus jelly preference for your entire school, but you're going to follow this sampling process over here and just take a sample. It might be too difficult to ask everyone in your school, so maybe you just ask the people in your class only and use them as a sample to try to represent the larger population. So in order to collect that data, all you need to do is ask every person in your class whether they prefer peanut butter or jelly. And they're simply going to give you an answer. They're either going to say peanut butter or they're going to say jelly. Let's say you ask everybody in your class and 70% of the students in your class tell you that they prefer peanut butter. You've collected data about the peanut butter preference of the people in your sample, so maybe you can use that to make an inference about the population. And notice that all we've done is just ask everyone a question. We didn't do anything to try to change their minds. We didn't run any kind of experiment. We didn't put them under any kind of condition. We simply asked a question. So all we're doing is observing what their preferences are. Now this, of course, would be an example of one-way data, because we could make a table that says this many people prefer peanut butter, this many people prefer jelly, and we would get 70% and 30%. And so we would have a one-way data table. We could also, though, conduct an observational study where we collect two-way data instead of just one-way data. Maybe we could ask people about their peanut butter and jelly preference, and then also record their height. So for example, if we were going to record that data in a two-way data table, we would say people who prefer peanut butter, people who prefer jelly, and then maybe we would have a distribution here of ranges of heights. So maybe, for example, people who are shorter than 5 feet tall, shorter than 60 inches tall, anyone between 60 and 64 inches tall, anyone between 64 and 68 inches tall, and on like that. And then we could record percentages here. So we already know the peanut butter preference is going to total to 70%, but maybe this group right here is only 5% of the data. This is 20% of the data, 25% of the data here. We know that the jelly preference is going to total to 30%. Maybe this is just 2%, and then 10%, and then 7% here, and we have more data off to the right for other intervals of height. But that would be an example of collecting two-way data in an observational study, and we could be interested in trying to figure out whether or not height affects your peanut butter or jelly preference. For example, maybe we're looking to see whether or not you're more likely to prefer peanut butter if you're taller, or you're more likely to prefer jelly if you're shorter. When variables move together like that, we say that they are correlated. But there's two types of correlation. There's positive correlation, where both variables increase at the same time, so they both go up together or they both decrease together. And then there's negative correlation, where when one variable goes up, the other goes down, or when one variable goes down, the other goes up. In other words, they move in opposite directions when they're negatively correlated, or they move in the same direction when they're positively correlated. So for example, if I am more likely to prefer peanut butter, the taller I am, so as height goes up, peanut butter preference also goes up, then we might say that height and peanut butter preference are positively correlated. But if my preference for peanut butter goes up the shorter I am, then we would say that those variables are negatively correlated, because as one goes up, the other goes down. These are the kinds of conclusions that we might be able to make in a well-constructed, well-executed observational study. Keep in mind, though, that even if you see correlation between two variables, that does not necessarily equal causation. And you hear that a lot. Correlation does not necessarily equal causation. And that's because even when we see correlation, we still don't necessarily know what is causing what to happen. For example, maybe liking peanut butter makes you eat more peanut butter, which makes you taller. Or maybe if you're just genetically going to be taller, something about being taller causes you to like peanut butter more. Or there can be another what we call confounding variable, which is some third variable that's causing both of the others. For example, maybe being male causes you both to be taller on average and to like peanut butter more. And so these things are correlated simply because they're both more likely to occur in males, and gender is what is confounding these results. So in general, just remember that when we do an observational study, we're simply collecting either one-way data or two-way data, and at best looking for correlation between variables. If we want to try to find causation, we need to do an experiment. We can't just do an observational study. Experimental studies are what we do when we're actually manipulating something that's happening. When you have an experiment, you're going to be dividing people into multiple groups, so at least two groups, but it could be more, and you're going to be treating them differently. So you're going to have at least two groups. So let's say we have one group here, and we have one group here. One group we call the control group, and the other we call the treatment group. Now, the classic example here of an experimental study is when you're testing out a new pharmaceutical drug. For example, maybe you're testing a new drug and you want to see if that drug has an effect on blood pressure, specifically if it decreases blood pressure. And for a study like that, you'll split your participants into the control group and the treatment group. The treatment group is going to receive the new drug, so they get the drug. The control group will not get the drug. However, you give them what's called a placebo or a sugar pill so that nobody can tell who's getting the drug and who's getting the placebo. If everybody gets a pill that looks the same, then the participants don't know if they're in the control group getting a sugar pill or if they're in the treatment group actually getting the drug. The goal is to try to control as much bias as you can. So for example, if we didn't give the control group any placebo, they would know that they're not getting the drug. And so maybe the fact that they think that their blood pressure isn't going to get any better because they're not receiving the drug actually affects what happens in their body. Or the treatment group, if they know that they're the only ones getting the drug, maybe their positive thinking about the fact that this might help them actually is what's causing them to get better. But if we give the control group the placebo pill, then we'll be able to rule out the participants' expectations as something that might be biasing the result of our study. When we do this, it's called a blind experiment. And we can even do a double-blind experiment where the people who are administering the drug and the placebo pill don't even know which pill they're giving to the participants. If they did know, maybe the way that they interact with the participants, maybe their body language or the things that they say or their facial expressions give the participants an idea of whether or not they're getting the placebo or the drug. But if the people administering this treatment don't even know which pill they're administering, then that's a double-blind study. It helps us to eliminate more bias. The goal, of course, of a study like this is to see whether the people who receive the drug have a more positive outcome than the people who do not, for whatever outcome it is that we're hoping for. Sometimes with experiments, you can do things like create a matched pairs experiment. Because, for example, if we just randomly select, again going back to random selection, if we just randomly select from our entire group of participants 50% of the people to be in the control group and 50% of the people to be in the treatment group, it might turn out that there are many more women in the control group and many more men in the treatment group. Again, if we're just doing complete random selection, we're not controlling it all for gender, so we could easily end up with many more women in one group and men in the other. We could also see the same thing with age. If we have a wide range of ages in our experiment, Maybe the control group ends up being much older on average than the treatment group. So in order to control for things like that, we do what's called blocking, or we create a matched pairs experiment. So for example, if we wanted to block on gender, we would divide all of our women and all of our men, and then we would randomly sample from the women, putting half in the control group and half in the treatment group. And then we would randomly sample from the men, putting half in the control group and half in the treatment group. And that would help us to potentially rule out gender as some kind of confounding variable that is maybe skewing our results if we don't have an even number of women and men. Or we could block on age as well, putting an equal number of each age group in both the control and treatment groups, but still random sampling within each age group to place people in the control and treatment groups. When we do a matched pairs experiment, we're just blocking on one or more things that are important to us. So for example, I would want to find a matched pair of 18-year-old females, and I would put one 18-year-old female in the control group and one 18-year-old female in the treatment group. And then I might have another pair of 22-year-old men, and I would put one of the 22-year-old men in the control group and the other 22-year-old man in the treatment group. Basically, we're finding pairs of people and splitting them up into the control and treatment groups so that each participant has their matching pair in the other group. So there's all kinds of things like that that we can do to help eliminate bias from an experimental study like this one. And then the last thing we want to talk about is replication. We always want to make sure that no matter what kind of study we do and how we run it, somebody else could come along behind us and easily replicate our study. So we want to follow a specific procedure, we want to record everything that we do, and we want to be really precise in the hopes that somebody else can run the same study with a different set of participants, but a set that mimics our original set based on the criteria that we've specified. And we want other people to be able to do that to replicate our study so that they can replicate our results. Because if we run our peanut butter versus jelly observational study or our blood pressure medication experimental study, and we come up with results where maybe in our experimental study we say, yes, the blood pressure medication does decrease blood pressure, or in the peanut butter versus jelly study, we find that being taller is positively correlated with peanut butter preference. It's great that we were able to find that, but it's possible that the results could still be biased or because of something that we did with the specific way that we ran our study. But if somebody else comes along behind us, runs the same study, and finds the same results, and people can do that over and over and over again, now we have more evidence that our results are in fact legitimate. We talked about having a population with n subjects in it. So this is our population. And taking a random sample of that population to get some smaller sample with lowercase n subjects in it. And it's this process right here that I'm drawing with the arrow that we're going to be talking about in this video. Because what we always try to do is randomly select people from the population for our sample. So we're hoping that this is random selection. If this is perfectly random selection, then we're hoping that we eliminate bias from the sample. And the goal is to get a perfectly representative sample. Because if the sample does perfectly represent the population, then when we calculate information about the sample, so when we look at the characteristics of the sample, or the sample statistics like the sample proportion p hat, or the sample mean x bar, then we can use that information to make inferences about what we're really interested in, which are population parameters like the proportion p or the mean mu. If the sample is perfectly representative, then basically we can just take our results for the sample statistics and scale those up to the population because we know the sample does a perfect job representing all of the people in the population. So an easy example of that could be, let's say I have a fruit salad. I have a bowl of fruit salad like this, and the bowl holds 20 cups of fruit salad. If the fruit salad is perfectly mixed, then every little 1 cup section should have the exact same ratio of pineapple to strawberries to grapes to apple slices, whatever, in that cup. If I take another cup as a sample and take that out, it's going to have the exact same ratio of fruit as the other cup. And all 20 cups in here, if I take them out, they're going to have the exact same ratios of fruit because the fruit salad is perfectly mixed. So if I were to take one of these cups out and it's a representative sample, let's say I take the 1 cup out and I find that there are 2 strawberries in the 1 cup. So I would say there's 2 strawberries in 1 cup of fruit salad. And if I know that the fruit salad is perfectly mixed together and every cup is identical, then I could say that there are 20 cups total in the fruit salad. So how many strawberries are in the full fruit salad? Well, really what I just have here is 2 over 1 equals x over 20, or I could write that as 2 is equal to x over 20. I could multiply both sides by 20 to get 40 is equal to x. So I would know that there are 40 strawberries in the fruit salad. But that's only the case if this 1 cup that I took was a perfectly representative sample because the fruit salad was perfectly mixed. But if more of the strawberries are in the bottom of the bowl down here, and I take a 1 cup sample from the top, I may not get a representative number of strawberries. So that's the reason that we're looking for a perfectly representative sample. We want to just be able to take what we know about the small sample and scale it up to the population or make inferences about the population. And this is a really simple example, but a lot of the times the reason that we don't have a representative sample is because of what's called bias. And really, there are 3 main kinds of bias that we want to talk about. There is response bias, there is what's called undercoverage, and there is non-response bias. Response bias basically means there's something wrong with the way that we collected the data. For example, we could have broken tools or tools that are not calculated correctly. For example, if we're collecting data about temperature, but our thermometer is broken, we're going to have measurement bias. There's something wrong with the tool that we're using. So the responses that we're getting from our subjects are going to be biased. This could also be something like an embarrassing question or a question that people don't want to answer. For example, if I ask the question on a survey, have you ever stolen something? People might be incentivized to lie because they're embarrassed about giving a truthful response. Or if you have something like biased wording in a question that makes people want to answer a certain way because you have a judgment already in the question. Like, have you ever rudely interrupted someone when they were talking? Somebody might see that and think, well, I don't want to be rude, and so they don't answer truthfully. Even if they have interrupted somebody, they say that they haven't because they don't want to be rude. So you have this biased wording that creates a judgment that incentivizes them not to respond truthfully. So all of these things are really about the instruments that we're using to measure, whether it's a survey or whether it's some kind of tool like a thermometer or a ruler or something. There's something about the data collection tools that we're using that's going to cause us to get some kind of biased response. We lump all those together in what's called response bias. Undercoverage is when we leave out a large group of people. So, for example, if I run a daycare center and I want to learn about the income of the parents of the children who I take care of, I could maybe ask those parents as they show up to pick up their children how much money they make on an annual basis. Well, if I only ask the first 5 people who come to pick up their kids, maybe the people who get off work the earliest make the least amount of money because they work the least. Or maybe they make the most amount of money because they're in a financial situation now where they don't have to work as much. I'm leaving out the whole group of people that come later to pick up their kids. So I'm really getting a biased look at the annual income of my parents. So basically what we're doing here is we're leaving out a group of people, but my daycare example might be called selection bias. Another example of undercoverage would be voluntary response sampling. So voluntary response sampling, which is when I only get responses from people who choose to respond to my study. Well, if I'm only getting people who voluntarily choose to take my survey or respond to my study in some way, they might be responding for a reason. Maybe they have more time on their hands. Maybe they're more enthusiastic or passionate about whatever it is that I'm trying to survey. Maybe they have access to resources that allow them to take my survey, whatever it is. But basically, I'm leaving out the entire group of people who, for whatever reason, choose not to respond to the survey. So I'm introducing bias there if I'm just going off of voluntary response sampling. And then you have convenience sampling, where I'm just sampling people based on whatever is convenient for me. So maybe I want to ask people about their eating habits. Well, if I just go stand outside a healthy grocery store and ask everyone who walks out the door about their eating habits, because that happens to be convenient for me as the researcher, I might get a totally different picture of the results compared to if I go stand outside a fast food restaurant, because that's more convenient for me. I'm potentially really skewing my results either way. So these are all slightly different examples of undercoverage. I'm just leaving out a group in one way or another. And then the last one is non-response bias, which is similar to undercoverage, but basically it's just that there are a lot of people who didn't respond to my survey. We specifically call this out when we have something where maybe we do a poll and 98% of the people that we asked don't respond to our poll. Our biggest problem there by far is non-response. It may be true that there are other kinds of bias in our data. So for the 2% that did respond, maybe there was some kind of biased wording issue we have to be aware of. But a little issue in our 2% pales in comparison to the fact that we didn't get 98% of people to respond to our survey or our poll. Our biggest issue by far is non-response. So if that's the case, we want to specifically call out non-response bias to indicate that that may be an issue that's skewing our results. Now, regardless of the kind of bias that we have, we always want to be able to think about the direction of the bias, what's called the direction of the bias. And basically, we're just paying attention to the direction in which our results might be skewed. So going back to our grocery store example where we stood outside the grocery store asking people about their healthy eating habits, maybe we are trying to get an idea of how many servings of fruit per day the average American consumes. But we just went and stood outside the healthy grocery store and asked the people who walk out how many servings of fruit they consume on average per day. What we would want to say is that because we used convenience sampling and we stood outside the healthy grocery store, we would expect that the participants in our survey eat more fruit on a daily basis than the average American because we're standing outside a healthy grocery store. So what we would want to say is that we might be overestimating the number of servings of fruit per day that the average American eats because of the way that we sampled. Maybe in another instance, we are underestimating, for example, here with our biased wording when we asked people if they had ever rudely interrupted someone or if they had ever stolen something. We might say that the number of people who answered yes to either of those questions is actually still an underestimation of the true proportion of people who have done that, because people will be inclined to answer no when truthfully they should have answered yes. So that might be an underestimate versus the grocery store example might be an overestimate. We always want to be aware of the direction of our bias. So given that there are so many ways to introduce bias, what do we do to try to avoid this kind of bias and get a good, unbiased representative sample? Well, one way is to use a random number generator on a computer. Just give everyone a number, so assign every subject in our population or everybody that we can ask a random number, and then use a number generator to pick out random numbers, and then the numbers that it spits out are the ones that we include in our sample. Doing something like that is what's called a simple random sample, which we often abbreviate as an SRS, a simple random sample. While that would be completely random selection, what we're talking about over here, totally random selection to get the subjects that we are going to use in our sample, this can still give us a biased result. Because like we talked about in the types of studies video, we could, for example, take a population of 50 men and 50 women and use a random number generator to split them into two groups. While that would be completely random and a simple random sample, that random number generator might just happen to divide our men and women into groups of 40 men and 10 women, and then 10 men and 40 women for group number 1 and group number 2. And that might skew our results because the men and women are so skewed across the two groups. So in order to fix things like that, we can do what's called a stratified random sample. And that's where we would do something like take our 50 men and we would use a random number generator to randomly divide them into two groups such that in group number 1, we have 25 men, and in group number 2, we have 25 men. But we split them up randomly using a random number generator. And then we take our 50 women and we divide them into the two groups, 25 into group 1 and 25 into group 2. We still used a random number generator to split them up, so the way we split the women was completely random. But now, because we've separated the men and the women, we have 25 men and 25 women in each group, so that's a stratified random sample that will help us control for an effect that gender might have on our survey or the study that we're doing. And then sometimes we'll do what's called a clustered random sample. And that's where we have a mix of samples. We create little clusters of samples, and then we pick small groups to be in our sample. So an example here would be instead of 50 men and 50 women, splitting them up into men and women, and then assigning 25 men and 25 women into each of two groups, we might create 10 groups first, each with 5 men and 5 women. And then each of these groups is a cluster. Then maybe for our sample, we just select 5 of these 10 groups, or 5 of the 10 clusters, these are really clusters, and we sample all the people in those 5 clusters. So there are lots of different ways to go about sampling, but the overall idea is that we want a random sample that avoids as much bias as we possibly can, and maybe depending on what kind of study we're doing, controls for things like gender or age or some other kind of variable that might confound our results, because it's getting a random sample, a truly random sample, that allows us to get an unbiased look at sample statistics that we can then use to make inferences about population parameters. We've already talked a little bit about how we can use a sample to estimate characteristics about a population. So let's just review really quickly that when we have a population, but the population is too big or spread out or inaccessible in some way for us to survey everyone. Therefore, what we do is we take a random selection, so we'll put here random selection of people or subjects, whatever's in the population, of people from the population. We randomly select those in order to create our sample. Now, what we're interested in is some parameter value for the population. And this could simply be a proportion of the population, a population proportion. it could be the mean, it could be the standard deviation, but there's some characteristic about the population that we want to find. But since we can't ask everybody, we take a random selection in order to get our sample. And then for the sample, we calculate what's called a statistic, which again could be a proportion for the sample, it could be the mean, the standard deviation, but some characteristic of the sample. So we call characteristics of the sample statistics, and we call characteristics of the population parameters. And then our goal here is to use what we learned about the statistic to make an inference about the parameter. In other words, maybe we find the sample mean, and we want to use what we know about the sample mean to then make an inference about the population mean, the corresponding population parameter. This is the general process that we're going through. So let's, for example, talk about the population proportion. When we talk about the proportion, we're just talking about the number of subjects in our population or our sample that meet a certain criteria. So when we say population proportion, we're talking about the number of people in the population that meet a certain criteria. For instance, if we want to know how many students in our school have brown hair, then the population proportion, which we call P, will be the number of students in our school with brown hair divided by the total number of students in our school. But let's say that there are 5,000 students in our school. And so because there are so many, we're not going to be able to survey every single one of them to see exactly how many students in the population have brown hair. In that case, we might take a random selection of 100 students to get a sample, and then survey just those to see how many of them have brown hair. What we'll get is the sample proportion, the proportion of students in the sample with brown hair, and we call the sample proportion P hat. Here's the thing though, if we take a sample of 100 students, and then we count the number of those 100 who have brown hair, we might get a value of, let's say, 60. So we would say 60 divided by the 100 students in our sample is 0.6. And so we get a value for P hat of 0.6, and the sample proportion is 0.6. But then let's say we take a different sample of 100 students, and 48 of them have brown hair. In that case, for that sample, we would say P hat is 0.48. And then maybe we take a third sample of 100 students, and we find that P hat is 0.71. 71 of the 100 students had brown hair. The point is that every time we take a sample, we may get a different value for P hat. The sample proportion is going to be different. So the question then is, if we're always going to get a different value for P hat, how do we use our value for P hat to make an inference or estimate the value of the population proportion P? Well, what we do is we take more and more samples, and as we take those samples, we're going to come up with lots and lots of values for P hat. Well, when we take all of those values for P hat and we consider them all together, what we're going to get is the sample distribution of the sample proportion, because this is the sample proportion here. So we're getting lots and lots of values for the sample proportion, and those values are going to create a probability distribution, sample distribution, that we can use to answer probability questions about P hat and therefore about P. The amazing thing is that if we do this right, the sampling distribution of the sample proportion is actually going to be a normal distribution. However, in order for the sample distribution of the sample proportion to be normal, we have to meet a few conditions. So the first one is that the sample needs to be random. So we need to have a random sample. And we saw up here that we did a random selection of people to get the sample from the population. That has to be true. The sample needs to be random. The second thing is what's called the normal condition. And the normal condition says that we have to have at least 10 successes and at least 10 failures in our sample. So what do we mean by successes and failures? Well, like in this example, we're looking for the proportion of students with brown hair. So we could call having brown hair a success and not having brown hair a failure. And so what we want to say then is that when we multiply the number of students in our sample, n, by the population proportion P that we're going to get at least 10. So this says we get at least 10 successes. The number of students in the sample multiplied by the probability of failure, 1 minus P, also has to be greater than 10, so that we get at least 10 failures. Now, sometimes in the problems you'll be asked to solve, you'll be given the population proportion, in which case you can use it in these formulas. If you don't know the population proportion, then that probably means you're working with just one sample, and you'll use that sample proportion in place of the population proportion. So for instance here, if this was our single sample, we had calculated a sample proportion of 0.6, then we would take 0.6 times 100 to get 60. That would show us that we're getting 60 successes, which is greater than 10, so that checks out. And then we would take 100 students in the sample, n, times 1 minus 0.6, or 100 times 0.4, and we would see that we're getting 40 failures. That's also greater than or equal to 10, so we're good there. We would have met the normal condition. So we just have to check those two. And then lastly, we need to satisfy the independence condition. The independence condition tells us that our samples need to be independent, and that can happen in one of two ways. If we are sampling with replacement, then automatically our samples are independent. If we're sampling without replacement, for example, we're asking students as they leave the building at the end of the school day, then we're sampling without replacement. And if that's the case, that's okay as long as we are keeping our samples under 10% of the total population. So our total population is 5,000 students, and 10% of that is 500 students. So if we're sampling without replacement, then the largest sample size we can take is 500 students. But since our 100 student samples are underneath that threshold, then we can still get away with sampling without replacement because that 10% threshold is actually going to approximate independence for us. So in this case, we've met the three conditions for normality: random sample, normal condition, independence condition, which you can remember is also called the 10% rule. Then if those three things are true, that means that the sample distribution of the sample proportion is going to be approximately normal. So because we have an approximately normal distribution, that means that we can identify here in the center of the distribution the mean of the sample proportions. And the amazing thing is that this is actually going to be equal to the population proportion P. We're also going to be able to find the standard deviation of the sample proportion, which, because it's the standard deviation for the sample, we oftentimes call it the standard error of the proportion. And that standard error formula is going to be sigma is equal to, and then the square root of the population proportion times 1 minus the population proportion divided by the number of subjects in our sample. Now keep in mind that for some problems, you're going to have the population proportion P, in which case you'll want to use that. But other times, you're not going to have the population proportion, and in that case, you can substitute the sample proportion P hat for this population proportion P. So let's go through an example. Let's say that we have an ice cream shop that claims that 40% of their 1,000 daily customers purchase a waffle cone with their ice cream. You decide that you want to verify this claim, so you're going to take a simple random sample of 90 of their customers. And what you'd like to know is the probability that the sample proportion, the proportion of people in your 90% sample who buy a waffle cone, is going to be within 5% of their claim of 40%. So like we talked about before, the first thing we want to do is verify normality. So we want to look at our three conditions. Well, the first is random sample, and we were told that we took a random sample. So we're kind of assuming that. So we have met that condition. The second is the normal condition. Are we going to have at least 10 successes and at least 10 failures? Well, we're taking a sample of 90, and we've been told that the population proportion is 40%. So NP will be 90 times 0.4, and that's 36, and that is in fact greater than or equal to 10, so we will have at least 10 successes. And then n times 1 minus p will be equal to our sample size 90 multiplied by 1 minus the population proportion 0.4, and that's 0.6. So 90 times 0.6 is 54, and that is also greater than or equal to 10, so we will have at least 10 failures. So we have met the normal condition. And then the independence condition, we're not sampling with replacement, we're just asking 90 customers who come out of the store. However, our 90-person sample is underneath the 10% threshold because 90 divided by the total number of customers, 1,000, is equal to 9%. So because we've stayed under this 10% threshold, we can assume independence, and therefore we've met the independence condition as well. So now we can go about the business of answering the probability question now that we've verified normality. The first thing we want to do is find the mean of the sample proportion. But we know that the mean of the sample proportion is going to be equal to the population proportion. So we can say that the mean of the sample proportion will also be 0.4. Then our standard deviation is going to be equal to, we have the formula over here, the population proportion, so square root 0.4 times 1 minus 0.4, which is 0.6. In other words, here in the numerator, we have the probability of success multiplied by the probability of failure. And then in the denominator, we have n, which is the size of the sample, and our sample size was 90. If we calculate that value, we get 0.0516, and now we have mean and standard deviation of the sample proportion. Our question is, what's the probability that the sample proportion is going to be within 5% of the population proportion? Well, if we sketch here our mean, we know that the mean is 0.4, so let's say this is 0.4. And then we want to know the probability that we're within 5% of that. Well, 5% is 0.05. So within 5% would be between 0.45 on the high end and 0.35 on the low end. So we're really asking, what's the probability that we fall within this interval? Well, we know that the standard deviation is 0.0516, just a little bit more than that 0.05 distance we're talking about. So what we want to do is express this 5% value, the 0.05 value, in terms of standard deviations. So we would take 0.05 and we divide that by our standard deviation, 0.0516. And what we get is approximately 0.97 when we calculate this fraction, which means that this value here of 0.05 that gets us from the mean up to 0.45, or that gets us from the mean down to 0.35, it's about 0.97 of a standard deviation. So it's almost one full standard deviation, but not quite. But now that we have this in terms of standard deviations, we can actually look this up in a z-table to figure out our probability. So we're really looking for the probability that we stay within negative 0.97 and positive 0.97 in our z-table. Now, if we look up positive 0.97 in our z-table, we get a value of 0.8340. And if we look up a value of negative 0.97 in our z-table, we get 0.1660, which really means that the probability that we are less than positive 0.97 is all of this area here, and that probability is 0.8340. But then the probability that we're less than 0.35, which is a z-score of negative 0.97, is 0.1660. So this probability right here, up to this point, is 0.1660. So what we want to do is we want to subtract the 0.1660 from the 0.8340 to just give us this value in the middle right here. The result then of that difference is 0.668, or if we round to the nearest hundredth, we get approximately 67%, 0.67 or 67%. In other words, what this tells us is that there's an approximately 67% chance that the sample proportion p hat of any 90-person random sample we take is going to fall within 5% of the population proportion p. In other words, given this particular sampling method, we have about a 67% chance of being within 5% of the ice cream shop's claim. Remember before that in order to get an estimate of the population proportion p, we took samples of the population and calculated for each of those samples the sample proportion p hat. And then we were able to create the sampling distribution of the sample proportions p hat and find a mean and a standard deviation for the sampling distribution of the sample proportions, which allowed us then to make inferences about the population proportion p. Well, the sampling distribution of the sample mean is, as you might imagine, really similar, but instead of talking about a proportion, we're just talking about the mean. In other words, if we again take samples of the population and we calculate the mean of each sample, which we call mu sub x bar, and then we graph all of those means in a distribution, they're going to form the sampling distribution of the sample mean. And that distribution is going to show us how likely it is that we get a particular value for this sample mean. Now, this all revolves around the Central Limit Theorem, which we often abbreviate as the CLT. The Central Limit Theorem is hugely important to us in statistics because normally when we're dealing with distributions for a population, distributions aren't usually perfectly normal. They don't usually approximate that bell-shaped curve. They can be skewed to the left, they can be skewed to the right, they can be uniform, they can be all kinds of weird shapes that are non-normal. But the Central Limit Theorem tells us that even when a population distribution, so the distribution for the population, is non-normal, its sampling distribution of the sample mean will be normal if we use a big enough sample. In order to be a normal distribution, though, we have to meet a few conditions, just like we did when we were finding the sampling distribution of the sample proportion. So the first one is that we have to have random samples when we're choosing samples out of the population. The second one is that we have to meet the independence condition, or the 10% rule. And again, we'll meet the independence condition if we're sampling with replacement. If we're sampling without replacement, then we just have to make sure that our sample size stays under 10% of the population. If we stay under that 10%, then our samples are small enough that it approximates independence. But either way, one way or the other, we have to meet that independence condition. And then the third one is that we need more than 30 samples. Now, this one has a couple of caveats to it as well. So if the distribution of the population is normal, so if the population is already normally distributed, then we can take a smaller number of samples if we want to, and the sampling distribution of the sample mean will still be normal. That's because the population distribution was already normal. But if the original population distribution is non-normal, then we have to take at least 30 samples in order for the central limit theorem to do its work, in order for the central limit theorem to turn the sampling distribution of the sample mean into a normal distribution, even though we started with a non-normal distribution. If we start with a left-skewed distribution and we use fewer than 30 samples, then the sampling distribution of the sample mean will also be left-skewed. If the original population distribution was right-skewed, and we use fewer than 30 samples, then the sampling distribution of the sample mean will also be right-skewed. So in order for the sampling distribution of the sample mean to be normal, we have to take at least 30 samples unless we already know that the original population distribution was normal. Now, if we meet those three conditions, then we will have a normally distributed sampling distribution of the sample mean, and then we can say that the mean of the sampling distribution of the sample mean will be the same as the mean of the population. So, in other words, the mean of the sampling distribution will be equal to the original mean of the population. We also know that the standard error of the sampling distribution of the sample mean will be equal to the standard deviation of the original population divided by the square root of the sample size. So let's walk through an example together. Let's say that we have a soccer ball factory. We have a company that produces soccer balls. And as you can imagine, since this is a whole soccer ball factory, they make a lot of soccer balls. And they try to fill each soccer ball to 8.7 pounds per square inch of pressure. So when they fill it up with air, they try to fill it to a mean of 8.7 pounds per square inch. And they have a standard deviation of 0.4 pounds per square inch for all of their soccer balls. So we would call 8.7 mu the mean of the original population, and we would call 0.4 the standard deviation of the original population. Now, the company's doing some quality assurance, and so they randomly select 25 soccer balls, and they're going to go ahead and check the pressure. And they want to know the probability that the mean amount of pressure in these balls is within 0.2 pounds per square inch of the population mean. So the first thing we need to do is check normality. And we were told in the problem that we took a random sample of 25 balls. So we can go ahead and assume that we've met that condition. And then when we took these 25 soccer balls, we sampled without replacement. We took 25 off of the line. We didn't put each one back every time we took it. So we're sampling without replacement. However, we can assume that since this is a soccer ball company making soccer balls in a soccer ball factory, that they make more than 250 soccer balls. So this is going to be under the 10% threshold, and we can go ahead and assume independence even though we're sampling without replacement. While we're not taking more than 30 samples, we're only taking 25 soccer balls. Let's say we've been told in the problem that the pressure in the soccer balls is normally distributed. In other words, the original population is normally distributed because the pressure to which they fill each soccer ball follows a normal distribution with a mean of 8.7 and a standard deviation of 0.4. So we'll meet this condition as well, and now we can go about answering our probability question. We know that the mean of our sample is going to be equal to the mean of the original population, so our mean is going to be 8.7. The standard deviation of the sampling distribution is going to be equal to the original standard deviation, 0.4, standard deviation of the population, divided by the square root of our sample size, so the square root of 25. And we'll calculate that that is 0.08. Now, since we want to know the probability that our sample mean is within 0.2 of the population mean, we need to express 0.2 in terms of standard deviations. Well, we know that one standard deviation is 0.08. So if we take 0.2 divided by 0.08, we get 2.5, which means that, let's say we have this normal distribution here. We know the mean is 8.7. This is the sampling distribution of the sample mean. So our mean is 8.7. And then we know one standard deviation is 0.08. So if this is the mean here, then one standard deviation, 0.08, might be here. Two standard deviations, 0.16, might be here. And then 2.5 standard deviations is going to be right here. And then same thing on the low end. We'd have one standard deviation. This would be 0.08 from the mean of 8.7. And then if we go one more standard deviation of 0.08, now we're going to be 0.16 away from the mean, and then 2.5 standard deviations might be right here. So since we're 2.5 standard deviations away, this is a z-score of -2.5 and a z-score here of 2.5. So we're looking for the probability that our z-score here is between -2.5 and +2.5. And if we look up +2.5 in a z-table, we find 0.9938. If we look up -2.5 in a z-table, we find 0.0062. Of course, this 0.9938 is going to give us all of this area here, all the way up to a z-score of 2.5. The z-score of -2.5 is going to give us all of this area right here up to a z-score of -2.5. So in order to find the value we're interested in, which is all the area in between those two, this area right here, we just want to take the 0.9938 and then subtract out the 0.0062. That subtracts out this little lower tail, leaving us with just the area in the middle that we want. And that difference is 0.9876. And then if we round that to the nearest hundredth, approximately 0.99 or 99%, which means that when we use these sampling conditions with the 25 soccer balls, that our sample mean has an approximately 99% chance of falling within 0.2 pounds per square inch of the population mean of 8.7 pounds per square inch. As you may have suspected by now, when we do statistics, it's not very often that we can prove something outright. This usually does not happen. What we can do is provide support for a hypothesis that we have. We can find evidence that supports our hypothesis. We can be reasonably confident, or we can have a certain level of confidence in our data, in our statistics. And so statistics is all about being as confident as we possibly can in order to provide support for a hypothesis that we have. But we usually can't prove that hypothesis beyond all doubt. And at this point, we're sort of bringing everything together. We always start out with a hypothesis. We also call this the alternative hypothesis, and so we'll usually denote it with a capital H and then a little a. And this is our statement of expectation. You can think about it that way. So what do we expect to happen, or what do we suspect is happening? What do we believe to be true? So for example, a hypothesis might be that students at Springdale High School, so Springdale High School, perform differently on the SAT test than students at Greenville High School. Once we have a hypothesis, a statement about what we expect to happen or what we believe is already happening, something that we suspect is true, we always then want to come up with what's called the null hypothesis. And we usually denote that as a capital H and then a 0. The null hypothesis is always just the opposite of whatever the hypothesis is. So in this case, we said that the hypothesis was students at this high school perform differently on the SAT test than students at this high school. So the opposite of that would just be that they do not perform differently. Students at Springdale High School do not perform any differently on the SAT test than students at Greenville High School. So notice how these are opposite of each other, and that'll always be true for the alternative and null hypotheses. We can also put these into notation. So we could say that our alternative hypothesis is just that the mean of test scores on the SAT for Springdale High School students is not equal to the mean of test scores on the SAT for students at Greenville High School, because the alternative hypothesis, we said they perform differently, which means that their means must be different. The null hypothesis, on the other hand, we would say H sub 0, the null hypothesis, would be that they perform the same. They do not perform differently. So we could say the average score on the SAT for students at Springdale High School is equal to the average score for students at Greenville High School. Now we'll get into this more later, but this is called a two-tailed test because we haven't indicated the direction of performance. We haven't said that students at Springdale perform better or worse than students at Greenville. We just said they perform differently, meaning that the means aren't going to be equal to one another. They're just going to be different. Something like that would be called a two-tailed test because there's no direction indicated in terms of one being more than the other or vice versa. But if we said instead that students perform better or worse, so maybe we say here, students at Springdale High School perform, let's say, better on the SAT than students at Greenville High School, then that would be our alternative hypothesis, and our null hypothesis would have to be changed to reflect that. So we would say that students at Springdale High School do not perform better. We wouldn't necessarily say perform worse because they might perform worse or they might perform equally. The null hypothesis is just strictly refuting whatever the alternative hypothesis is. So here, if they perform better, then for the null hypothesis, it's just they do not perform better. They do not do whatever we said they would do up here. Then we could say that if students at Springdale perform better, then that means our alternative hypothesis would need to be the mean of the Springdale scores is better, greater than the mean of the Greenville scores. In that case, then, for the null hypothesis, do not perform better, we would just leave this as an equal sign. The interesting thing about hypothesis testing is that once we write our hypothesis and our null hypothesis, and we have the notation for those two, what we're actually going to do is test the null hypothesis. So even though the alternative hypothesis is really the one that we're interested in, we always end up testing the null hypothesis. So this is actually going to be what we're going to test. And there are always only two possible outcomes when we test the null hypothesis. Either we reject the null hypothesis or we do not reject the null hypothesis. We'll talk about in a second how we go about doing that. But if we reject the null hypothesis, that's going to lend support, again, not prove, but just support our original hypothesis. Because think about this example. We hypothesize that students at Springdale do better than students at Greenville. Therefore, the null hypothesis was students at Springdale don't perform any better than students at Greenville. Well, if we are able to do some statistics and gather some data that allow us to reject the null hypothesis, we're saying this is not true. We were able to show that this is not true, which therefore, if we're showing that it's not true that students don't do any better, then what we could infer is that it might be true that students do perform better when they come from Springdale instead of Greenville. So rejecting the null hypothesis is going to lend support to or provide evidence for the alternative hypothesis, the original hypothesis that we wrote. So rejecting the null hypothesis is how you lend support to the idea that you're investigating. If we aren't able to reject the null hypothesis, then that just means that the data we found or the test we ran, the conclusion we came to, was that we couldn't find any evidence to support the hypothesis. That doesn't necessarily mean that the hypothesis is true or that it's not true. We just didn't find any evidence to support it because we were not able to reject the null hypothesis. So now the question becomes, how do you go about rejecting the null hypothesis, or when would you not reject the null hypothesis? Well, what you want to do before you start your test is you want to pick a probability level. So let's say that we pick a level of 10%. When we say 10%, what we really mean is that we're setting a kind of threshold where we say we will only reject the null hypothesis if when we collect data on SAT scores for students at Springdale High School, we're going to take a sample of the students at Springdale, we're going to look at their SAT scores, and then we're going to find a mean for those SAT scores. So we're going to find mu sub s, the mean of SAT scores for our sample of Springdale High School students. What we're saying with that 10% is that we're setting a threshold such that that mean score on the SAT is unlikely enough, it's high enough, that the chances of getting that score from a random sample of Springdale students is going to be less than 10%. In other words, we would expect to get that value only 1 in 10 times, or only in 1 out of every 10 samples. That's that 10% number. So we're setting kind of a high bar for ourselves and saying that if we get this result that's really uncommon, it only happens 10% of the time, then what that tells us is that we got a really exceptional result. The SAT scores for the students at Springdale is so significantly higher than the scores for Greenville High School students that we would only expect that to happen 1 out of every 10 times. And if that feels good enough to us, that it feels like it provides strong enough evidence, then that's the bar that we're going to set for ourselves as the level at which we reject the null hypothesis. So we'll say then that if we get a mean for the Springdale students that meets that 10% threshold, then we will reject the null hypothesis and conclude that we've been able to provide some support for the alternative hypothesis that Springdale students actually do perform better than Greenville students. Now, what that looks like when we're actually doing the math is that we look at the 10% probability threshold as a z-score. Now, since we're looking to see that Springdale scores are higher than Greenville scores, if we imagine this as a normal distribution, and we have this 10% threshold, then what we want to do is look at the z-score here that is associated with this top 10%. So we want this here to be 10% of the area under the curve, and then we're looking for this z-score right here that's the boundary for this 10% level. Keep in mind that if this is 10%, then all the area to the left of this line here is 90%. So we could look in a z-table, look in the body of the table for 90% or 0.9000, and if we look for that value, we find a z-score of approximately 1.29. So a z-score of 1.29. So that tells us that to be above 90% or in the top 10%, we need a z-score of 1.29. We call this value here for z the critical value, and it is the dividing line between the region of rejection where we reject the null hypothesis, so region of rejection. And again, this is a good thing because if we find a score that's in this top 10% here of probability, we're within the region of rejection, we can reject the null hypothesis and therefore provide support for the alternative hypothesis. So it's the dividing line between the region of rejection and the rest of the area here, which is the region of acceptance. And this is the region where if we find a data point within this region, then we accept the null hypothesis and we do not get evidence that supports the alternative hypothesis. We'll talk about this more when we talk about one- and two-tailed tests, but keep in mind that this was a one-tail test where this 10% threshold of probability all gets allocated to one tail of the distribution, creating just one tail here for the region of rejection, and that's because in our hypothesis we said Springdale students perform better than Greenville students, as opposed to just saying Springville students perform differently, in which case we would have done a two-tailed test, but we'll talk about that more when we talk about one- and two-tailed tests. When we talked about hypothesis testing, we talked about how we can either test that one value will be different than another value, and in that case we could maybe say something like the means will be different than each other, And then we talked about hypothesizing that one value might be greater than or better than or something another value. And in that case, we might say greater than or less than. But in the case of hypothesizing that two values are different than one another, we call that a two-tailed test, or sometimes a two-tailed test, a two-sided test, or a non-directional test, because this kind of hypothesis doesn't have any direction. We're not saying one value is better than another, or vice versa. We're just saying that two values are different than one another. So in a distribution, that might be something like this. Maybe we have one mean here, and we're hypothesizing that the other mean is different than this one. So in that case, what we would be doing is looking for a value for the second mean that's far enough away that it's on the extremely low end of the distribution or the extremely high end of the distribution in the tails, and we're talking about in either one of the tails, so it's a two-tailed test. Because in this kind of hypothesis, we're not indicating a particular direction, we might find that one mean is significantly lower than the other, in which case we would find it over here in this lower tail. Or we might find that the value of this other mean is way over here in the upper tail. We're not sure which direction it's going, which is why it's non-directional, which is why we do a two-tailed test. But when we hypothesize that one value is greater than another, or better, or more than, or less than, anything like that, we call that a one-tailed test. And that's because only one side of our distribution, so only the upper side or only the lower side, is going to have a region of rejection. So both of these little tails are regions of rejection in a two-tailed test. But in a one-tailed test, one side won't exist. We'll only have one region of rejection, either on the upper side over here or on the lower side over here, but not both. Now, one thing here that's important to realize is that if we set a 10% probability level for both a two-tailed test and a one-tailed test, so let's say we're running two different tests, we have two totally separate hypotheses, we're running two unrelated tests, and for the one-tailed test, we want to say that we have a 10% probability level. In that case, if we had this hypothesis here where we're saying this mean is greater than this mean, we already have mu sub 1 here. In order for this to be greater than mu sub 2 is going to be somewhere down here on the lower half, or at least that's what we're hypothesizing. So if we set a 10% probability level, that means that the entire 10% has to go here in this lower tail. But if we set a 10% probability in a two-tailed test, we have to divide that in half and allocate 5% of the probability for the upper tail and 5% of the probability for the lower tail. Keep in mind, though, that if we do this 5%, so let's say this line right here indicates 10% of the distribution, so this is the bottom 10%. But if we do 5%, that might mean that our line moves, let's say, down to here on this side and then down to here on this side, such that this is now our 5% on one side, and this is our 5% on the other side. What we notice over here on the left is that our region of rejection is now different. So if we set this 10% probability level and we do a one-tailed test, then our region of rejection is this entire area here. So we'll say region of rejection, because it goes all the way up to this 10% line. But if we do a 10% probability level with a two-tailed test, our region of rejection drops down to this 5% level because we can only put 5% over here. So then the region of rejection is only to here. That's important because if we find that this other mean here, mu sub 2, if that were to fall, for instance, let's say right here, and we say that this is mu sub 2, that would then fall within the region of rejection for a one-tailed test, which would cause us to reject the null hypothesis and therefore provide support for our alternative hypothesis. But if we were doing a two-tailed test, this would fall outside the region of rejection because we're outside this 5% window right here, which means that we would fail to reject the null hypothesis, and we would therefore fail to provide support for the alternative hypothesis. So it matters whether you pick a one-tailed test or a two-tailed test. It could make a difference about whether or not you're able to reject the null hypothesis. What we can basically see here is that the two-tailed test, we'll just say the two-tailed test like this, is always more conservative because it makes the region of rejection smaller. This region of rejection at 5% is smaller than this region of rejection at 10%. So if that's the case, if the two-tailed test is always more conservative and you're always going to be less likely to reject the null hypothesis, then when you say, why would you not always run a one-tailed test rather than a two-tailed test? It'll give you a greater chance to reject the null hypothesis since you get this wider interval here. However, we can really only use a one-tailed test when we have good reason to believe that we know the direction of the difference here. So if we feel pretty strongly, or we're pretty confident, that mu sub 1 is greater than mu sub 2, then we could go ahead and use the one-tailed test on this lower half here. But a lot of the time, we're really not going to be sure. We're not going to know whether mu sub 1 is greater than mu sub 2 or vice versa. And if that's the case, if we're not sure, if we don't have good reason to believe that we know the direction, then we really need to use a two-tailed test. And that's just going to force us to find a more extreme sample mean in order to fall within this smaller region of rejection that we get for the two-tailed test. Now before, to look at these one and two-tailed tests, we talked about picking a 10% probability level. What this means, this 10% probability level, it means that 1 out of every 10 samples will cause us to reject or accept the null hypothesis incorrectly. Now from this, we can say that there are a few types of errors that we could commit. So let's say that the null hypothesis is actually true. If we accept the null hypothesis instead of rejecting it, then that's the correct thing to do. We have no problem there. Or if the null hypothesis is actually false and we reject it, then we've also done the correct thing there. We have no issue at all. So all of that is totally good. But if we pick a probability level of 10%, what we're saying is that for 1 out of every 10 samples that we take, we're either going to commit a type 1 error or a type 2 error. A type 1 error is when the null hypothesis is actually true, but we end up rejecting it because our sample mean falls within the region of rejection. 1 out of 10 sample means is going to fall within that region of rejection, and we're going to go ahead and reject the null hypothesis, but we shouldn't because the null hypothesis is actually true. That's a type 1 error. A type 2 error here is when the null hypothesis is actually false, and we should reject it. So our sample mean should fall within the region of rejection, but 1 out of every 10 times, it doesn't. And so, because it doesn't fall within the region of rejection, we're going to accept the null hypothesis even though we should have rejected it. So with a type 2 error, because the null hypothesis is actually false and we should reject it, this is an instance where we should have been able to support the alternative hypothesis, but we failed to do so. With the type 1 error here, the null hypothesis was actually true. So we should have rejected the null hypothesis, but we didn't. So this is where we think we have support for the alternative hypothesis, but we actually don't. So we think we're getting supporting evidence, but we're not. This is where we don't think we're getting supporting evidence, but we actually did, we just can't see it. So 1 out of 10 times, one of those two things is going to happen if we pick a 10% probability level. So let's go ahead and summarize and say that a type 1 error is when we think we're getting support, but we shouldn't have. And a type 2 error is where we don't think we're getting support, but we should have. We often call the probability of committing a type 1 error the alpha level, and the probability of committing a type 2 error the beta level. When you pick a probability level for your test, so when you pick a 10% probability level, you're actually deciding how much you want to risk committing a type 1 error, which is why the region of rejection that we sketched here is sometimes called the alpha level. The last thing we want to mention is the idea of significance. which is the probability of obtaining a particular result by chance. We call the significance p. So if we were to say that the p-value is 0.01, it means there's a 1 in 100 chance, so 1 in 100 chance of obtaining the result that we found. Or we could say that the region of rejection is 0.01, or that the alpha level is 0.01, or that the type 1 error rate is 0.01. So if we were to conduct a one-tailed test, like when we looked at our distribution here, we're conducting, let's say, a one-tailed test on the lower half of the distribution because we're saying mu sub 2 is less than mu sub 1, then a p-value of 0.05 would define our region of rejection as this region right here. And it means that our test statistic will have to be greater than the critical value associated with this spot right here. In other words, that the z-value we get will have to be somewhere in this region here in order for us to reject the null hypothesis, which makes sense since we have already defined this as the region of rejection. I want to talk just for a second about something called the p-value because we've mentioned it just briefly. But a p-value or a probability value, the p stands for probability, is the observed level of significance. It's the smallest level of significance at which you can reject the null hypothesis, assuming that the null hypothesis, of course, is true. So think about it this way. Let's say here that we have a normal distribution, and let's say that we're doing a one-tail test, and it's just going to be a lower tail test. If we want a confidence level of 90%, so let's say our confidence level is 90%, because this is a one-tail test, that means our alpha value or alpha level of 10% all has to go in this lower tail. So let's just say that here is our 10% alpha level, and so this whole area here is 10%. Since the p-value is the smallest level of significance at which we can reject the null hypothesis, what we're saying is that the p-value has to be inside this region of rejection. So again, this is the region of rejection where we reject the null hypothesis, versus everything else up here is the region of acceptance where we would accept the null hypothesis. So basically we're saying that if the p-value is inside the region of rejection, if the p-value is less than or equal to alpha in the case of a one-tailed test that's a lower-tailed test, so p would be less than alpha, this is alpha here, and then p is somewhere to the left of alpha, so p is somewhere in here, it's smaller than alpha, then that just says we're going to be in the region of rejection and we're going to reject the null hypothesis. But if p is greater than alpha, it means p is somewhere over here on the right and we would not reject the null hypothesis. Now, the smaller the value of p, the more confident we are that we can reject the null hypothesis. So even if we're doing here a 90% confidence level, which means the alpha level is 10% and the area of this region is 10%, if our p-value is 1% over here at 0.01, we're still going to be more confident about rejecting the null hypothesis than we are if our p-value is, let's say, 8% over here at 0.08. So the deeper we are into this region of rejection closer to the tail, the more confident we are about rejecting the null hypothesis. And the same is true if we're doing a one-tailed test on the other side. So if we have an upper tail test, and let's say this time we want a 95% confidence. Again, this is a one-tailed test and it's just the upper tail test. Nothing to do with what we just did over here. We're just using the same distribution. So if we want a 95% confidence, that means our alpha level here is 5%, so 5%, which is the area under the distribution or the area of this little tail over here. Which means that if we're going to reject the null hypothesis, then our p-value has to be greater than or equal to alpha because it needs to fall in this region over here. It needs to fall to the right of alpha. So P has to be somewhere greater than or equal to alpha if we're going to reject the null hypothesis. If it's less than alpha for this upper tail test, we're going to be somewhere over here in the region of acceptance. And just like before, the deeper we are into the region of rejection, so maybe we're all the way up here at 0.99 or 99%, we're more confident in rejecting the null hypothesis than if we're right here at, let's say, 0.96 or 96%. Now, this was for a one-tailed test, so a one-tailed test, and this was for a lower tail test, and this was for an upper tail test. But what about if we do a two-tailed test? So this time, we're going to look at a two-tailed test. In this case, if we want 95% confidence level, that means our alpha level is going to be 5%. Because it's a two-tailed test, we have to divide this 5% into two tails. Well, 5% divided by 2 is 2.5% each, or 0.025. So that means I can draw two tails that are symmetric about the mean, and the area over here is going to be 0.025, the area of this little tail region. The area over here is going to be 0.025. If I'm anywhere in the lower tail, I'm in the region of rejection. If I'm anywhere in the upper tail, I'm in the region of rejection, because in a two-tailed test, you have two regions of rejection, one on the lower side, one on the upper side. And if your sample statistic falls so far away from the mean that it falls in one of these small regions, then you can reject the null hypothesis. And then, of course, in the middle here, we have the region of acceptance. In the case of a two-tailed test, when it comes to the p-value, all we're saying is that if the p-value is greater than the alpha value, then we do not reject the null hypothesis. So we're not really saying that the p-value is either really small or really large. What we're saying is that if the p-value is greater than the alpha value, so in this case the alpha value is 5%, we're saying the probability of rejecting the null hypothesis is greater than 5%. But if that's true, then that means that our sample statistic isn't going to make it over here into these small tails, which are the regions of rejection. We're going to land somewhere, just outside of the region of rejection somewhere if the probability, the p-value, is 6% instead of 5%. So for a two-tailed test, if the p-value is greater than the alpha value, then we do not reject the null hypothesis. But if the p-value is less than or equal to the alpha value, then we can go ahead and reject the null hypothesis, because that means that the probability of our sample statistic landing in the region of rejection is going to be within that alpha value, which defines the boundary of the region of rejection. As we've already talked about a bunch before, a lot of times we're interested in something like a population mean, but we don't know what it is, and we can't survey everyone in the population because the population is too large or too spread out, we don't have access to them, whatever the case may be. So we can't figure out what a population mean is. And so in place of asking everyone in the population, whatever our question is, or collecting data about everyone in the population, instead we take a sample of the population and then we find the sample mean, which is x bar. What we're hoping is that we can use the sample mean as an estimate for the population mean. But again, as you know, this sample mean might be a good estimate of the population mean, or it might not be. We could take lots and lots and lots of samples from the population, compute the mean for each sample, and we might find a different sample mean every single time. So if that's the case, which sample mean do we use to represent the population mean? How do we know which sample mean gives a good estimate of the population mean? We have all of these questions. So sometimes, instead of just calculating a sample mean and using that as an estimate of the population mean, sometimes instead we'll calculate what's called a confidence interval. And we do that by finding the sample mean and then with a little math, constructing an interval around the sample mean that describes how confident we are that the interval we constructed around the sample mean overlaps the population mean. So let's think about it another way really quickly with an illustration. Let's say the population mean has a value of 10. So we wouldn't actually know this normally, but let's just say we could know that it has a value of 10. And now we'll put that aside for a second. So we take a sample, we calculate the sample mean, and let's say we get a value for the sample mean of 7. So if we were to graph the sample mean on a number line, so let's say the sample mean is right here at 7, so this is x bar, the sample mean, we might construct a confidence interval around this sample mean that maybe goes all the way from 2, 5 less than 7, up to, let's say, 12, 5 more than 7. And what we're trying to do mathematically is say something like we're 90% confident or 95% confident or 99% confident that the actual population mean lies within this confidence interval from 2 to 12, so that it lies somewhere in this interval. We kind of took a peek behind the curtain here and found out that the population mean was 10. So in this case, the population mean actually does lie within the confidence interval here, but we wouldn't normally know that. We would just construct this confidence interval. Now, if we're constructing intervals with what we say would be like 90% confidence, for example, if we're constructing confidence intervals with 90% confidence, what we're saying is that we're going to take samples from the population over and over and over again. So we're going to take lots of samples. We're going to find the sample mean of each one, and then we're going to construct a confidence interval for every sample using the same process. If we do that, we'll talk about how to do this in a second, but if we do that at a 90% confidence level, what we're saying is that 9 out of every 10 of our confidence intervals are going to overlap the actual population mean. So this is really important. The population mean, it has a real, actual, fixed value. We don't know what that is, but it doesn't move, so it might be here. If we take another sample, it might have a mean of 12, and then we might build our confidence interval like this for that sample. Then we take another sample, maybe it has a mean of 10, and then we construct our confidence interval like this. And then every once in a while, we're going to get a sample where maybe the mean is 14, and our confidence interval looks like this. But we're going to get a confidence interval for every sample that we take. And what we're going to see is that this confidence interval overlaps the mean right here. This confidence interval overlaps the mean here. This confidence interval overlaps the mean here. This confidence interval for 14 does not overlap the mean. So as we take more and more samples, compute the sample mean, and then build a confidence interval for each one, if we are doing that at a 90% confidence level, that means that 9 out of every 10 of our confidence intervals will overlap whatever the actual population mean is. So here we had 3 that overlapped and 1 that didn't. But as we take more and more samples, we expect that 9 out of 10 confidence intervals will overlap the actual value of the population mean. So how do we actually find a confidence interval? Well, we have a formula for the confidence interval. So we give a confidence interval as AB. So A is the lower end of the confidence interval. In the case of our sample here, where we had a sample mean of 7, and then the confidence interval from 2 to 12, 2 was the lower end, 12 was the upper end of the confidence interval. So we would express that particular confidence interval as 2, 12 in place of AB. So the confidence interval is AB, and that's going to be equal to the sample mean plus or minus what's called the critical value. We can write it as Z star, or sometimes we write it as Z of alpha over 2. We have z star, and then we multiply that by sigma divided by the square root of n. So sigma is our population standard deviation, and n is the sample size. So we understand sample mean. We know how to find that. We know population standard deviation, and later on we'll look at what we do when we don't have a value for population standard deviation. And we know n, the sample size. Maybe there were 25 people in our sample or 100 people in our sample or whatever it was. We would plug that in for n. So we know everything else, but what is this z star value? Well, it's called the critical value, and this is just the z-score that's associated with the confidence level that we choose. So remember before we said we were constructing these confidence intervals with a 90% confidence level? Well, we would start with that confidence level, whatever confidence level it is that we desired. We would look that up in a z-table, and we would find the associated z-score, and we would plug in that z-score for this critical value z star. The reason that we also see this z star expressed as z sub alpha over 2 is because confidence intervals you can always think of as two-tailed tests. We never have a one-sided confidence interval. Confidence intervals are always two-sided. Remember that the alpha value or the alpha level represents the region of rejection. So let's say we imagine a distribution like this around 10 here. Our confidence interval goes from here to here on our distribution, and these tails, these are the regions of rejection. So this is basically saying take the alpha level, which gives you the total percentage of both the right tail and the left tail. So alpha totals up both of these percentages, combines them into one sum. But you're saying alpha divided by 2, which means you're only looking at one tail. You're dividing the area in half, which is what we do here. So we're only looking at one side. And so we're basically saying the z value is the critical value, gives this boundary between the region of acceptance and the region of rejection. So that's why it kind of makes sense to put it in this kind of notation. But either way, this notation means the same thing, the z star or the z alpha over 2. We can also think about this confidence interval formula as the sample mean plus or minus, and then this right here is what's called the margin of error. So we can go ahead and label that the margin of error. And that's because really what we're doing is, again, if we take this example here where the sample mean was 10, sample mean's 10, so we're saying the confidence interval is 10 plus or minus some distance. So if that distance is 5, so the distance from 10 to the right edge of the confidence interval is 5, then the distance from 10 to the left edge of the confidence interval would be 5. So we're saying 10 plus or minus a margin of error of 5 units gives the full confidence interval from the left edge here to the right edge here. So we could also express a confidence interval just as 10 plus or minus 5, or as 5 all the way to 15. So we just like to call that out and define that as the margin of error. Now, sometimes people wonder, we mentioned before, a 90% confidence level. Well, you might be wondering, why wouldn't we always just pick a 99% confidence level or a 99.9% confidence level? Obviously, it sounds good or better to be as confident as possible. Well, the problem is there's always trade-offs. So the higher the confidence level that we pick, the wider our confidence interval is going to be. And even though we want a higher confidence level, we want a narrower confidence interval if we can get it, because the narrower the confidence interval, the easier it is for us to hone in on the actual value of the population mean. So confidence level and the width of the confidence interval are kind of pulling against each other. One way that we can narrow the confidence interval is by increasing our sample size, because as the sample size goes up, the margin of error is going to decrease, which is going to narrow our confidence interval. Now, I want to look at an example, but before we do, I want to talk one more second about confidence levels, because remember we said before that when we pick a particular confidence level, that's going to be associated with a z-score, that gives us the critical value or the boundary line between the region of acceptance and the region of rejection. There are some confidence levels we use all the time, like 90%, and they're always going to be associated with the same z-score value because 90% is really just the area under this probability distribution. It's going to represent 90% of the area, and that's always going to be attached to the same z-score. So if I want a 90% confidence level, I'm always going to use a z-score of plus or minus 1.65. If I want a 95% confidence level, I'm always going to use a z-score of positive or negative 1.96. And if I want a 99% confidence level, then my z-score is going to be positive or negative 2.58. I wanted to write these down because we use these particular confidence levels, 90, 95, and 99%, all the time. So let's walk through an example where we have a machine that's filling water bottles, and the amount of water that the machine puts in each bottle is normally distributed with a standard deviation of 1 ounce. We're going to take a sample of 100 bottles, which means N is going to be 100, and we measure the ounces of water in each bottle, and we find that the sample mean is 16 ounces. So on average, there are 16 ounces of water in each bottle of our 100 bottle sample. So what we want to do now is find the confidence interval for a confidence level of 90%. So based on what we already know, we can say that our confidence interval AB is going to be equal to x bar, which we already know is 16, plus or minus the margin of error. We don't know the critical value z star yet, but we do know population standard deviation is 1 ounce, and we know that the sample size is 100 bottles, so we get square root of 100. So notice that we have everything we need for our formula except the critical value z star. We get that from the confidence level of 90%. So keep in mind that this 90% confidence level, when we go to look it up in our z-table, remember that a z-table always gives us just the probability or the area below whatever value we look up. So if we were to look up 90%, we would get all of the area here below that 90% level. But for a confidence interval, we always have to do a two-tailed test. So we don't want to leave the remaining 10% outside of this 90 up here in the right tail. We want to distribute it half and half on both sides of the distribution. So we want 5% over here, and we want 5% over here, which means that if we want 5% on this upper half, we actually need to look up 95% because that would be the boundary between the rest of the probability distribution and this 5%. So we want to look up 0.9500 in our z-table if we want a 90% confidence level. So you always want to take your confidence level and you want to say 100% minus your confidence level. So 90% is going to give you the difference there, so 10%. Then you want to take that and divide it by 2. So 10% divided by 2, and you get 5%. Then you want to take 100% and subtract that result, so minus 5%. The result is 95%, and this is the value you want to look up in your z-table. So again, that's 0.9500. We look this up in the body of our z-table, and what we'll find is that it's associated with a z-score of 1.65. So right here, this spot is a z-score of positive 1.65. Here at the lower boundary of 5%, that is a z-score of negative 1.65. And that would be associated with that lower 5%, so 0.0500. So that's how you find the associated z-value, and so we're going to put in then 1.65. When we do this, what we get is 16 plus or minus 0.165, or if we rounded to the nearest tenth maybe, we could say 16 plus or minus approximately 0.2. So 16 would be our sample mean, 0.2 would be, remember, our margin of error, and the confidence interval would be 16 minus 0.2, which would be 15.8, all the way up to 16 plus 0.2, or 16.2. So what we could say then is that we are 90% confident that the interval 15.8 to 16.2 overlaps the actual value of the population mean. Now, we did all of this based on sigma being known. So we did this whole problem based on the fact that we knew population standard deviation. But a lot of times you're not going to know population standard deviation. So in that case, what do? Well, obviously the only thing you have to go on is your sample. So instead of population standard deviation, we compute sample standard deviation, or the standard error, and then we say that our confidence interval is just given by AB equals the sample mean x bar plus or minus still the critical value z star, but then multiplied by the sample standard deviation, or the standard error, divided by the square root of our sample size n. Keep in mind, though, that we can only use this formula when we have a sample size greater than 30. So n has to be greater than or equal to 30. The reason is because only for large samples where n is greater than or equal to 30 does the sampling distribution closely mirror the normal distribution and therefore allow us to use the z-table. So we can only use the sample standard deviation if our sample size is greater than or equal to 30. So then what do we do when we don't know population standard deviation and our sample size is smaller than 30? We have a small sample. Well, in that case, we have to use what's called the t-distribution. We can't use a z-table. And that's because the z-table gives us probabilities for a normal distribution, for a normal curve. But if our sample size is small and we're using sample standard deviation, then our curve isn't going to mimic a normal curve. The curve's going to look a little bit different. In fact, it'll be a little bit flatter. So we need a different table to give us values for this critical value. And that table is what's called the t-distribution. Now, the t-distribution is similar to a normal distribution because it is bell-shaped. It has this bell-shaped curve, just like a normal distribution. It is symmetric about the mean, and the area under the curve is 1, or 100%, just like a normal distribution. But the shape of the t-distribution actually depends on what's called degrees of freedom. And you find degrees of freedom, we can write this down here. You find degrees of freedom, which we often abbreviate df, using the formula n-1. So if your sample size, for example, were 10, then your degrees of freedom would be 10-1, or 9. So in a sample size of 10, you would have 9 degrees of freedom. And the shape of your t-distribution will depend on how many degrees of freedom you have. The smaller the number of degrees of freedom, the flatter your t-distribution is going to be. So if we were actually going to sketch the t-distribution, it would maybe look something like this. It would be flatter. But as you have more and more degrees of freedom, the t-distribution gets taller and taller like this. Once you get to about 30 degrees of freedom, because your sample size is 30, that's when the t-distribution then basically mirrors exactly the normal distribution, which is why we can get away with using the normal distribution and the z-table when our sample size is large, when it's greater than or equal to 30. So, as you might have suspected, when we're dealing with a situation like this where we have a small sample size, we have to use the t-distribution, and we don't know population standard deviation, our confidence interval is going to be given by AB is still x bar plus or minus. We're still going to have sample standard deviation, and n is still going to be our sample size. But instead of the critical value z star, we have the critical value, or the t value, t star. And you'll find the t-distribution in any stats book or a formula sheet for probability and statistics And it looks really similar to the z-table, except that what you do is down the side, you look for the degrees of freedom. So you'll see in the table listed down the left side degrees of freedom as 1, 2, 3, 4. So in this case, if we had a sample size of 10, we would go down until we found 9 degrees of freedom. And then you cross-reference that with either your confidence level, so in this problem, 90%, or with your upper tail probability. So remember we said that when our confidence level is 90%, we actually put the 90% in the middle, leaving 5% on each end. So either you're going to look up 5% for your upper tail probability, or 90% for your confidence level. You'll find in a t-distribution that those two things are in the same column because they mean the same thing. This is upper tail probability, this is confidence level. So down the side of the t-distribution, you'll find the degrees of freedom. You'll look yours up, and then you'll go over until you find either 90% confidence level or 5% upper tail probability. Those will be in the same column. And then where those meet in the body of the table, you'll get your value for t star.